Yeah, good morning and welcome to cold San Diego. Happy to have you with us again. We have our final session of the Battery Chemistry for Automotive Applications Symposium. This session is devoted to novel cell and electrode designs. 3 speakers, and then we have a Q&A, and then we move over to a coffee break and to the plenary keynote program of this week. It's my great pleasure to introduce one of our 3 great speakers this morning, Surya Moganty, Dr. Surya Moganty, the Chief Science Officer of Psionic Energy. Surya gained expertise in advanced battery materials, liquid electrolytes, electroanalytical and organic synthetic chemistry, and process engineering. And with this, he's responsible for the success of the company's research and development efforts on the silicon battery. He received his PhD in chemical engineering in 2009 from Clarkson University, worked as a postdoc at Cornell University, and at Cornell he co-invented the technology that was licensed by Psionic and that we will learn about today. Welcome, Surya Moganty. Good luck, my friend. So this is the slider, this is the pointer.
Thanks. Thank you. Thanks for the kind introduction, and also I'd like to thank the organizers for giving the opportunity. I have a tendency of speaking fast. I try to slow down, but I'm open afterwards if you have further questions. Today we're going to talk about unlocking silicon from how do we control the expansion. Before we go into the talk, I would like to introduce the company. Like Martin was telling, it came out of Cornell University. We were Gnomes Technologies prior to that, working on advanced electrolyte designs for multiple battery chemistries, including lithium metal, lithium sulfur. And then recently we acquired an IP from University of Colorado. By combining these 2 IPs, one is on the electrolyte and other is on the silicon anode. Under the Psionic Energy banner, we're developing high energy, low cost batteries designs, and our business model is licensing. So the company is located in Kodak Industrial Park. We're fortunate to have such facility where we can actually do abuse testing of the batteries. We have state-of-the-art battery abuse testing. This is because of the electrolyte development. We were able to handle up to 40 amp hour cells. And we also have more than 1,000 cyclists so that we can do a battery R&D very quickly. At the same time, I would like to thank our VCs who are supporting the company for the last couple of years. So then moving on to the talk, anode is the missing link in order to increase the energy density of the next generation cells, right? We know graphite is incumbent, and then silicon and lithium are the best candidates. If you look at all those key performance indexes for those material level, silicon is definitely in the sweet spot of increasing the energy density. That's the reason why current batteries use already 5 to 10%. But increasing the loading of silicon can dramatically also offer higher energy densities without changing the manufacturing processes. But there are multiple challenges. Everybody knows about them. I'm not going to spend time. But what I have done here is what is the industry approach of solving these different level of issues. Material level, you can do engineering on the particles. Then on an electrode level, either you can dilute the silicon, that's what we're currently doing, or come up with nanostructured anode designs where you grow the silicon onto the copper foil like we heard yesterday. On a cell level, you can come up with complex cell designs, pre-lithiation, etc. But all these things, again, for commercial application, in my humble opinion, it's cost, manufacturing, ease. So other issue with limited loading of silicon is because we are mixing with graphite, right? Because graphite is intercalation, silicon is alloying. When you mix them, there is competition, lithium crosstalk between graphite and silicon. There's a lot of literature nowadays coming up understanding the interplay between silicon and graphite. For example, when you're charging the cell in a silicon graphite composite anode, the silicon will get utilized first, like I was showing here. The reason for that is the higher operating potential compared to graphite. If you're doing discharge, it's opposite happens actually. Graphite gives off and then silicon will come into play. But in order to coexist with graphite, this is what we're currently doing, you need to engineer the silicon on particle level to overcome those reactivity and expansion challenges. To unlock the true potential, I think graphite must be eliminated. It's just my humble opinion. But if you do that, there is consequences. This is a nice article from Argonne National Lab. What they've done is they looked systematically what happens when you take the graphite out. As you can see, expansion follows silicon pretty much. The more you put in, the more you have to deal with it. And also there is a lot of forecast coming from industry experts saying that there will be increase in the silicon loading in the graphite, but the loading in the anode is incremental in nature because of the problems that the silicon presents. Then, the question that we asked ourselves is it possible to work with higher loading, pretty much, graphite free anode designs? So yes, if you can improve the electronic conductivity of the silicon, right? And if you can secure the silicon from electrolyte attack, which is don't have to repair the SCI so that you don't have to consume the lithium ions. Second is, the most important is you have to have an anode architecture that can allow this kind of breathing process that silicon is gonna provide to the anode, right? So innovations in the binder and electrolyte, that's where we are coming from, are key for doing that. So there's again a lot of literature on binder designs. Silicon definitely needs a new type of binder, and there is a lot of patents and publications available in literature talked about different types of binder designs, but mostly there is no standard for silicon only anode designs, but people are trying PA and CMC mix as a standard binder to at least get some data. So then going to our technology, this slide just showcases the science behind what we're doing, right? It's a simple roll-to-roll mixing process. It's a solvent, and you dissolve silicon and polymer. During the electrode drying process, the polymer gets activated. Like I was showing in this cartoon, we are actually providing the particle level and electrode level protection using a simple roll-to-roll and polymer binder system that we have. So some of the cross-sectional image that I'm showing here showcases, the ultra-thin anodes. Because you don't have graphite, you can create really thin electrodes compared to the state-of-the-art 4680 cell, which anode thickness is about 250. You can get up to 50 on each side, so that's 5 times thinner. So you can enable the fast charge as well. So the dual effect, we call it conductive glue, is going to protect the silicon from SCI and electrolyte attack, and at the same time, allow it to breathe in and breathe out. Again, some of the pictures to showcase that it is a roll-to-roll. We have 2 coating events every day, every week. We close to 50 feet is what currently the prototype manufacturing we're currently doing on multiple silicons. So then let's look at the proof of concept, right? So in order to test this, what we have done is we bought silicon, crude micron silicon from Alibaba.com, and then use them to see if we can enable, given the science behind this particular coating technology that we have, right? So as it works, so what I'm showing here is a half cell data of double-sided electrodes, and the cross-sectional image of the anode, where you can see it's a crude micron silicon with irregular size, nicely distributed and protected by the binder coating. So this allows the silicon to stay calm and then don't react with the electrolyte too much. At the same time, allow it to provide the capacity that you required for. So these are very thin, 3 to 3.5 milligram per centimeter square coatings. They're already giving close to 8 milliamp per centimeter square aerial capacity. And this technology is truly agnostic, right? It's not just for the micron silicon, it can work with anything. So we started working with other material suppliers, where we started to test their material in a graphite-free environment. And some of the data I'm showing here is half cell data. Again, it follows the material properties, right? The silicon oxide we know has very low Coulombic efficiency. But if you go to the silicon-rich materials, Coulombic efficiency is not, first cycle Coulombic efficiency is not an issue, so you can get over 90%, which is almost similar to what a graphite is. But the challenge is the delamination, as I was showing. If you're using a regular binder system, the electrode expands. It's not just G, it's also XY. When you start working, you'll realize. And that actually delaminates from the current collector. With our conductor glue, we don't have that challenge. And we can truly unlock the potential of the silicon material. So other breakthrough that we have is on the electrolyte designs. This is again coming from the GNOME's technologies work. So what we are doing currently is using DFT as a means to down select, because we have like made more than 700 new additives. How do you test them? You cannot test everything. So we're using this technique, very well known DFT method, to understand the LUMO homos. So you can pick what is the right additive for SEI on the anode, also on the same side on the cathode. So we use that to down select some additives, and these can help form an SEI on the silicon surface. And actually we use the binder as a protection, and then the SEI forms either on that or inside. So here is again proof for that. So what we have done is we've made R&D pouch cells and tested them up to 4C charge. FEC is a well-known additive. It's a must-have if you're using silicon, but it also presents other challenges. The FEC is responsible for forming this lithium fluoride rich and also organic layer. Along with our additives, we were able to further change the SEI that will help to improve the rate capability as well. So these additives contain elements like phosphorus, fluorine, and nitrile groups, which helps to form a better SEI, because you definitely need a new additive when you're using a graphite-free anode design, such as what we're doing here. Then let's look at this performance data, right? So we have this crude micron silicons. That's the SEM of the particles. Then we made cells. And you can see they work. You're getting close to 400 to 450 at 80% capacity. This is 811 one-layer cells. But however, this is not enough, right? Because you have to think about the aerial capacity. In order to hit above 300 watt-hours per kg, you need minimum 4 milliamp per centimeter square. Most of the data that you see, if it is only 2 to 2.5, then the cell energy would be even lower than what a current lithium ion is producing. Then we started testing at higher loadings. So you can see when the crude micron silicon doesn't stand, right? So you can see the red graphs are the same, but higher loading. And the degradation is accelerated. The reason for that is, even though you're providing the conductive pathways and then protecting the silicon, the micron size silicon breaks. And during lithiation, the broken particle actually contains the lithium. Those trap the lithium, hence you have a capacity fade. So then in order to solve that, we started working with these engineered silicons, right? So you can see this plot shows some of the data that we collected in the R&D cells. So as you can see, if you increase the loading, you can get close to 400 cycles without any issue. Further optimization of the binder and electrolyte system, we can achieve close to 1,000 cycles, right? So again, none of these have any graphite, and we are utilizing very high silicon, around close to 1500 milliamp per gram. The challenge is the expansion, because they all look nice on an R&D cell, but when you start making multi-layer cells, the silicon true nature will come out. So these are some of the teardowns I'm showing you, where we don't have the delamination because of this nice binder design and electrolyte design we have. But what we have is another challenge, which warps the electrode, and also, as I was saying, there is dimensional change, not on the Z, XY, and that can, if you're using a 10 micron foil, copper foil, you have to use to get energy density, then there will be copper breakage happening. But how do you balance this, right? So we can further modify the anode design and other things to overcome. That's what I'm going to show you. So here is an example where when you apply a very low compression force on those electrodes, these are a lot bigger also. The size of these electrodes is about 120 centimeter square. So these are like A6 paper size. And when you pair that with 4 milliamp per centimeter square, you can either do a controlled way of utilizing the silicon, or applying small pressure. We were successfully overcome this kind of warpage issue. The beauty with this design is we don't have a delamination, right? At least one part of that is gone. Then we need to handle these warpage so that you don't have challenges when you are cycling multi-layer cells. These all look good when you are measuring on the anode level, right? So this is what I've done is in order to compare ourselves, we have taken the DOE report recently published, where they compared different silicon materials at different loadings, and what you are comparing here is the anode capacity versus anode level expansion. Even graphite does expand when you're doing the very first time lithiation. So our designs are 3 times and even higher in terms of anode capacity, but still the anode level expansion is around 20 to 30% on anode. So what does it mean on a cell level? So in order to truly test that, you have to build a multi-layer cell. So given we have a champion anode, cathode, and electrolyte combinations, we recently started building these 2 amp hour, 3 amp hour pouch cells and started understanding the electrode level expansion or a cell level expansion. What you're seeing here is, again, cycle life data for these cells that are undergoing at C by 3, C by 2, and also room temperature and 45 degrees. And we were able to successfully take the 1-layer cell data and then scale that into multi-layer cells. What is important here, other thing that I want to point out here is when you're forming, you're experiencing, we see in around 5% expansion on a cell level after formation. After that, that's what actually the customer will see, because they will receive cells after formation. So you have to start thinking about what is the expansion after formation, right? So what I'm showing here is the total expansion of the cell going from formation to 300 cycles, but truly the expansion that the customer will experience is only 2%, even with the 900 milliamp per gram utilization on the anode side. So this is the goal of our journey, is to use these R&D cells. That those are 1-layer cells. We've been building 50 cells, give or take, on an average of on a weekly basis. So using that knowledge, what we're trying to do is optimize the anode composition, which is what is the right kind of molecular weight of the binder and the percentage of conductor carbons, etc. Then what is the right electrolyte design for a given electrode and anode pair, cathode pair, right? We use DOE, which is using Taguchi methodologies. We can narrow these designs into few champion combinations, and those champions go to the scaled up cells, which are about 2 amp hours. One thing that I want to point out is when you are testing on 1-layer cells, everything look very nice because you have electrolyte that's pretty much flooded the cell. So that's not the case when you are building multi-layer cells. There will be some challenge between R&D cells and then when you scale up. So here we reduce the electrolyte amount, balance the N2P, and also verify the cell level expansion. Then finally, take those best candidates from these and then make 20 amp hour cells, which we will be doing the first half of this next year. Those 20 amp hour cells will have the performance minimum 360 watt hours per kg, because we are already tripling the anode capacity and utilizing more than 4 milliamp hour per centimeter square on the cathode. So hopefully with that, I've at least convinced that we have a technology that's truly agnostic to silicon. So we are a cell developer. We're not working on the silicon materials. Our goal is to enable everyone else silicon in a graphite-free environment in a roll-to-roll coating methodology. And other thing is important is also the electrolyte design. You have to do that from the beginning because it's silicon, it's not graphite. So some of the knowledge can be applied, but you need to redesign the electrolyte. And the swelling of the silicon, we have to understand from all levels: particle, electrode, and cell. And pre-lithiation is definitely advantage if you can use it, but we are not using it as of now. So with that, what I want to do is, do not fight the silicon problem. We have to learn to work with it. Thank you.
Yeah, Surya, thank you. I'm a big Marvel fan, so thank you for this final slide. Okay, yes. Next speaker is Dr. James Wilcox from Innovix. James leads Innovix Mobility, and doing this, he is adapting and developing Innovix battery technology to meet EV specifications and technical demands. James joined Innovix in 2008 as part of the core engineering team, and then had many different positions in Innovix, and yeah, now he's vice president for mobility. And yeah, welcome, James Wilcox.
Thank you. Thank you, Martin. Thank you for everybody being here today. I'm really excited to be able to share some of the work we've been doing at Innovix in terms of developing a new cell architecture that really kind of helps us unlock the potential of some of these next generation materials. And I'm really excited to talk about, after the conversations yesterday, several presenters highlighted the mechanical issues that are arising as you try to put lithium and silicon into these cells, into traditional cells, and the failure modes. And several people highlighted the need to start thinking about the solutions at a system level and not just the material level, whether that be the module or the pack. What I hope to do today is to convince you that we can do some of that mechanical work at the cell level too. So some disclaimers. We were lucky enough to go public last year to support our consumer business, but unfortunately that comes a lot of overhead, so you can read at your pleasure. Just to start, I just want to give you some things I want you to be able to walk away with about our architecture. For one thing, we've developed a material agnostic cell platform. Right? This means we can really work on any material, but really it excels in enabling these next generation chemistries that really require either high stack pressure or need to accommodate large volume changes like silicon. And if you're able to do that and increase the silicon content or increase these material contents, you can really unlock step changes in energy density. The other element I want to talk about today is the thermal performance we can get. Just fundamentally from building the cell differently, we believe we can unlock an order of magnitude improvement in terms of internal cell temperature gradients, which can change how you think about not only cell performance, but also how you do systems design. If you also build the cells differently, you can unlock different ways to improve robust, abuse tolerance. For example, we've talked about break flow technology that we've invented that really increases the tolerance to internal shorts. I'm not going to talk about this today, but we've talked about it at AABC in the past. And if you want more information, please go to our website or talk to us offline. And the other element I want to highlight is the fact that we've been doing this for a long time. The company was founded in 2007. We have over 100 patents with significantly more in the works, and that cover both the architecture and the process. We think we're in a really good position as we look to enter the mobility space. And the other unique thing that we have that not many of our competitors have is we're scaling up production today. Right? We are building cells for the consumer space out of our factory in Fremont. And these are going to some of the world's leading consumer electronic OEMs. And so we're already going through that learning phase, that manufacturing hell phase. And we're taking all that learning and building it into our EV strategy as we move forward. So this is our factory in Fremont up in the Bay Area. We're located just across the road from Tesla. This is where our initial consumer lines are located. That business has gotten really successful based on our energy density that we were able to provide to our customers. And we've been able to develop a revenue funnel of over $1.4 billion with over $400 million in design wins. And so we're really excited about this. If you're ever up in the Bay Area and you'd like to tour the facility, please reach out to us. We really think that seeing the assembly lines and the manufacturing space really helps people understand our technology in a way that we just can't convey in a forum like this. But we really love to walk through and talk about what we're doing and show people what we're doing. So before I talk about our solution, I want to talk a little bit about what the problem is, right? So I think everybody here knows about traditional cells. They've been optimized over the last 25 years, either through a winding or stacking process. And they really are highlighting the ability to optimize for cells that undergo very low volume expansion, like the silicons, the silicon graphite blends, graphites. But as you start to put in these next generation chemistries, the mechanical problems start to arise. Like they have too much volume expansion, too much stress built up. It can lead to buckling, electrodelamination, material failure, rapid degradation. So one of the things we learned very early, as well as other people, is one of the biggest levers you have is stack pressure. Right? If you put enough stack pressure on a silicon electrode, for example, And we found on the order of 10 megapascals, you can actually stabilize that electrode and get very good performance. But the problem is, if you try to put 10 megapascals on a traditional cell, it becomes a mechanically unworkable problem. So for example, if you take a 30 millimeter by 50 millimeter by 3 millimeter cell, small consumer cell, right, and you need to put 10 megapascals of pressure on it, on the large face of the cell, you're not talking about needing to apply 1.7 tons of force, right? Any mechanical constraint system to do that is going to be bulky, extremely costly, and you can essentially wipe out the value of the silicon. So what we did is we started looking for solutions where we could get to those types of mechanical conditions, but we're no longer fighting the cell itself. Can we redesign the cell in such a way to enable this? And this is what we've come up with. So at the most simplest level, what we do is we stack electrodes. Instead of large sheets, we stack them orthogonally. So same materials, roll-to-roll produce, standard separators, but now we laser pattern them and stack them, and we stack them such that the face of the electrodes is now facing a smaller area of the cell. So now in order to apply the same pressure, the area's gone down, the force goes down. So now we're talking, instead of 1.7 tons on that same 30 by 50 millimeter cell, we're talking about 200 pounds. And those are the types of stresses that thin stainless steel members can take in tension, right? And that's exactly what we do. What you can see here is our electrode stack. We wrap around what we call a constraint, and that handles all the mechanical stresses during formation, aging, and life, right? Beyond this, we've omitted it from this diagram just for clarity, but we then do bus bars on the ends of the electrodes. They tab out to traditional tabs. This gets put into a pouch for our consumer lines today, so it looks no different than a traditional cell. Going forward, we have the opportunity to either continue to do that for the EV space, where we do a pouch, or we can also move it to a prismatic platform. Those 4 things I want to highlight in this talk today. One is the energy density that we can get by changing your cell architecture. I want to give an update on some of the cycle life and counter life that we've been testing. Talk about some fast charge benefits for silicon in our architecture in particular, and then end on a little bit of a new topic for us, which is some of the thermal benefits you get just by stacking your electrodes in a different way. So energy density, we talked about how increasing stack pressure is critical and required to go to high silicon content electrodes, right? That allows us to accommodate those initial volume expansions inside of the cell, right? And we also have this ability in this new architecture to pre-lithiate very efficiently and very directly because we have access to the top and bottom of the cell during formation. So you put all those together, and now we can optimize both the mechanical and the electrochemical and material conditions to get the most potential out of the silicon material. So today we're shipping silicon oxide anodes that are achieving over 900 watt-hours per liter on a cell phone size scale. And we recently announced that in R&D, we've hit over 975 watt-hours per liter. All right, so we believe this architecture allows you to get more of these next-gen materials. And we're in production today doing it. Cycle life and counter life. This one present an update. We talked about this in June, but this work is being done with the Department of Energy as part of the BTO program. And it really is focused on demonstrating silicon-dominant electrodes that can achieve high cycle life and high calendar life. Right? So the program goals are to achieve 1,000 cycles and a 10-year calendar life. Right? And the plot on the left, you can see that we've greatly exceeded that on R&D cells. We're over 1,500 cycles today, and the cycling is continuing very smoothly. Right? On calendar life, the testing's been going on for over a year now, and we're projecting over a 10-year calendar life using the Argon model. So these together, I think, really highlight the ability to get really good performance out of silicon dominant, or in this case, 100% silicon oxide anodes by structurally stabilizing the electrode stack. Right? I'd also like to acknowledge our collaborators on this. NREL is doing a lot of cell modeling for us, and also Mitsubishi Chemical is helping with the electrolyte. The other thing you'll notice is that the electrode loading for these cells is actually quite low. Right? This is 3.6 million powers per centimeter squared. And that was a direct request from the Department of Energy during the start of this program. They really wanted to have an electrode system that taxed the anode and made sure you had no failures on the cathode to really get at the silicon failure mode. So that's why we dropped it way back. And obviously this doesn't make a really compelling energy density cell for EVs. And subsequently, we've run additional cells. Now we're 5.1 million powers per centimeter squared. And you can see the performance is tracking along beautifully, right? So we definitely think we can scale this technology to different size cells, different loading electrodes, and different materials. And it's a really stable system once you get the mechanics worked out. Fast charge. So everybody here knows that silicon should have fundamental advantages when it comes to fast charge. The higher specific capacity allows you to make lower electrodes, thinner electrodes, get reduced transport losses. You also have a higher lithiation potential, right? So you have an extra 100 millivolts, so you have an overhead before you have to worry about lithium plating on graphite. So silicon should be a fast charge material, especially if you can get to a silicon dominant cell and not have to worry about any of the graphite potentials. So we took the cells that we talked about that just passed 1500 cycles, took the same cell design, and we just see how fast we could charge it. So we did 2C to 10C CCCV charges, and you can see the charge acceptance curves on the left. And they behave beautifully. We're able to get up to 5 minutes, 0 to 80% charge time at 10C. It's a small cell. We have a lot of work to do to go work on the thermals and scaling it, but we've done a lot of that scaling already in our consumer line, so we're very confident that we can get it done. The other thing is just doing it once, it's not really significant, right? So we want to really understand what's the robustness of the system during prolonged fast charging. So we selected a 6C charge rate. In this case, it gets us 0 to 80% in just about 9 minutes, fully charged to 99% in just under 15 minutes. And we cycle it 6C CCCV charge, 1C discharge continuously. We didn't do any duty cycles, not every third or fourth or fifth cycle. We really wanted to just push the system as hard as it go and see what happened. And you can see this capacity retention was actually quite strong. So after 400 cycles, we still had 97% of the original capacity left, right? So by being able to go to the silicon dominant electrodes, you really can unlock this potential and achieve stable life, which is really encouraging. So this last topic is something that we haven't talked about in the past, and it's something that is really truly material agnostic. So everything I've talked about at this point has really been about silicon and silicon oxide, because that's what our consumer business is based on today. Even though the platform's completely material agnostic, it can unlock these properties. But this next section really is fundamental to the way we build a cell, right? So this audience is well aware that maintaining very low thermal gradients within a cell is really important to maximizing life and kind of dialing in the operating window to get the most out of the cells. And the problem is, inherently in the cell, the thermal conductivity is very asymmetric, right? You have these very high conductivity planes going down the electrodes, and then in the transverse direction going through the separators and electrolyte, significantly lower thermal conductivity, up to 33 times lower. Which that means really impacts how you design the cell, and how you can extract heat really limits the performance envelope you can work in. And just to highlight this, we've created some one-dimensional steady-state thermal models. We took a reference cell, in this case 173 by 115 by 32 millimeters. So there's nothing unique about it, just a reference cell. And we wanted to compare the conventional stacking methods to our stacking methods on a variety of different cooling arrangements in the pack. And what you're seeing in the middle picture there, and those vertical lines are now that represent the electrodes. The tubes at the bottom represent the cooling tubes in the pack. So in this case, it's a bottom-cooled system with a traditionally stacked electrode system. And what's seen on the left is then a thermal map. And on the y-axis, you're seeing time. And on the x-axis, you're seeing the distance away from the cooling plate. And so what we did is we took these systems, we applied a 2.5C CCCV charge, and we monitored the temperature profile and the distance away from the cooling plate. And you can see in this case, the maximum temperature gradient we develop on this 2.5C charge is on the order of 31 degrees, 32 degrees C. It's quite high. So you have that kind of differential heating in your cell, differential heat, you're gonna have differential aging, performance, kinetics. There's a lot of issues you have to deal with. And so you either have to redesign the pack cooling system, or the system cooling system, or limit your performance in the cell. But another thing you can think about doing is take that same cell, same traditional electrode stacking, but what if you cool on the face? So if you cool on the face, you have access to the large surface area, right? And also you're cooling over a shorter distance. You're pulling heat only for 32 millimeters in this case, not 115 millimeters. Problem is now you're going in the high resistant path. And as you can see here, the temperature profile gets significantly worse. Right now we're over 50 degrees C. So cycling a traditional stack electrode really doesn't make sense. What we can do with the Innovix architecture is we're going to align those two pieces together. Now we're stacking in this orthogonal direction. So the high conductivity path in the electrode system is actually aligned to the large face of the cell, right? So not only that, it's aligned in the shorter dimension of the cell. So putting those two things together, we can extract heat much more efficiently than a traditional cell. In this case, you can see the temperature gradient across the cell is on the order of 2 to 3 degrees Celsius. So having that kind of temperature uniformity allows you to do a lot of different things, right? Now you don't have to worry about overcooking parts of your cell, increasing impedance rise, and things like that, you can now start to think about, can I get more out of my cell, or can I simplify my design system? And so what are the different ways you could think about using this technology? And once again, I want to point out that this has nothing to do with silicon. This is purely based on the fact of the way we design cells, our stacking and electrode patterning that we've developed over the last 15 years. Well, you could charge faster. You simply could just overbuild the system. You can get heat out of your cell more quickly. You can run it at higher C rates and maintain the same life and tolerances. Maybe great, you can end up running a smaller pack, right, for certain vehicles or certain operation modes. You could increase your electrode loading, all right? If you want to maintain the same thermal profiles, you can increase your electrode loading, increase your energy density, reduce your manufacturing costs, and save your costs at the cell level, right? So dollars per kilowatt hour matter at this point. You could just take advantage of the more uniform cell aging, right? Now you don't have to worry about this differential aging across your pack. You have very tight tolerances across the whole envelope. You don't have to worry about impedance growth and defects happening in certain areas in the cold parts of the cell or getting too high on the hot side. But that's all on the cell level. There's the things you could also do at the pack level. And this is something we're really digging into with many of our OEM partners right now, is understanding how can we actually capture this and what does it mean and what can it unlock? One of the big things is you could run warmer coolant, right? And as a chemist, that doesn't always make sense to me. That's why that's great. But it really helps you expel heat from the system much more efficiently, right? If I can get the heat out, I only need to run the coolant relative to the coldest part of my cell. I can up the temperature. My system gets way more efficient. What can I do with that? I can make a smaller radiator, right? I can reduce my compressor size, the weight, and the power, right? Or I could redesign how I do my cooling. I could run at lower pressures, lower flows. I could reorient or remove certain cooling fins and still maintain the same performance. And what's important about this is this all saves weight, it saves volume, and it saves cost at the vehicle level, right? And so this all comes back to the fact that we really believe that when you're trying to solve these problems for these next generation materials and try to get the next step of performance in your cell, you really need to look at the system, right? It's not a materials problem, it's not just a cell problem. It really is, how can you create value all the way through to the vehicle, right? And we really believe that the cell is a great way to start to do that. So that's all I really had today, but I was hoping to talk to you today about our architecture. It's truly material agnostic, but it can really unlock some performance that you can't get in traditional cells, particularly around enabling these next-gen materials and getting more out of them, whether it be energy density, whether it be rate, whether it be thermal properties, right? We're kind of uniquely positioned in this market with our consistent consumer lines. They're up and running. We're shipping today. We're shipping to some of the major OEMs like Samsung, right? These are big deals. We're learning a lot. And that's all feeding into our design study going forward. And I also want to thank for all the OEM partners we're working with and all their insights. I look forward to continuing working with them. If you have any questions, please feel free to reach out to us. Thank you.
Thank you. That was very interesting, especially at the end. Yeah. We are finishing this season with a presentation which is also devoted to electrode and design. Next speaker is Dr. Pascal Boulanger, CTO and company founder of Nava Technologies. Pascal worked 10 years for nuclear energy and then 6 years for solar photovoltaic energy, a very good mix. And then he became the deputy director of a fundamental research center at CEA. That's a very big French institution where he was working with 700 people. At that time, which was in the early 2000s, then he also contributed to the discovery of the material that is the heart of the Nava technology. Welcome, Pascal Boulanger.
Well, good morning, everybody. It's both a pleasure and an honor for me to be here. I come from France, and I will present you our latest results on technology that we have developed more than 10 years ago, At the beginning, it was more for ultracapacitor, but 3 years ago, we started the development of this technology and to see how we can apply it to lithium batteries. So that's the purpose of this presentation. First of all, a few words about NAWA. We are a French startup. We are located in the French Riviera, in the south of France, quite a nice place. We have almost finished our research and development phase on ultracapacitor, and we are now developing our manufacturing tool to manufacture ultracapacitor for different applications. I will not talk about that. In 2000, we have been the pleasure to acquire a US company, a US startup from MIT and University of Dayton, with which we have do a lot of collaboration. Now, this company is called NAWA America, and I'm very pleased to collaborate with American people. It's very, very powerful. Our view is that we will use this material really as the word agnostic was used several times, and it's really an agnostic material that can be used in different applications. I just can show you different target product that we are developing. The first one is ultracapacitor. So why ultracapacitor? It's because it's very simple. You have a carbon electrode, you have another carbon electrode, and you put an electrolyte in between. So it's very simple. With this NAWA America company, what we are doing, we are using the same material. I will explain, but as a reinforcement of carbon fiber composite material to make them almost unbreakable. And it will work as a kind of nano Velcro in between carbon fiber plies. But what I will talk about today is the use of this material for lithium battery to make really high power and energy batteries for traction. So the material that we are developing is this one. It's a carpet of more than 100 billion of carbon nanotubes, all vertically aligned. 100 billions of carbon nanotube per square centimeter. It's huge. It's the same order of magnitude as the number of stars in the Milky Way, or hopefully for all of us, the number of neurons that we have in our mind. So what we want to do, and is really our mission, is to make this material accessible and available for the industry globally, integrated and optimized for different kinds of application. Lithium battery is one application. Our nanotube are, I would say, the best in the sense that that's the best balance between the performance and the safety and the protection cost. They are pure, very low amount of catalyst. They are very long. They can be few centimeters. They are very dense. We can vary the density. There is no bundle. The spacing can vary as well, depending on the process. And we can grow them very fast. In the literature, you can see this material is very promising. You have a lot of articles that show some advantage and some application for this material. I can just illustrate that by two recent publications on making long, vertically aligned carbon nanotube. When I say long, I say that the nanotube by itself is, so I can take this laser, it seems. Okay, the nanotube is continuous from the bottom to the top of the carpet. And here you have a nanotube, a carpet that is continuous from the bottom to the top. It's about 14 centimeters. So it's not an electrode, it's almost a wire. So in terms of limitation, carbon nanotube are always seen as an expensive material, very hard to produce, and very expensive, but in fact, that's not true anymore. The theoretical limit for the growth of carbon nanotubes, so how you make it, is really very high. You can grow a carbon nanotube to 3.6 meters per hour in length here, which means 6 centimeters per minute. So, and for making an electrode, we don't need that thickness. We need only a few tens of micron. So we can go very fast. NAWA has really is a lot of effort on scaling up the manufacturing of VACNT with different equipment. We started within the CEA, and we started the project NAWA in 2012 when we were the first world record to be able to grow vertically aligned carbon nanotube on a silicon wafer, 30 centimeter width. It was a batch process, but it was at that time in 2011, it was the first world record. Then after I created NAWA, And we've been able to demonstrate that we can grow VACNT on a single side, but on a roll-to-roll aluminum substrate. It's important because most of the process operate at 800 degrees, and you cannot use it on aluminum. What we've been able to reduce the temperature down to 600 degrees, and that is compatible for aluminum, and on a roll-to-roll process. And then after, we continue to develop our own equipment to be able to unlock the manufacturing of this material at an industrial scale. So that's what we do with for ultracapacitor. Now we have developed a new machine, which is a pilot machine in which we are able to do rolls. So you can see this is a full roll of aluminum, of a vertically aligned carbon nanotube on an aluminum foil, 30 centimeter in width here, and here you have the same, but 1 meter in width, continuous, simultaneous double side covered with VACNT. It's a roll-to-roll process, and so with that, we are able to do some cells, 10 by 10 centimeter cells of ultracapacitor. So in terms of manufacturing, I think we have reached a certain level, and we want to get benefit of that to be able to use this material for lithium batteries. So just some other illustration here, different substrate. We can grow on different substrate. We can grow on aluminum. It was our first target for ultracapacitor. But we can also grow VACNT, on stainless steel. This is what we are doing for composite application. The interesting thing is that we can control the adhesion, in fact, in the process. So this one, we can easily lift off the carpet and transfer the carpet into a carbon fiber prepreg, for instance. And we've been recently able also to upscale the VACNT on copper foil for lithium battery anode, especially. At this stage is single side, but we will be able to do double side, no problem. It's not a question of the process, it's more a question of the machine, and we have the machine to do that. Another very interesting thing is that we will be able also to selectively grow the carbon nanotube, and so have some in a substrate. We can have some areas here where we have no nanotubes, and some area here where we have nanotubes. So it's it's an implementation of a new post-synthesis process for selective growth. It gives a very interesting bimodal porosity that can have benefit for the use in lithium battery electrode, I would say, anode or cathode, and it has superior performance compared to the state of the art. So why VACNT can be interesting for lithium battery? It's mainly because it completely changed the paradigm of the cell design. Instead of using powders and binders and additive or things like that, we are completely changing the material. We're using a material that is a kind of scaffold to host some active material. You don't need a binder. It's a dry electrode process. You don't need any solvent. It's very fast. It has a huge specific surface. You can coat the carbon nanotube. It has all the nanotube are perfectly aligned. It will increase the conductivity of the ions inside the electrode, and and we will have also very good electrical conductivity thanks to the nanotube themselves. They are very small, 5 nanometers, and very good thermal conductivity as well. So all those properties all together combined makes the vertically aligned carbon nanotube carpet as a very good potential candidate for an electrode or for any a substrate. So I invite you to have a look at the video we have on YouTube. I will not present the video right now, but it explains that by doing that, you can have a much faster transfer of the energy from the electrolyte up to the substrate at different level. You will reduce the electrical resistance at different level, and you can benefit also from a much better homogeneity of your electrode material that will help having a lot of different advantages in terms of fast charging, which will be the best advantage, but also higher efficiency use of the material and some benefit in terms of safety and also in terms of lifetime. So just to illustrate what I want to say is that there has been also some good article in the literature that shows the advantage of vertically aligned carbon nanotube. we can see the advantage of vertically aligned carbon nanotube with a reference that is not vertically aligned carbon nanotube, which is something different. And we can also compare the use of vertically aligned carbon nanotube with nanotubes that are not vertically aligned, because today nanotubes are already commonly used in lithium battery, especially to improve electric conductivity. They are used as an additive, but it still requires some other binders and some additive as well. In our case, we don't need that. We don't need that, and we are able to even increase different things. The adhesion, the electrical resistance, as you can, as you can see here, and here the performance in terms of stability or in terms of performances. This is compared to something that has no nanotube or no vertical nanotube here, and here this is a comparison between vertically aligned carbon nanotube and dispersed nanotube. So nanotube in powders that are not vertically aligned. So what we wanted to do is really to, all those results in small labs, at small scales. And what we want to do is really to see how we can extend those results, how we can apply those results, how we can find some other results, but at industrial scales. So first, what we did, we tried with something that is the simplest way to do. We grow a thin layer of VACNT on a substrate, which can be a standard copper substrate, for instance, and we coat the classical graphite active material first, and we made a measurement about the electrical serial resistance. So you can see here, this is the sublayer, quite homogeneous on a copper collector, and when we have made the electrode, you cannot see the sublayer because it's too small. It's less than 1% of the global graphite content. What is very interesting is that if you do that and you measure the electrical serial resistance of your electrode with graphite, you can see that this is what we will have with a copper foil without anything. So after cycling, before cycling, after cycling, this is what you will have if you use a commercial coated copper foil with basically it's carbon black. And this is what you will have if you use VACNT. So we have the best, the lowest electrical serial resistance, and this electrical serial resistance is also decreasing with the cycling. So just a thin layer of VACNT, which is less than 1% of the overall electrode thickness, has a huge impact, both on the ESR and also on the, it also indicated that we can have a faster ionic mobility of the electrolyte, thanks to the slope here. So what we did exactly the same, but on the other side. Instead of taking graphite, we did the same with NMC, active material. So it's on an aluminum. We grow a thin layer of VACNT and we put aluminum, and we had exactly the same kind of result comparing to a reference cells. That is here, we have a much lower ESR that you can see here. So VACNT significantly reduced the ESR interface between any active material, in fact, and any substrate. So all those results have been obtained at the cone cell level, but we are starting a campaign to be able to show that we will have the same result at pouch cell level. The good news is that we did exactly the same for ultracapacitor, and we had very consistent results when we switched from the cone cell to the pouch cell. So then what do we have in terms of cell performances? Is here I can share the difference in terms of capacity improvement and capacity retention. So in terms of capacity improvements, we were not expecting a lot of improvement because we are adding only 1% of carbon, which is not really, in terms of capacity, will not bring anything. But in fact, it appears that even with 1% of VACNT at the interface, we have a slight increase of improvement. And it's not shown here because those results are from the same cells. And but even if you take a bad NMC active material, the improvement of the cell performance would be even better. So you can, in one way, it will make your material better. VACNT will make your material better. And in terms of fast charging, here that's the most important benefit that we can have. So you have here reference cells without VACNT, and you have here the same cell, same loading, and so on with VACNT, thin layer of VACNT. So you can see that we can have a much better fast charge. We can go from 2C to from 1C to 2C, or with almost the same capacity retention. And if you compare at the same C rate, we have a much better capacity retention versus reference cells. So of course, this has been obtained at the coin cell level. It has to be proven at the pouch cell level, and that's what that's our program for 2023. So, as a conclusion, there are many advantages of the use of vertically lined carbon nanotube. What we think is that it's really a fantastic material that is really agnostic and can be used in many different applications. And for lithium battery, it could be also very helpful. You can have different ways to use it as a thin layer, but we will present in another conference some other results with much thicker layers. So in terms of power, I think that the use of VACNT will help you to develop the fastest electrode, whatever your material. It will increase the ionic, electrical, and thermal conductivity. It will have also some effect in the thermal management of the batteries. It will bring you high power performance, faster charge and discharge. In terms of energy density, the carbon by itself will not bring anything, but it will allow you to increase the efficiency of your material, whatever the chemistry. We have some, we are conducting some tests also on sodium or sulfur or other chemistries. And it's a good match also with lithium metal and solid-state battery because it can stabilize the lithium metal foil. It works with any electrolyte. It can be combined with liquid electrolyte or with solid electrolyte as well. In terms of raw material, the process that we are using is very, very green. We are using only green carbon sources that come from the transformation of the CO2 into the atmosphere from the plants. And we are using also green hydrogen and recycled, or we will use green hydrogen and recycle aluminum or copper. We are taking care we are paying a lot of attention on the safe use of nanomaterial. Our nanotube by themselves have been classified by the new regulation as the safest nanotube ever. So we are very, let's say, sure that this kind of material can be used in the industry. In terms of environmental footprint, we can lower the energy intensive manufacturing process, and the machine, I did not show you the machine because we don't want to disclose the design of the machine, but the machine is not very long. If you compare our machine, which has a footprint of 6 meters by 6 meters, it can do the electrode the same way as a classical coating machine that is 6 meters up to 50 meters or 100 meters long. So in terms of footprint, it will be very interesting. Our next gigafactory will be smaller than actual gigafactories. And in terms of cost, it has to be validated, but the process that we've let's say, developed is a high throughput process and very efficient process. And in terms of cost, today we have been able to we are on par with the cost for ultracapacitor, and with with increasing the speed thanks to the change in the substrate, because we can, with copper substrate, we can increase the temperature of the process, so we can increase the growth rate, so we can increase the throughput. We could be able to decrease the cost of this material, and there will be a kind of additional cost, but it will not be important if you compare to lithium anode cost. We have also some other advantages. So we are hiring, we are in growing environment. So if you want to join the NAWA team, it will be with pleasure. And I just want to thank you for your attention. Wow, perfectly on time.
Thank you, Pascal, for introducing us to the Rapunzel carbon, I would say. Huh? Yeah, James and Surya, join us. Yeah, we have another and final Q&A session. Please make yourself comfortable in the chairs. By the way, I'm the only one standing and I'm called chairman. Okay, yeah, I should do this. Do we have a mic there? Yes. Okay, that's a good idea.
There's no mic.
No, we don't have a mic. No. And I stay here.
I can give you mine if you want.
That's good. I stay here. So there's one question over there. Craig, you're helping? Thank you. Yeah. In the very back, please give us your name and affiliation.
Benjamin Passenberg from Porsche. I have a question for Enovix. So very interesting concept, but you need a lot of stapled active layers there. So it's about factor 10 or more that you need. How do you do this in the processing? Do you have a very quick process to do this? And what's about the cost there?
That's a good question. So we do have to stack more electrodes and stabilize that stack. That's absolutely correct. It's not an order of magnitude. It's generally an order of 2 to 3 times, right? So it's significant, but not as order of magnitude. So we've done a lot of work on our consumer lines, developing a very unique electrode patterning, stacking, and electrode interconnect process. The laser process. It's very robust and it's scaled from small cells to cell phone cells very well. And we're really confident that we can scale that in high throughput in the EV space as well.
Okay, please.
Hello, I'm Thijs from Leidenjar. I have also a question for James from Enovix. So I was curious in your cell design how it would compare to a cylindrical cell, since I would think you could also contain the, let's say, pressure if you wind electro. I'm just curious what you think is why your technology is competitive or not, or what. Yeah.
Yeah, so cylindrical cells, obviously, you can withstand higher internal pressures than a prismatic cell or a rectilinear cell. You can also benefit from some thermal properties if you look at some of the tabless designs that are there as well. The problem with the cylindricals is you get things like core collapse, right? As you try to bring up the pressure and try to scale the cell, you run into fundamental problems that increasing the core energy density leads to other failure modes. So we think by doing this rectilinear approach, you can have more uniform pressure, more uniform stacking. Now you're in the pack level, you're not putting spheres together, you're putting rectangles together, so there's an areal fraction increase. We think you put all this together, you have a very competitive space with cylindrical.
Maybe you would like to expand a little bit on the force per area discussion. I think that's maybe helpful also for understanding the benefits of this design, okay?
Yeah, sure, so obviously with a cylindrical, as you increase the radius, the stresses go up significantly. You have to go with really thick walls, everything like that. By stacking in this kind of orthogonal direction, we can control which face we want to essentially stack against. And that allows us to really control what kind of stack pressure, what kind of forces we need to manage. And so we can fundamentally stack more efficiently, right? So if the cell needs to be longer, we can just make the electrodes longer. If the stack needs to be taller, we can make it taller, just stack more electrodes. And the constraint doesn't need to change. If we make the constraint, if we make the cell thicker, we go from 10 millimeters to 30 millimeters. Now we do have to make the constraint a little bit thicker, right? Because that strength goes up, there's a bending moment aspect in there. But it's very efficient. It's under the power of 1.5. So even for a large format cell, you're still not talking about very thick steels. You're still talking very thin, couple 100 micron thick steels. So it scales very nicely.
Okay, next question, please.
Yeah, this is Lou from Aurora Flight Science, a Boeing company. Since we are working on aviation applications, the gravimetric energy density are very critical to us. So I just wondering, for the cells you have demonstrated, which kind of gravimetric energy density you have achieved at which kind of C rate?
For whom is the question, please?
Boeing. My name is Lou Yang.
Yeah, but can you please say who of the 3 speakers you would like to address this question
James,
to?
yeah.
James, okay.
Yes.
The question is, what is the gravimetric energy density?
Yes.
Yeah, so obviously we put this metal constraint inside the cell. So there's always going to be a penalty gravimetrically to do that. And we believe that by doing it at the cell level, you can get efficiencies and you can save at the packer system level, right? Especially if you add in the cooling benefits. So when we do modeling and project to larger format cells, we're getting to that 350 watt-hour per kg range. We believe that's achievable. Today on our smaller cells, I believe we have on our website, I don't want to misquote a number, but it's in the upper 200s, I believe, on our consumer cells today. So there's a small penalty to be paid, but we think you can win on the overall system.
So what you are saying currently at around 200 watt-hour per kilogram?
No, it's above that, I believe. We'll have to look at it in the, yeah.
Okay. And my next question to Pascal is the vertical land common nanotube. So what's the additional cost for this process to the current character? And when you go through the calendaring process, will there any damage to the vertical land common nanotubes? Thank you.
Thank you very much for your question. So in terms of cost, I don't have the real number, and we need to progress, and especially we need also to progress in partnership with cell makers or OEMs, like in cars or in the aerospace industry, because we are quite new in this field. But what I can tell you that the process by itself allows us really to grow nanotube easily. And once you find the recipe, the problem is not to grow nanotube, is to be able to manage the growth of the nanotube, because it's so easy to grow them that, and I think that in terms of cost, we only need natural oils, the raw material. So it's very, very, very low cost. And I do not see any, compared to, if you look at the performance that you will have, I do not see that the additional cost will be an obstacle of the use of this technology. I will come later with a few numbers. We need to do the calculation with right people. Today, I'm sorry, I don't have this, but what I can tell you is that for ultra capacitor, we've been able to decrease the cost of ultra capacitor, and I think that with the battery, that will be the same. And what about your second question?
Yeah, my second question is that in the typical electrode manufacturing process, we have to go through a high pressure process to condense the active material. So I just wondering, for the vertical land common nanotube, will that process damage?
No problem. You can compress them. They keep compressed, or they come back depending on the pressure. So we know that that's not a problem. I did not show. I can show you a picture of compressed vertically lined carbon nanotube. They are not. For them, it's a little bit like nothing is happening. 5 nanometers, 100 micron length. So even if you compress it up to 80%, for them, it's the same. No problem with that.
Thank you.
Hi, Nick Gernon from Polaris Battery Labs. For Pascal, could you clarify? I think I saw that the vertically aligned carbon nanotubes have a cycling capacity of around 800 milliamp hours per gram, with a first cycle efficiency of about 50%. On their own?
Did you get that number from my slide?
I believe so.
Okay, so it's not the VACNT by themselves.
Okay.
It's it was the NMC. Okay.
Oh, I'm sorry. I thought I saw a slide where you showed cast CNTs with a extremely low cycling capacity, and then the vertically aligned.
Okay. In a paper.
Yes.
Yeah. Okay. It was okay. So CNT by themselves, if you are using CNT as an intercalation material, you will have a huge first cycle with a huge loss of efficiency, and then after you will be stabilized around 200. Yeah.
Okay.
But I would not recommend to use VACNT as an intercalation material. I would recommend to use the VACNT as a host material.
Yes. Yeah. Thank you. And so where I was going with that was also, do you see increased first cycle losses once you apply an electrode coating to the VACNT substrate?
So it depends on the cell design. You are talking about the SEI, in fact, and yes, sometimes we see an increase in the first cycle. So we have to face the SEI because we have a huge specific surface. But depending on the way you coat the CNT, you can completely get rid of that.
Oh, so it passivates the CNTs essentially?
Sorry?
It passivates the CNTs?
Exactly.
Okay.
Yeah.
Thank you. And then just a quick question for James. Does the orientation of the Enovix cell, does that facilitate electrolyte wetting in any way?
It can, yeah. So we obviously are vertically aligned in the pouch, so it'll give you direct access to all the edges of the electrodes on a short diffusion length. So depending on the aspect ratio of your cell, there can be advantages in wetting as well.
Okay, then I would like to ask a question to Surya. So I have actually two questions. One is a very simple one because somehow, maybe I missed it during your talk. It's basically you are adding something to the slurry and you're adding something to the electrolyte, and then you get this enormous improvement in performance. You have done nothing else.
Yes, nothing else. We have taken crude micron silicon, took the graphite out and used a binder that's, again, not been used in the battery industry, but commercially available, low cost. It's the anode process and the electrolyte redesign.
Okay, I think because that was one thing which I did not get really. And then the question was when you were showing your mechanism, how the binder works. I got the impression there's a cross-linking of binder molecules, and this creates a network which is, let's say, immobilizing or stabilizing the three-dimensional electrode concept. Is there no reaction between the silicon and the binder material, or the current collector and the binder material, because you have this enormous adhesion to the current collector? So this was not really. I cannot explain it by just when only the binder reacts. Yeah.
Right. The binder actually has multiple attributes when you activate during the drying process. It provides the mechanical strength because it's cross-linked. And also during that process, it also provides conductivity, which of course I did not show. We have done Raman spectroscopy to find out what is that G and G bands are. And third one is because of the particular molecular structure, it also allows the lithium ions to penetrate, because you're not just protecting it, but you're also allowing the lithium ions to go through, essentially. Thanks for the question.
Okay. Do you have one more question here? Yes, please.
Yeah, the first off, great presentations. The first question is to Suri. In terms of rating the silicon, do you feel that there's an optimal rating that most silicons will need to be run at for lifetime? Because obviously you're always fighting against that highest alloy, which is causing the largest amount of expansion and more SCI and fighting the binder system. And then I have a follow-up question for Enovix.
Let me then answer. Thanks for the question. And what I think is, if you want to truly take out graphite from the anode, you need to think that the cost of the material should be equal to what graphite is. Otherwise, at the end, we see that, right? LFP is coming back. It's because cost is everything at scale. So from that's one of the reasons why we started working with this metallurgical grade pure silicons. But the challenge with them is the particle breakage. You can protect it from the electrolyte attack and other things, but as you start using it, it will break, right, without pre-lithiation. You can actually pre-lithiate and break them before, but that's going to cost again. So to answer your question in a way is that there will be diversity, right, because silicon oxide is already commercially available. People are using it. And then Enovix just said that they're also using it in higher loading. So, and there are other companies who are using them. So silicon oxide will be dominant, then the silicon carbon composites, and eventually we have to get to the micron. That's the reason why we're focusing on this so early, so that we can make a path towards that.
No, thank you. And then a question for Enovix. Since you're using SiOX and since the first cycle losses are so large, it's going to be necessity to pre-lithiate. And if I remember from, I don't know if it was this presentation or the last presentation, but yeah, that it's a very elegant 3D architecture, but it requires that you can put lithium into the cell, which will then diffuse through those orthogonal electrodes. In my remembering correctly, that you can only go 30 millimeters, and after you don't get uniform lithiation anymore. So what is the plan to go to larger widths? Because if you're going to go to EV, 30 millimeters is way too thin. So what in your mind is going to be the critical challenge to going to longer lithiation or going to cells that are thicker than 30 millimeters in the future? Because that's obviously going to be a critical bottleneck, right? That diffusion path of the pre-lithiation.
Yeah, you're right. I don't know if we've ever discussed an upper limit on that. At least I have never have. So. But you're right, there is a transport limit. We directly diffuse from the sides of electrodes from both phases, diffuse the lithium in. And as you do scale, there will be some additional development that needs to be happen there to allow for the time for that to happen. We haven't really seen uniformity problems yet, and the upper limit on that. It's really about time and time to manufacture and cost effectiveness. So I don't see a huge technical limitation. It's just a time manufacturing question. The other thing to think about is, we're doing 100% silicon oxide anode today for the consumer space. The points that are just made is that industry values energy density over all else, right? Or volumetric energy density. And so that really benefits going to 100% silicon oxide, but really pushes you to do more pre-lithiation. Depending on the chemistry set you pick, you may be able to dial that back and open up other ways of pre-lithiating as well. And we're looking at all of those. It really is a system chemistry choice.
Yeah. Okay, we are already out of time, but I want to have one more question. And one is actually to Pascal. When you have this toothbrush morphology of your current collectors, okay, then how can I imagine that the active material slurry goes into this? Is it like, you put toothpaste or and then it sinks in, or
Okay.
How do you bring it into this?
So very good question, in fact. And we have 3 strategies to bring the active material in between nanotube. First, we do not bring them in between nanotubes. So you have to have in mind that the spacing between the 2 nanotubes is between, let's say, 20 to 100 nanometers. So you cannot infiltrate a powder of more than 100 nanometers. So the first strategy is just to put the active material on top. That's what I showed. The second strategy is to selectively grow the VACNT, so to have some plots of VACNT, and you put the active material in between the plots. That's some results that we are working on, some quite good results, in fact. And the third solution is to completely change the material. Do not use powder anymore, but do some coating material like plating lithium metal inside the carpet. That's the 3 strategy we have.
Mm-hmm. I think for plating of lithium metal, that could be interesting. I agree.
It is.
Final question, and I excuse for this question. So I'm not a native speaker, okay? But if you talk about agnostic, okay, everything is agnostic, okay? What does it mean? So does it mean that you are not looking for a better silicon and binder material, or especially Surya and James, or would it be that if somebody provides you with a great carbon additive, with a great binder, and with a great electrolyte additive, you can improve? Or is it that you can have any material, don't care, we have always excellent performance?
We're always looking for better materials, right? Our goal is to get more out of the materials that we have today and to keep on building on that. We're not a materials company, so we're really dependent on a lot of the work that's being done to really open up lower cost materials and higher performing materials. And so we're really looking for partners to work with to develop it. We literally, the agnostic part of our structure is that nothing about our architecture requires a specific material set. So we can use our architecture to get more out of whatever material comes next, and maybe even accelerate some development opportunities or create some different boundary conditions that may make some of these new materials more viable in a system level.
In simple words, it's a platform technology, right? That's what I mean by agnostic. So we can take any silicon material, any cathode, and then put together a cell design that works.
And you?
It's the same question. It's a more technology platform, and we have already tested different kind of materials. So with this 3 strategy, we can have many different applications. We have already tested the NMC, LFP, graphite, silicon as well, and we are about to get some first result with lithium metal as well. So
maybe in one of the future AABCs, we see a presentation of the 3 of you too. Then we bring everything together, okay? The carbon, the binder, the electrolyte additive, and the cell design. And then we have the best battery ever, hopefully. This is ending our session and also our symposium. First, I would like to thank all the speakers again. Good discussion. Thank you to all of you who asked questions. The chemistry symposium for this year is over, but after ABC is always before ABC. So we are having an ABC Europe in Mainz again in June of next year. And then also in December, I think even later in December, in San Diego again. Not the same hotel probably, but hopefully a warmer room. That would be nice. This is my wish for Christmas, okay? So, you have a great day and see you later at the plenary, which is in this room. Bye. Thank you.
Good morning and welcome to the keynote plenary program. I'm Craig Wohlers, Executive Director of Conferences at Cambridge Intertech. I would like to thank all of you this year for making this the largest AABC ever in the history of AABC. So I appreciate, thank you so much for that. As a celebration, which I'm joking, but we'll have fireworks tonight at 6:45. It's not exactly our fireworks, but it helps to celebrate that achievement. So thank you very much. With that, also want to just note to please encourage you guys to use the AABC 22 hashtag in your LinkedIn post. We really would like your feedback and your impressions of the meetings as you post. That also enters you into a drawing to get a free registration for next year. So please do that. We love that feedback as you go along through the conference. We're now very excited to kick off our plenary program by introducing our first speaker, Tim Grew. Tim is the leader of General Motors' global battery cell and electrification strategy. His responsibilities include battery cell production and next generation electrification strategies. Tim joined GM as the chief engineer for Allison Hybrid City Bus. His teams have launched multiple generations of GM electric propulsion systems, including the GMC Hummer EV and upcoming electric crossover from Cadillac. Tim earned his Bachelor of Science degree in Electrical Engineering from Rensselaer Polytech Institute, as well as a Master of Science degree in Electrical Engineering from Syracuse. Before joining GM, he worked at General Electric, developing distributed power systems for aircraft, locomotive, and heavy-duty transportations. Please welcome Tim to the stage.
Well, good morning, San Diego, and thank you for being here. That's a Ron Burgundy quote there. I'll try to cut that and have it be the last one. So a little bit back, Mary made the statement that our industry is changing more now than it has in the last 50 years. And I'd really like to thank the AABC for being a big part of that transformation. I mean, who could imagine that in 2022, we'd be able to watch the future national champions, Michigan Wolverines, beat the Ohio State football team, and at the same time, enjoy Equinox EV, Blazer EV, Denali EV, Hummer EV commercials all at the same time. And it's part of this group that made all that happen. So I'll talk a little bit about how GM contributed to that, and then the material supply chain dilemma right now, and then how we go forward in the future. So our overarching approach to this is zero crashes, zero emissions, and zero congestions. It's all the tech is tied together. The EV battery enables us to do more driver assistant functions. It allows us to have zero emissions where we can actually run on the sun. And then it can lead to the future of the autonomous vehicle where there's zero congestions. Or the EV battery can help us other ways in society with supporting the grid moving forward, and we'll talk all about that. So how do we go about it? Well, we said we wanted to have a common platform. And we wanted to have the platform focus on the high volume runners, right? The SUVs, the crossovers, the pickup trucks, and then get into the ability to have the same platform do the expressive vehicles along with the future autonomous vehicles. And that's where we started down this path. And kind of the working mechanism behind all of that strategy was this relentless pursuit of cost reduction and performance at the same time. And we call it the circle of innovation on the left-hand side. And then on the right-hand side, we kind of say, well, how does that actually affect battery cost reduction and increasing performance? So everybody's heard of Moore's Law, continuous improvement, every operation, every day, every step of the value chain, work on taking what you got and making it better. And that'll start to asymptotically approach a minimal cost. But then in parallel with that, you do some breakthrough technology. And Ultium is an example of that breakthrough technology. We're actually going to go drive scale with a single cell driving the entire platform. You're going to actually have new ways of actually processing some of this material and actually create some new partnerships to accelerate that into the future. And at the same time, you want to do your true entrepreneurial work. The lithium metal anodes. The other tech that you have on every step of the way to say, well, now that I do have maybe twice the energy density and I want to stick with 300 miles range, how do I shrink that thing and incorporate the power electronics into that pack? And work all that in a continuous way where we really don't know the bottom of the cost curve. But later on in the presentation, I'll give you some insights to all of that. So what GM did with Ultium is we made a cell specifically designed for the vehicles, about 580 long, about 115 high, and that goes cross car. On a typical SUV or crossover, about 288 of them. On a truck, about 576. And we'll show you how this single cell is upgradable for the future. Currently, we use a very advanced artificial graphite, but an NMCA cathode to get the life that we want and the performance that we want. And it can upgrade to things in the future while we keep all that capital. We keep all those battery plants and everything running out at flat rate. So we have the volume and the capability. So this is an example of a great Ultium joint venture. It's called Ultium Cells between General Motors and LG, where we signed it and then we really started to work together. So we both made our avatars. We simulate everything, every operation, every part of the building, every step through the entire cell manufacturing process. And we work together to say, well, how can we do it better? You know, we started back in 2020, and now we're in production here in 2022, which is pretty fast. And that was through that collaboration, through that virtual simulation. In February 22, at the height of the pandemic, we laid our last bit of steel in our Warren factory. We continued to build it out to get all the other subsystems and to get the community engaged, to say, how do we get a workforce generated to make all of this happen? We partnered with Youngstown State University to make some curriculums together with it all. And today, here's the plant. It's huge, 2.8 million square feet. One of the biggest factories around to make all this happen, and it's up and running. And you know how you always like your kids, you always think they're good looking no matter what? Look at how good this cell looks, right? All planar, right? There's 200 amp hours, boom, going into packaging. All the welding that's done on the high current tabs is done adjacent to the electrode so you can isolate it and not have any troubles with the manufacturing. All of that knowledge and all that step went into that cell working together. And so now we can retire all of our avatars. We can actually go into the plant, do all the virtual simulation training on the screen so every operator can figure out how to really control the process to center it. And we've turned that vision into reality, and it's up and running in Ohio today with huge support from the community. So now we got a great cell. We build things we call cell module assemblies. In North America, we have 24 pouch cells going in. In China, we partner with CATL and have prismatic cells go into that same basic footprint. From this, we can build the car, right? It is a structural battery pack. We can build the car around it, and that's an example of the Lyric. And if you look at it and say, well, now how can I take that modular up to pickups and SUVs, which have much higher energy requirements? Well, it's quite simply where you use some of the vehicle structure in the battery pack. I always like to call this the George Washington Bridge, where it's a double-decker battery pack. And you basically have that then be fully integrated with a structural member of the car so it can meet everything that you would ever want it to meet in the SUV or heavy-duty truck capability. But the key point here is all with the same cell. And then you can flex from there. You know, get going, get all the capital installed, get all the capability installed, get all the workforce trained, so you can make that happen. You know, the trucks on the left, the crossovers and SUVs on the right. We also can do the expressive vehicles, where basically any place there's volume, you want to stick an electrode. And we can do some of the more exotic packs right there. That's an example of the Celestique pack, which is one of our very expressive vehicles. We actually lay the batteries down on their side to make that work and do a horizontal stacking with it. But then keep everything else the same. Keep all the wireless battery management system, keep all the control systems the same. And we can actually fit about 6 kilowatt hours under the second row seat foot to make that happen. And so that's a great example of how you start with your core DNA and then you adapt it into something very unexpected and don't leave anybody behind. We can actually have one common cell work across all these different platforms. And to kind of visualize that, you know, we'll start looking at the Hummer, huge 3-motor, 1,000 horsepower system. and say, well, okay, let's use that in a Silverado, but instead of a 24 module, maybe make it a 22 or a 20 module going forward. Take that same Silverado rear drive unit, use it in a Lyriq, and go down to a 12 module pack moving forward. And then you can grow or shrink the length of that pack or exchange those drive units to give you that performance. And can you imagine a Blazer EV with a front and a rear performance unit? That thing's going to be amazing. Talk about exploring the boundaries of tire limit moving forward with this. And it's all with that common architecture. So that was a big push that we had to say, how do you get going with this? And then let those cycles of innovation just improve it continuously every model year, everything going forward. That's how we're able to do a front drive only Equinox below $30,000. That's how we're able to do everything in between and even go into the big vehicles with the package delivery with our BrightDrop platform. So, we want to focus on SUVs. We got the Lyriq, great vehicle. Say, well, the next big one is the pickup trucks for GM. We've got the Silverado, we've got the Sierra, we've got the Hummer. A lot of those brands we're bringing back, really exciting customers being able to do whatever they need to do. On the very expressive, this is basically an additive manufacturing car with the Celestiq where you can customize it. I think Lenny Kravitz is putting a guitar in the dashboard with that one that he's making. And you can do the big stuff. And some OEMs are doing 80,000 pounds, but how about 200,000 pounds? Well, this is an agreement that we have with Wabtec, great North American locomotive company. We're putting a little under 25,000 cells into a locomotive, about 8.5 megawatt hours. Now, as you can imagine, everything about a EV is you want to treat every cell the same. So it's got a very well-integrated liquid cooling system. And that the wireless battery management system is really being put to its limits here. We can wirelessly communicate with all that, communicate everything on vehicle in real time that you need to do, and go work with the freight optimization systems of the rail companies moving forward. So that's coming out in about 2024. 200,000 pounds is the limit. You can put a couple of these together and you can even make bigger trains with them. And there's a lot of pull in the market for that. In addition to other industries with this Ultium platform, you have a lot of flexibility. I kind of mentioned that cell module assembly. It's basically got a QR code on it. You scan it. Up in the cloud, you've got everything you need to know about that module. How it was made, where it's been, how to recycle it. Makes it very easy for other industries to use it and customize it. It's the new Crate engine moving forward. The GM Performance Group is doing conversion kits. Pure Marine is making boats out of it. And there's a whole raft, everything from articulated lifts at the airport to Zambonis are going EV with Ultium. And having that entire support system to make it be a success for them is what that modular system provides us, to have those expanding markets. So now we'll transition into some of the tougher topics. And, the supply chain. As we're doing this conversion in our industry, where are we going to find the metals? Where are we going to find the critical materials? We've got an overarching strategy to say we want to control our destiny. We want to secure it in a very sustainable way. We want to scale it where we bring in new technology and fundamentally change the cost that it takes to process these materials and always lead in cost competitive solutions. So what have we done? We've developed really strong relationships beyond the binding agreements with trust and cost transparency to say, here's what we see as benchmark today. Now, how can we co-invest to accelerate a lower cost or a higher performance capability? And working with all this, we're able to come down those unit steps on those innovation cost curves. Okay, and we have some examples of it. Right now, we're fully supplied through 2025 and expanding into 2030. About 1 million cars in 2025. and trying to expand to more of that in 2030. So, you know, these are binding agreements, but you can also look at them as improvement agreements. Where in the agreements, we not only say, well, how do we do it today and how do we actually optimize that, but how do we go to the breakthrough or the entrepreneurial level with you to make it all happen? So a great example is Livent. Again, very focused on supporting materials, 1 million cars in 2025, and actually having a lot of their operations move to North America in 2025 is kind of the work that we're doing with Livent there. On the real entrepreneurial side, right here in California, just a little bit east of here, the Salton Sea in California, it actually has a lot of lithium in it. You know, controlled thermal resources, drill a well, it's surprisingly like oil, right? The geyser comes out with a brine, you clean up some of the silica in there, and then you can do some direct lithium extraction in a very novel process. And we've partnered with controlled thermal resources to go accelerate and make that happen. You know, we're not geologists, we're not experts there, but they say there's a lot of potential there just in California here to provide most of the lithium that the US auto industry needs. From an ethical point of view, Glencore, Mirror line in Australia, get the cobalt. Lock that in, make sure you're not going to have trouble with it. And then keep on expanding with nickel and cobalt, again in Australia with Queensland. And we recently announced Vale here in North America to provide us some high-grade nickel moving forward. And so working all these base materials, but also working the actual cost to process these materials is what we're all about. And getting rid of some of the, what I would call industrial waste opportunity. You know, is there some intermediate spec along the way to say, well, this is what we have to do to meet a generic industry requirement that doesn't apply to automotive? And how can we eliminate that with this dedicated source to make it happen? At the next level up is cathode active material. LG Chem is different than the company that we work with Ultium Cells. That's called LG Energy Systems. They are different companies, but they've got the same name. With LG Chem, we've secured enough cathode active material for 5 million units through 2030 and looking to expand and improve that. And then we've signed deals to actually build cathode active material plant where there's a lot of hydroelectricity with POSCO in North America. And having that plant come online as quickly as we can to make it happen. So, you know, lithium hydroxide is a good number. If you combine, you know, a consensus between McKinsey and a lot of the other predictors as to where the market forecast is going to be, you combine that with some of our direct source cost ramping in, we think by the end of the decade, with the juniors and the established majors, we're going to have a very stable supply chain, but it takes a lot of work. We've got a dedicated global supply chain and engineering team working on this to turn this into our reality in the future. Another big thing we're focusing on, and this just makes sense from all business case perspectives, is about 75% of this we want to come from North America in 2030. And we think the resources are here to make that happen as we continue to scale this. Always keeping our eye on 2035, 2040, where the returned vehicles can actually be the best source of the critical materials. Okay, working with the hydro processes, working with the recyclers to say the recycled material works just as good as anything that we have mined. We recycle every battery that we get back. And we've proven that these recycling processes are very cost effective and they work in our future batteries moving forward. So keeping that actual lowering the dependence on the raw extraction in the long run is something that we're working on today. The darn batteries just last too long. So that's going to be a ways out there until we get the scale there. But we're always making sure that we don't miss it. So we do a lot. We got huge labs in North America on the breakthrough area to get it into production and make it a reality with all these different cars that we want to make and all these different trains. On the entrepreneurial side, we got over 2,000 next-gen patents coming out of our R&D group. And we've actually redone the development process where we can take 95 weeks out of making a car. through a lot of this, do everything virtually, correlate your reality to the virtual model, and then just get to market a lot faster. So, you know, a big part of this is this Wallace Innovation Center. It's really a manufacturing center to say, well, okay, here's the next great technology. How does it really run the way we run our factories? You know, it's an innovation center. We welcome partners to come into this with us and then go accelerate their technology into our product. It's actually up and running now, and we're making cells in there. And we're developing next generation processes in cell manufacturing with many, many innovation partners working on this. So, you know, my kids look beautiful. The lines are up and running. Everybody's working. We got the workforce enabled to do it. We talk about, compared to the Bolt EV, which was kind of 2016 technology on battery cells, we're down 40%. It's our production well under $100 a kilowatt hour right now. And with all of this innovation, we see direct paths to get under $70 a kilowatt hour at the cell level and make all that happen. And then multiply that through the improvements at the vehicle and at the rest of the system level. But it takes a lot of tech that isn't necessarily just making a cell. It's how do you build the prognostics in the data cloud so that you can detect things way before they start getting in trouble. You know, how do you build a team that can introduce that new technology 95 weeks quicker than you ever did before any internal combustion engine? So, you know, the future is now. Ultium got a crazy Hummer, 0 to 60 in about 3 seconds. Watts to freedom. Fast charged, 10 minutes, 100 miles. Lyric 310, very usable vehicle. Tow anything you want with our Silverados. Cruise is actually driving driverless with the technology now. And you get an Equinox for under 30K in the future. So I'd just like to say, you know, hail to the victors valiant. Hail, hail to AABC, the leaders and the best. That was a Michigan reference.
Thank you very much for that, Tim. All right, our next speaker is Ted Miller. Ted is Manager of Battery Cell Research and Advanced Engineering at Ford's Battery Center of Excellence, known as Ion Park. Mr. Miller leads the research, development, and implementation of advanced cell, material, and battery recycling for Ford EV applications. His team is building an advanced fabrication pilot laboratory within Ion Park to develop and demonstrate beyond lithium-ion EV cell technology. He manages key collaborations with developers of solid-state cell technology and commercialization of battery recycling. Mr. Miller was chairman of the United States Advanced Battery Consortium, the University of Michigan Energy Institute External Advisory Board, and a member of the Idaho National Laboratory Strategic Advisory Committee. He served on the Boeing Non-Advocate Review Committee, the U.S. Navy Independent Expert Review Team, and as an OEM representation for the U.S. Flybridge Alliance. Please welcome Ted to the stage.
All right, thanks, Craig. And thanks to Craig for inviting me to come back. It's really a pleasure to be back here in Coronado and be in person at the event. Nice to see everyone and get to meet people face to face again. So this is a real treat. But Tim did a great job. I don't think I have that level of graphics to share with you, but hopefully some useful information. And so what I want to talk about is maybe it's a bit of a deep dive, if you will. And so it was nice to hear from Tim and you know, sort of the large scope. But I want to talk about battery materials, and I think we recognize clearly that there's risk, and I'll cover that a bit. But I think there's also clearly opportunity, and it sort of depends on the time frame that we look at this. This is interesting. This changes quite a lot. So I took a snapshot as I was doing my research within the last couple months. And I mean, if you weren't convinced, I don't think I have to convince this audience, but the level of commitment that's being demonstrated. So this is just industrial. This is just automotive OEM commitment. to what's happening and what's happening in battery and in EV investments, you see that it's actually pretty balanced. There's virtually as much investment across the industry in battery investments as well as the EV investments. What's interesting is how fast the total battery capacity that's being built out is growing. So I'll show you some references that are about a month prior to this, and they're not quite caught up, but this is, nearly 6 terawatt hours of total energy, and $1.2 billion of, I'm sorry, $1.2 trillion of total spending. So it's really remarkable. So as I say, if there was any doubt, especially in past years, about whether this is going to happen, I think we're well beyond that by now. And sort of double clicking on that to some extent, I want to at least cover what we're doing at Ford. You probably know that we're partnered with SK. SK is one of our partner suppliers at this point, but now we've moved into a joint venture called Blue Oval SK. So we have battery plants under construction. I just actually got some new photos of all the steel going up, but I think you're familiar with what that looks like, but it's actually really progressing extremely fast. So maybe we're fortunate that it's happening a little bit after a lot of the supply chain hiccups, but the steel is going up very quickly. So we'll have 2 plants in Kentucky and 1 in Tennessee. And again, that's going to be just on those sites, 129 gigawatt hours in the US. You can see that we're investing along with SK over $11 billion just in this project. Obviously, the jobs are important as well. And then we'll start production of those batteries for new EVs in 2025 at those sites. So that's really exciting for the team. Obviously, a huge development. And the one other thing I maybe should explain, that sort of the evolution of what's happening at Ford and in terms of our commitment to electric vehicles. So there's this Ford Model E, and so I'm part of the team that's Ford Model E. So we have Model Blue, which represents a lot of our traditional products, but Model E is really leaning very heavily into all of our electrified products, our EV products specifically. And so, trying to sort of break the mold as we need to, sort of fully clean sheet design on electric vehicles, connected technologies, and really doing that and bringing that to full scale. And that includes not only our EV platforms, but batteries, e-motors, inverters, charging, recycling capabilities, all comprehended within Model E. And it also includes a lot of the connectivity, the software, the architecture that it takes, that's the underpinning to sort of really provide that, best software, the engineering, and the user experience talent as well. And then we are really doing a lot of it, and I think Tim mentioned it's a nice way to put this entrepreneurial, this experimentation that you need to do, this really capturing the key IP. And so that's a core part of Model E and part of our DNA from the past. Obviously, Ford was heavily involved in hybridization of vehicles, plug-in hybrids themselves. And so we really built a significant portfolio, and we're doing much the same here, more dedicated to just electric vehicles specifically. This is what we're looking at. So we're in 2021, we were at about 60,000 EVs. By 2023, we'll be at 600,000. We've kind of announced it. That's obviously a tenfold growth from 21 till just next year already. So a really dramatic increase in our EV production, and that'll already move to 2 million. So that's a dramatic increase, obviously, just in 5 short years. So we'll be at 2 million units by 2026. And this is kind of gives you a layout. I think hopefully most of you have heard about our Mach-E. It's a really exciting product. People, I think, really love the product. Everyone I've spoken to, all the feedback we get. What's maybe not as sexy or as heard about is our transit EVs, but actually commercial fleets are really, really interested in these products. And so these are selling extremely well. I think we're, in all cases, it's a matter of can we ramp production fast enough? So, we've really doubled down on commitments in that respect. And I don't think there's anything that's been as exciting as the F-150 Lightning. You can't imagine how much of a market there is for a F-150 electric vehicle. So, and it's an incredible product. So I won't go on and on, but it is truly an incredible product. So, and then we have a sort of the balance of that is a brand new midsize SUV that will be launched in Europe. So that's sort of how we get to 600,000. So sort of the first increment of dramatic increase in our EV production. And then we're doing much the same scale up in Europe. So in Europe, again, here you see sort of a slice of what's happening. So this is the European contribution. You see the numbers for 21, 26, and then we'll be at 1 million in Europe alone by 2030. And then by 2035, you know, the entire fleet will be electric. We've done a significant transition, as you can imagine, coming from sort of this combination of the ICE world and the electrified vehicle hybridization world. So our centers in Europe are really transitioning now to become fully electric vehicle centers and really centers of excellence for us there as well, as we have in North America. Okay, and I just, you know, a couple of external sources. Again, this is just what's happening in terms of growth. I think what's important to us when we look at what's happened in the electric vehicle market over the past decade is, you know, I think as an industry, we're sort of looking for where's that inflection point, where are things going to change? And I think historically we've always said, look, once we get to 10%, it's going to take off rapidly, and that's really exactly where we're at when you look at, you know, 10% of the market. So, you know, 17 million electric cars on the road. So this is, I think, if people were sort of at all sitting on their hands anywhere in the industry, this dynamic and this kind of information really push them over the edge. So that's good. For a lot of us who have been working on this for a long time, you know, we're glad that everybody sort of joined the party now. So that's good news. But I think this was important for many people to see, and many people who are making investments, and many of our shareholders as well. And then, you know, sort of how does this look? So BNEF does a nice job. They look at this across sectors. So whether they're, you know, traditional cars, light duty or medium duty commercial vehicles, sort of where are things headed. And you can see that, you know, this takes it out a little bit further out into sort of 2050, where you've got almost across the spectrum, almost all electrified vehicles. I think the one key challenge, and I know there are talks on this subject as well, and they're quite important, is how do we get the medium and heavy duty commercial vehicles fully electrified? So you see that there's potentially some gaps there, and it sort of depends on the scenario that's used, whether it's, you know, sort of a traditional economic transition scenario, or really there's a net zero scenario where that's going to be driven to completion as well. But I think that, you know, we recognize the challenge there. I was glad to see that Tim showed that, you know, electrified automotive or locomotives, so that's good news. And then, you know, this is sort of how it breaks down, at least through 2040, in terms of the how's this looking in terms of electrification, especially obviously as you see battery electric being predominant, maybe some, at least the Bloomberg folks think there's going to be some fuel cell penetration, still some hybrids in the market, obviously, but, you know, dramatic reduction by 2040, virtually, you know, almost nothing left in the IC realm. And then you see how that builds out on the right-hand chart here in terms of production over that period of time. And I think what's really interesting in the way I look at this is more of this graph, and it's getting back to some of what we talked about earlier, is, if you will, the car park. You know, so the registered vehicles that are on the road globally. And I think this is quite important because, and I think Tim referred to this, you know, sort of these, you know, we certainly want these batteries to last the life of these vehicles, but that means we're a long way from having a lot of these batteries back in circulation. But so you have to take a long-term view, but you can see by 2040, now this is the car park, so this is 1.5 billion registered vehicles across the globe. And now the point is, by 2030 and moving towards 2040, we start to think about having, if you will, the urban mind. We start to think about materials that are coming back from the field. Obviously, we have manufacturing scrap that will be, you know, secured immediately, but we really have to take a long-term view, and I think that's very typical of an automotive OEM to have that kind of a long-term view. So that's what I look at this. So I look at this almost as snowplow effect. You know, when do I start plowing enough forward that I actually have an opportunity? And I'll touch on that. And again, I like this breakdown. We did some work with Craig mentioned I was involved with, as was Tim in U.S. Live Bridge Alliance. I like the way that BCG sort of broke this down by market, but this is, you know, just very near term through 2030, what the battery market looks like, and you can see it's just overwhelmingly mobile applications, automotive applications in general. I just like their resolution that they break this down to that extent. I mean, it's kind of shocking. I mean, for somebody like myself that's been at this for a while, and I remember talking within Ford about Apple's Apple's needs in terms of batteries and how, we just weren't even there. Now you find a small sliver that represents all consumer electronics. So it's just really, the game has changed so dramatically. But that means it's incumbent upon us in the automotive realm, obviously, to figure out how we get there. How do we transition? Because this is a dramatic change. And this just breaks it down again by kind of by market. And you see it's actually reasonably evenly divided between the US, Europe, and China. China still looks predominantly where most of the demand is going to exist, but just again, a different way to cut the same information. But I think what's really important is, what's happening in terms of battery materials. And obviously we talk about that a lot in this conference. And this is really, this is the aha, we need to do something about this. And this is just give you an idea across these materials of key need in batteries, just what kind of increases are expected between now or, within this decade, 2020 to 2030. So by 2030, almost across the board, it's an order of magnitude increase in these battery materials. And you see some variation across the spectrum, but I think that's really quite telling, and this is where we have to pay attention to every one of these things, and obviously there are going to be some critical needs that we have to address most acutely, and Tim mentioned a few of those sort of most critical elements to begin with. I mentioned this, but it may not have gotten one of my slides in here. So that sort of leads me to, again, this sort of conclusion that where the opportunity lies is clearly going to be battery recycling. I'm glad that's such a topic of interest here. And so battery recycling, how do we get the maximum value? How do we reclaim all of those materials? That's really, in my opinion, really going to be key. So that's one of our key focus areas. And again, you see this, it is a strategic imperative. It is comprehensive. It's from when we manufacture the batteries to, but even some of the regulatory landscape, even the extended producer responsibility, so that we make sure that those batteries are coming back into, and those materials are coming back into the supply chain as well. And you see that coming through even, some of the policy measures that are happening now. Okay, and this is just a good example if we think about recycling. I think we've done some work with Roland Berger. They did a nice analysis. They were really just starting to look at, if we, again, extend this out even in a relatively near time frame, where there's an opportunity in terms of recycling. So initially, it will obviously be a significant amount of scrap. So we're going to reclaim all of that scrap. We're going to extract all those materials that are needed. But now by 2030, as I was mentioning, at least you're starting to see an appreciable number of those batteries that are coming at end of life. So we have, again, another source of materials that we're obviously going to reclaim. Okay, I won't spend too much time on this. I just maybe briefly mention that, obviously we've been involved in the US Library. A lot of colleagues in the room have been involved as well. This was just the US Library Alliance, how it was sort of formed. And then we were asked as industry participants to get engaged along with the Federal Consortium for Advanced Batteries, and so several others. This is sort of a who's who got involved in these several forums that we had to sort of really decide what the US could do, what we could do uniquely as the US to start to address some of these key battery topics and these materials topics. And really what we came to, and what you see highlighted here in green, is we said really the key place where the government can play a role is really more upstream. Some of the midstream, but the material processing, obviously the raw materials, some of the mining resources, we said R&D was quite important as well. But it's interesting, we really came to this consensus quite quickly. And frankly speaking, when we went downstream, and you heard from Tim, you've heard from me about how much we've already committed and will continue to commit to things like cell production, things like battery production. So clearly that's going to happen. So we were saying really the ship has sort of sailed. Industry's investing already downstream. It's really more mid and upstream. So, and I think the good news is, for what it's worth, we saw a couple of things happen. Obviously, the U.S. bipartisan infrastructure law was important. You see that, where the investments were occurring there. So it's a combination of manufacturing, recycling, material processing. So I think, that's good news. We see very much kind of nice alignment with some of the things that were coming out of Liebridge and some of the conclusions we arrived at. The Inflation Reduction Act, and I think this is a hot topic here, obviously, and it's motivating a lot of critical decisions in the industry. really providing incentives, which we think is the right thing to do. So you know, there's obviously more details that have to come here. There's some sort of rules of engagement, but I think this is actually quite important. And again, very much aligned with a lot of what came out of the LiveBridge discussions. I've just sort of say as well, it wasn't lost on the Canadians what's happening here, and looking at it more as North America or maybe USMCA effectively, but certainly in Canada, there are you know, a number of mining resources, and so they saw so much of the same thing. They were sort of realizing it was an opportunity to do some funding and move those industries forward as well. And with that, I'll thank you for your time, and look forward to speaking with many of you in the Q&A after. Thank you.
Thank you very much, Ted. Our next speaker, Craig Rigby, who is Vice President of Technology at Clarios. Craig joined Clarios, formerly Johnson Controls, in 2007 and currently serves as the Vice President of Technology. Craig has played a key role in developing business and product strategies to shape the rapid changes in automotive battery technology over the last decade by synthesizing an understanding of market drivers, customer strategies, and emerging battery technology. He also leads the advanced engineering activities, including technology scouting, product development partnerships, vehicle systems analysis, and competitive product benchmarking. Rigby also has held several leadership roles in product engineering and product management with Clarios, as well as with Ford Motor Company, where he was on the leadership team that launched the Escape Hybrid in 2004. Rigby holds a Master of Science in Engineering Management from Wayne State and a Bachelor of Science in Naval Architecture and Marine Engineering from the University of Michigan in Ann Arbor. Please welcome Craig to the stage.
Good morning. And thank you for having me back at AABC. Always a pleasure. My favorite conference of the year, mostly because the exposure to different types of technology, what's happening in the future, really granular discussions that are really exciting about what can happen. And so the only problem I've got is there's too many tracks with too many great speakers to be able to capture it all at the same time. So we got to figure out, Craig Rollers, we got to figure out how to replicate all this and be able to get it at the same time. I also want to acknowledge Tim and Ted, the conversations they had. It's a lot of what you're going to hear here is going to reflect some of what they've said, and I think but maybe a slightly different take. My objective today is to find the remote first. My objective today is talk a little bit about the imperative. You heard the word from Ted that there is an imperative around batteries, and particularly I'm going to focus on the United States. This is reflective of time I've spent in the last 20 years working on vehicle electrification, the last 15 years spent at Clarios. And particularly as it relates to Clarios, things that we've done trying to bring lithium-ion technology to market to support electrification, and importantly and bluntly, things we haven't done. It also does reflect time spent on the LiveBridge Consortium. Ted shared an overview a few minutes ago on that, and I was lucky enough to be invited to be part of that as well, and I think it's been really a very important activity. There's several colleagues here in the audience who've been part of that, contributing to the thought process about what we do here in the United States to establish a competitive supply chain to deliver on what's necessary, what's imperative around meeting the demand for advanced battery technologies. The goal here should be, as it would be with any region or any country, for us to be self-sufficient in defining our own destiny in terms of how we're going to deliver on this, how we're going to capture the economic value of this, and how we're going to use it to build our industry. So the first thing I'll talk about, and you're going to notice there's not going to be any graphs on this. There's going to be a few numbers, but this is going to be probably the least technical presentation you're going to see the whole week, so you can thank me later. We've heard a lot about the adoption rates, right? This is it's what we've all been waiting for. I've been working on this for 20 plus years. We thought this would happen in 2010. We thought this would happen in 2015. 2020, it still wasn't apparent. Well, here we are, 2022, it is happening. And what we see, if you take the charts that Ted was showing around vehicle adoption, if you take xEVs, hybrids, plug-in hybrids, full battery electric vehicles, the compounded annual growth rate we're going to see for vehicle adoption is around 30%. It's incredibly aggressive. So now all the work we've been doing over the last 15, 20 years on this industry around R&D, design, engineering, to create batteries and create solutions that were economically viable, that were safe, that provided the performance, that work doesn't stop, but now we have a new set of problems. This growth rate is going to drive demand for lithium-ion technologies to support EVs, particularly the battery electric version of these vehicles. 6x of what it is today. 6x. That is a lot of capacity that's required. You've heard about the commitments from GM, you've heard about the commitments from Ford. There are others on the cell manufacturing, but it's not just what happens there. Now, I would be remiss to talk about this. I know the AABC, automotive's in the title, but it's not just automotive. Stable power, think about grid resiliency, think about helping renewable energy enter the grid, requires energy storage. So we're seeing actually a growth rate in a relative sense that's even faster in stable power than it is in automotive. Nearly 40% compounded growth rate in BESS system deployments through 2030. So it's not just automotive, it's the whole industry that's going to have to rise up to meet this increasing demand. And as a side note, for all the innovators, if you got any metal air battery people here or flow battery people here, there's an opportunity beyond what lithium ion will do in BESS that I think is notable. When you get to longer duration storage, 10+ hours, lithium ion is probably not the solution there. And we're looking for opportunities. There is white space to happen there. So this isn't just a lithium scaling problem, it is also an R&D problem. So one could reasonably ask, after the last couple minutes, this sounds like great. This sounds like paradise. This is what we've all been waiting for, right? Well, there are some challenges. And there's some challenges particularly around the way we think about this in the US and the position that we're in. The first challenge is today, for all the batteries that are being produced and put into cars today, in the US, in terms of US labor, US factories, only about 30% of the value add is captured for those products. So what does that mean? If you think about the value chain all the way from the mining and extraction materials, the processing of those materials into cathode, anode powders, the creation of other components that go into the cell, and actually the cell manufacturer itself, that value add, we only see about 30% of that here in the US. And primarily, that's coming from the cell manufacturing that's already been installed and put in place. That will continue to improve, but we will struggle on the other parts of the value chain. Why is that? Well, because right now, all roads lead through China. China has done an incredibly good job at building out their infrastructure, building out their supply chain. The majority of materials, whether it's cathodes, anodes, they are processed and provided by China to the rest of the industry. That is a result of not only investment, but very, very particular industrial policy, which is a term you're going to hear a bit more in the next few minutes. Another reason is that traditionally in the US, these supply chain investments, which are capital intensive, have long time to market in terms of when you actually start to see revenue, and have, frankly, returns that are okay, but not stellar. These are not simply not attractive investments for the US market. In other parts of the world, you see investors who are more strategic, they're more patient, they have a longer term view on what it means to get returns. Here in the US, if you're putting down an investment versus something that has a short product cycle, has relatively lower CapEx requirements, and has much faster returns, it's a pretty simple choice. And frankly, working in a company that has been trying to rationalize some of these investments for the last 15 years, this is a problem. And the last challenge, not the only last challenge, but the last one I'll talk about here, is around workforce. To face the challenge we've got to grow this industry and scale up, we are not prepared from a workforce perspective to deliver that. Whether that's talking about PhDs, developing things in the lab, whether that's talking about technicians setting up lines on the floor, blue collar, hourly labor, skilled labor, even things like data scientists to deal with all the information that's going to come off these batteries once they're in the field. we need to do more, and we're not prepared to do that. That sounds pretty dire, but there is potential. And I think the conversation about Lightbridge is an important one because it was explicitly something that was put together and convened by the Department of Energy and FCAB to get information that would support industrial policy. How do we change this game? Industrial policy is critical in what's happened in China, critical in what's happened in Japan, it's critical in what's happened in Korea. It's even, since 2017, actively being done in Europe. We need to do that here as well. So thinking through some of the recommendations that Ted flashed up, what can we accomplish if we can set some industrial policy, if we can drive a different view on the way we think about investments? We can see improvements. Referencing the 30% I talked about earlier, if you take some reasonable pragmatic actions, we think we can capture up to about 65% of that value. Most of that comes from the Gigafactory announcements you're seeing and the cell manufacturing plants that are being deployed today, getting to roughly 90% of that cell manufacturing being done here in the US. It also means getting some of these raw material extractions up and running. You heard reference of that in a couple of the other presentations, and also getting into some of this mid-cycle materials processing, getting that onshored here. There are probably some things that aren't going to get fully brought onshore, but it can be a good start. In doing so, we can shift away some reliance from China, whether that's bringing that directly here or relying on trade partners that we already have established today. We can move away from that, shift to that reliance from China. We can also help, through some government interaction and policy, shape investment views in a way that's more positive. How do these investments get treated literally from a tax code perspective, financially, and how do those reflect in terms of the attractiveness of the investor base towards companies that want to and are ready to execute on these projects? And as a result, the projection is you could see up to 200,000 more jobs in this industry, incremental beyond what it would be in the momentum case by 2030. So this is a lot of potential. It's a good story. It does not mean the US moves into a leadership position, but it definitely means we would close the gap in terms of where we stand today. So, talking about industrial policy, what is happening, and it's not exclusively a government issue, but the government does play a key role. And we're already seeing some activity. Ted flashed up a few things already. I'll just touch on real quick. The bipartisan infrastructure law that's been put in place has provided capital infusion to help stimulate some of the execution of projects around materials processing, materials extraction, moving up into cell assembly. At the same time, we're seeing the Inflation Reduction Act on the other end, really incentivizing end use, providing end use incentives to stabilize demand. If you put those two things together, helping with capital, stabilizing demand, that's a big contributor to making these investments more attractive, more bankable for those who are going to provide the capital. Really, really critical. Two things. The capital infusion we've seen so far isn't significant, but it's sufficient, or it's necessary, not sufficient. And then the end use incentives need to be a lot more durable than they have been in the past. We need to see a long time frame to provide a stable view of demand and really de-risk the investments that are going to be brought into this industry. Constructing trade partnerships, we're already seeing a lot of activity in this space. We have to facilitate those partnerships that allow us to get access to materials that, frankly, we either can't find or can't ramp up fast enough here in the US. Part of doing that here in the US is going to be around permit reform and expediting. Right now, there's projects that really have a lot of value and could help bring some of this value capture here to the US, but they're stuck in the permitting process. Now, this doesn't mean give industry full reign to do whatever they want. This has to be done in an equitable way, in a fair way, but it has to be done in a way that can accelerate the execution of these projects and start getting materials available here in the US. One thing I don't have up here, but I think is also really critical from a federal government perspective, is what kind of programs they can put in place to help with retraining, upskilling, and really incentivizing folks to want to come into this industry to contribute to this growth. And I think that's also very critical. So one of the other things that I'd like to touch on is related to the closed loop. You heard this from Tim, you heard this from Ted. If we're truly going to get to a sustainable supply chain for advanced batteries in this country, you cannot do that simply by building up what happens on the front end. You have to think about the closed loop. This is something at Clarios that we've lived with today, and frankly, it's part of how we run our business. It's not even a conscious thing, it's just what we do. Because for us, making sure that every time we sell a battery on the lead acid side, we get a battery back is intrinsic to who we are, what we do. What that leads to in an end state, in a mature market, in the long term, is 99% recovery. In North America, 99% of the batteries, actually more than 99% of the batteries, lead acid batteries that are sold, are recovered one for one. And those batteries go into the recycling system and they're reused for future batteries. For us, on a global basis, that means we get 80% recycled content in every battery we produce around the world. This is really just meant to say, in the long term, if we can achieve these same kind of numbers around lithium-ion batteries that are going to be deployed over the next decade, this is a major factor in contributing to a sustainable future for this country in terms of supply chain. So the last thing I want to talk about is innovation. So why is it, I said earlier, why cannot we be a leader in this industry? We're catching up right now. We have a long way to go. Part of that is industrial policy. Part of that is lack of investment. Part of that is lack of labor training and upskilling. One thing we do very well here, though, is we do innovate. We've got tremendous amount of talent around innovation. And the way this can translate to a long-term leadership position is by actually innovating and changing the rules of the game. Whether that's inventing new cathodes, whether that's really commercializing solid state, whether that's bringing in technologies that can use more available, more abundant materials that, frankly, we don't have an issue finding. This will be the trick in terms of really positioning the US for long-term success, is you have to innovate your way to a sustainable future. So for everybody here who is working on something that I mentioned, some new technology, just because we're going to see this rapid scale up on the current version of technology today doesn't mean there's not space for this. In fact, it's even more critical than it's ever been in terms of where we'll be not just 10 years from now, 15 years, 20 years from now. So keep innovating. So with that, I thank you for your time and your attention and look forward to the Q&A in the roundtable.
Thank you, Craig. Our next speaker is Yoshinori Kita. He is the Deputy CTO and EV Battery Business Office at Panasonic Corporation of North America since 2021. In 1995, he was a visiting scholar at the University of Pennsylvania. He received his doctorate of engineering degree from Keio University after he joined a Sanyo Electric company in 1992. He mainly engaged material development for next generation of lithium-ion battery from 2018 to 2021. He was responsible for material development of lithium-ion battery at Panasonic Corporation. From 2021, he is based in the US and committed to sell mass production in the Gigafactory and material development for lithium-ion battery in North America. Please welcome Yoshinori to the stage. That's the advance. In advance.
Okay. Thank you for introducing me, and let me state my appreciation to have such an opportunity to talk here. And actually, I'm a little bit nervous and a little bit hungry. I'm hungry now, but please give me a time before lunchtime, And I try to introduce what is Panasonic energy and what we are needing in North America. Let me start. Let me my name, Yoshikida from Panasonic Energy Company. And now I'm based in Reno, Nevada, and belongs to Panasonic Corporation of North America. And at first, let me introduce Panasonic Energy Company. Panasonic Energy Company was founded in April 2022, just this year, and located in Osaka area, Japan. So our company is a newborn, just newborn. But we have nearly 100 years history for battery business. As a Panasonic Energy, we have, we have almost nearly 100 years history for battery business. In 1931, we started a dry battery business. And also we have already shipped cumulative number of cells, 165 billion cells. And also we have business lead acid, NiCad, lithium primary, and nickel metal hydride battery, and lithium ion batteries. And also we have nickel metal hydride battery and lithium ion battery for automotive. So we started a new business, more battery types, and we apply more applications from household and professional use, and then ICT use, and now we are going to eco-friendly vehicles. Dark green means we introduced mass production in worldwide. So we can say the pioneer of new technology implementation. This is our current business area of Panasonic Energy Company. You know, we have a lithium-ion battery cylindrical cells, 1865 and 2070 size for electric vehicles. And also, we have a module and system for energy system, and also various types of lithium batteries for data center and laptop, e-bike, and so on. And also we have dry batteries and primary battery and so on for remote control, right? Gas meter, eco, tire pressure monitor system, and so on. So we can say it's like a department store for batteries. And this is the first EV battery facility in Nevada. We have already started mass production in 2017, and nearly 7 billion cells has shipped. Our capacity is 35 gigawatt hours per year. And this is not only the capacity, but actually our shipment. Very beautiful area. And we can see the very beautiful sunset here, from here. Unfortunately, when I go home, too dark. And this is the second facility our second facility in North America. We have already started construction of a new facility, and that will produce cylindrical lithium batteries for EV. And we are planning initially 30 gigawatt hours per year. And this is a groundbreaking. And this is our drawing image for the new facilities. It will be a very green, beautiful area. Okay, and this is our cell production. A vertical axis is a cumulative numbers of cell production. We have studied 1865 cylindrical cells in Japan for EV, 2011. And sorry, in January 2017, we started mass production in Nevada, 2070 size type of cell. And only in North America, we have already shipped nearly 7 billion cells. And also, we are planning, as I mentioned, 30 gigawatt hours at Kansas facility. So, Japanese company sometimes conservative, maybe conservative, but we are aggressively, and once we decided, we will definitely do it. But we see the world change, big changes in the world. So our Panasonic Energy Corporation, we have a mission, a vision, which is we are achieving a society in which pursuit of happiness and sustainable environment are harmonized, free conflict. This is our mission and our vision, energy that changes the future. And our will, doing what humankind requires. That is our mission, vision, and will. And this is, from here, I'm introducing our 4 challenges. First one is technology. And the second challenge is supply chain. And third challenge is monozukuri. Monozukuri is in Japanese, but I mean just manufacturing difficulty or professional manufacturing or something like that. And the fourth one is environment. Let me start as a technology. As a pioneer of cutting-edge technology introduction, we have been leading the evolution of lithium-ion battery. You know, we have studied lithium-ion battery business from 1994. Firstly, we introduced a graphite anode. And 2003, NCM cathode, and 2006, NCA cathode, high nickel cathode. And we have introduced heat-resistant layer separator and silicon plus graphite anode. And we have already achieved 3 times higher energy density versus 1994, already 3 times. And now we have 20% and more increasement by 2030. That is our plan. And technology for next step, we have already 8065 and 2170. And now we are developing larger capacity and lower cost 4680. After verification of production in Wakayama factory in Japan, this is to the south of Osaka area, Japan, mass production will start in 2023, next year. Second challenge is supply chain in North America. As you know, in North America, we have a cell manufacturer and automotive manufacturer. And also in North America, we have many minerals. So we are focusing on suppliers in North America. I understand the various type of many suppliers starting business for lithium-ion batteries. And also I understand some of them are established and some of them are startup. And experienced company, new company, North American company, and move to North America from Asia or others. And some suppliers employ new technology and maybe traditional technology. There are so many kinds of suppliers, but we, Panasonic, need all suppliers in North America. And this is our policy. Maybe this policy comes from our experience with many Asian suppliers or experience with customers in North America. In general, supply chain means product or procurement. But we believe supply chain must be include not only procurement, but technology and quality. And also, once we started collaboration with suppliers, we never say just okay or not good. We never say that. Discuss and discuss, and then discuss. Let's grow together with us. And this is third challenge, monozukuri, I mentioned in Japanese. But please understand manufacturing difficulty or professional achieving like that. Here is 100 milligrams and 100 grams, 100 kilograms, 100 tons, and 100 kilotons. By 3-digit change, requirement in technology is so different. Panasonic has experienced lithium-ion battery monozukuri from 1980s for research and development. And from 1994, business started, and we have many factories in Japan and China and so on. And we have already experienced 6 years in North America. But I believe we still have some more challenges for gigafactory engineering. So we have experienced, but not enough. So we welcome to many engineers for all steps. And last challenge is environment. This is byproduct, carbon dioxide reduction of the difference between EV and internal combustion engine vehicle. The difference is 172 grams per kilometer. So after end of life of automotive, we can estimate carbon dioxide reduction is 5.7 kilogram carbon dioxide per 12170 cell. So, as I mentioned, we have nearly 7 billion cells already shipped in North America. So we can contribute to 40 megatons of carbon dioxide reduction. But please keep in mind, maybe double counted by our suppliers and maybe by our customers. That is, please keep in mind. And this is our fourth challenge for environment and by process. This is our cathode, our cathode material from mining to, and this is a current process, very, very in general. But we are trying to skip this portion to reduce the carbon dioxide. And this project is doing by with University of Tokyo and Prime Planet Energy Solutions under Toyota and the Toyota Tsusho Corporation. This is just one example, but I was excited to hear so many presentations yesterday here. There are in US, there are many recycling companies are focusing many things. So I'm very glad to hear that yesterday. And this is last page, fourth challenge environment by manufacturing. As I mentioned, we have not only lithium-ion battery, but many factories in worldwide. And Panasonic Energy has achieved carbon dioxide zero factory at 5 global sites already, which is 5, and expanding to all sites by 2028, including the Kansas and so on. So let me summarize. Panasonic Energy Company is just born this year, but we have 100 years history. And Panasonic has undertaken the second EV battery facility in Kansas, already started, and we decided. And Panasonic Energy is facing 2 core challenges: technology, supply chain, and monozukuri, and environment. Thank you for kindness, that's all.
Thank you very much. Our other speakers, could you please come up to the stage? We have people in the audience, our colleagues, if you want to raise your hand and we can start some questions. Go ahead, and there's questions on this side.
Thank you very much for fantastic talks.
If you could please also just state your affiliation and your name.
Oh, yeah.
Thanks.
I'm Woo-Sik Jang from Geon Chemicals. I have a question to Mr. Craig Rigby. So at the end of your talk, you mentioned that keep innovating. So what kind of innovation direction could be? So like, for example, all solid state battery or recycling or finding the new active materials, what innovation direction could be the mainstream?
I think it's still working, yeah.
Yep.
Okay, you can hear me. It's a great question. And I think, for the purposes of what I was talking about, I'm thinking about innovations as whether it's design, materials, innovation, or process innovations that create disruption in sort of the current state of the art, right? We're building an industry, we're seeing a lot of growth, we're seeing deployment of cell manufacturing, materials processing, based on essentially a paradigm of the way we make cells today, the way we use chemistries today. Obviously, there's various versions of that, but there's still a pretty basic paradigm. And I think the opportunity for innovation can be in any of those areas. It can be a new material, it could be solid state, which is certainly disruptive in terms of the way we think about the process and performance. It could be process related that creates a significant step function in cost reductions. From the perspective of reshuffling the deck, if you will, around leadership, global leadership around battery technology, I think any of one of those brought to market and commercialized and industrialized could be really critical. I think the key point, and I'll leave it there, is there's a lot of technology being developed here in this country. We've seen that in the past. We have to make sure as those technologies get mature enough to be industrialized, that industrialization, that investment happens here, and then the export of those technologies happens from here to the rest of the world. So I don't think it's limited to any one thing. I think it can be anything that disrupts the current state of the art.
Okay, go over there.
Hi, this is Asma from Rivian. I have a question for Tim, actually two questions. One related to the Ultium cells, and you're trying to transition to a unified cell for all of the different platforms that you're developing for EVs. What is your vision for future when these batteries hit their end of life? Are you transitioning into recycling all of that and bringing them back into the supply chain, or is a transition to a second life like home energy storage? And the other question I have is, knowing you're just transitioning into one Ultium cell, if there are different chemistries that will require a different cell architecture, what would be your plan for making that transition and shift into a new architecture that can satisfy all of the different platforms that you're developing right now?
Well, thank you for the question. And congratulations with all the progress Rivian has made to transform our industry. So the first question about recycling, how do we enable it? How do we make sure that we create the demand for it on our side? And so Ted mentioned every bit of scrap we recycle, we make sure we can then put that back into our value chain. So that's automatic that we do in all of our factories. We have recyclemybattery.com, which will have the actual owner of the battery find many ways to recycle it and keep that path moving forward. Moving into the hydro processes, or there's some exciting technology to say go direct cam to cam capability, is what we're working with innovation partners on to say we can actually use it and make it a big part of our future. Secondary use. Ultium was fundamentally architected for very easy secondary use. And that, individual cell module assembly with the wireless communication, you hook up the coolant, you got the power, it'll self-configure for you with secondary use. And so you can kind of see some of that, we're doing new batteries right now on the locomotive, or on the, smaller specialty equipment manufacturer markets or things like that. But that's a natural to say that when you're done with your battery as an individual user, now through GM Energy, there's going to be a marketplace where we can tie those people together and kind of have it be a future potential market for secondary use or recycling, and then the customers will have a choice. For me personally, we don't know where it's going to go. We just want to enable a lot of options to make it happen. And we don't have to be the only one doing it. We want to partner with the innovators to meet their needs to make it all happen. I think your second question was all around, well, how do you upgrade the chemistry within the format or change formats? When you look at the fundamental capital investment you make, it's all about reusing that capital. The 580, we coat too wide when it comes with that. And then any technology that can have that similar electrode coating capability is where it'll just fit into it naturally. Always the big question is, it's basically a 100 amp hour cell, you know, and so how can you then reconfigure a 100 amp hour cell to meet all of your needs? And we can do a lot with voltage as well as capacity to make that happen. I didn't mention that in North America, we hook 2 in parallel or 3 in parallel. We could hook 1 in series, moving together with all that. And that's all done through all those tabs with it. With our partners in China, we've got 2 different size cell where we just change the prismatic width, moving back and forth. And so, you know, where will we be 20 years from now? It'll be an evolution, because GM has a lot of welding technology where we can take approximately 8 different kinds of steels and weld them together in very small pieces in our body shops, and then make all these expressive vehicles that are structural packs moving forward. Right now, Ultium is a good starting point with that. Will we go to something, you know, I think one of the industry terms is more cell to pack or cell to vehicle type solutions. All of that is possible. You know, you can kind of imagine those crossbars that translated the crash load across the vehicle. Well, if we double the energy density and move them out of the crash, we don't have to do that anymore. And then we can have that same basic kind of very serviceable, very large secondary use CMA fit into any future vehicle in whatever people imagine 5-10 years from now. So it's just a starting point, and then we'll adapt as we go forward. And I hope I answered your question.
In a little bit of follow-up to that, I wanted to get both Craig's and Yoshinoro's thoughts on design for recycling at the cell level, and what it will take from an industry standpoint to move that issue along as recycling becomes more and more of an issue, and how we're going to really recycle these materials, because we're obviously going to need them.
This is, I'm not sure that this is just a good reply, but I have one data we can share here. Is after 200,000 miles actual driving by Model S and X, the retention capacity is average is 90%, plus minus 5.
That's great.
So, from the standing point of just one engineer, I'd like to use our cells more. So I understand there are so many difficulties. I understand that.
Yes.
But I hope that is my answer.
Yeah, go ahead. Yeah, absolutely.
Yeah, so I think it's a good question, and it's interesting because historically, and Craig will remember this as well, we sort of, you know, based on relatively low volumes by our standards of vehicle production, even with our hybrid electric vehicles, as we started our sort of, you know, most recent journey in electrification, given the volumes, we sort of did things in a not very designed for assembly way. You know, we had to make it very practical, but we weren't building a million F-150s. We were building maybe tens of thousands of Escape hybrids, for example, or other products. So, you know, we sort of, you know, swallowed hard and said, okay, we're going to have a lot of fasteners. These batteries are going to be assembled in a way we wouldn't normally do it, but it's what we could do practically. And not because we sort of had some constraints. The assembly plants were fixed. How do you make a process that fits into the assembly plant and not disrupt everything? So in an odd way, we have, you know, working with partners like Redwood, they love our old batteries. They're great. They can just take them apart and take the fasteners out. It's exactly, of course, what we don't want long-term, because that's not designed for assembly. It's not designed for speed. It's not perfectly efficient. And frankly, we did it really reliably, but there's lots of tails to how you get that done. So, you know, it's kind of a good, I think there's a healthy tension between sort of, you know, designing for, frankly speaking, it's really kind of hard to say we're going to design explicitly for recycling. That's pretty difficult to do. I do think, and I think you see this across the board, we tend to have some kind of a unit that we build to. And so I'm sure this is true for Tim as well. We do welding to a certain level. We may have something called a module, or we call it an array, or whatever the case might be. That helps for serviceability because you would rather not have to change a pack if you have some issue. But it also means that you have sort of a unit from a recycling standpoint. So that's pretty manageable in some respects, and it's also easy to redeploy some of those units. So that's why I think Tim sort of, you're not sure whether we're going to go sell the vehicle. That's really challenging. It's a great concept. I love the concept. I'm sort of a person pushing for that, but it means that batteries never fail under any circumstance. It's just a really tall order. So I think we'll find the right balance point. I think back to what Tim was saying, there's an evolution that's going to happen. We're going to figure some of this out. And I don't have the perfect crystal ball. I can tell you that we're much further along in the design for assembly, but we haven't forgotten the fact that we also need these to be redeployable. We need somebody to safely take them apart, et cetera. But so yeah, we're going to find the solutions.
Yeah, and just to talk about some of the forward-looking potential, right? I mean, both of us have the uniform stacked electrode, so every piece of that electrode gets the same life and the same experience. But at the end of life, then you can kind of imagine, if you would, a water jet process. And rather than shredding and I never can do this word right, precipitating, is that a good word? The materials out of it, you can mechanically disassemble it. So imagine a water jet, relieving the separator on the sides through a vision system, and then separating anode and cathode. And so now you're starting from a stronger place where there's less, pyro mixed in with it. And enabling that was pretty fundamental on, well, how can we now go parallel develop something like that to make that happen? And ultimately, everybody's goal is get it as direct as you can, right? And get off the sulfates or anything else on those intermediate steps. And if you can get that CAM material separate and then start from there, those are some of the innovations that we're looking to partner with. And so, the height of the cell, the length of the cell, all of that factors into some of that portfolio management with the view on recycling, but it does require innovation. It does require new ideas to make that happen.
And I think the conversation has come a long way in a very short amount of time where we're at now. So we should all be very proud of that and move in that direction. But they are certainly big challenges. Other questions from the audience?
We have a question right
Go ahead.
back here.
Hi, Andrew Saucer, Argus Media. We're getting closer towards 2025 when many auto and battery makers have a lot of their goals laid out as sort of their first sort of target. I'm curious what y'all see as some of the challenges y'all are going to face getting to those goals in 2023 and maybe 2024 specifically.
I'll answer this first because Tim's already kind of answered it, I think, in some respects. But as I think I sort of covered a different part of it, so I think our talks were kind of complementary. But through 2025, we're all locked up, right? I mean, we have to have agreements in place. That's done. So I think the risk are 2030 and beyond. I think that's where I see the bigger risk. And again, everyone's feverishly working to manage that risk. It's just, there are some things that are a bit unprecedented. There's never been this much demand for lithium on Earth ever. But I sort of take heart thinking about the fact that, I remember the early days of electric vehicles, at least the modern age of electric vehicles, when we were really kind of all surprised when Nissan came out, really low volume, but with a pure cobalt cathode. It was sort of what they could do at the time. But we clearly recognized we were never going to launch a vehicle for various reasons, but especially we weren't going to be able to get to scale using a cobalt cathode, a pure cobalt cathode. So I'm also encouraged that, that the nice thing about automotive is you've got scale that's going to drive the innovation, and there's scale that will justify the investment. So I'm encouraged, and uncommon things like the Salton Sea, we wouldn't have tapped that a decade ago. So there are new, and actually lithium is reasonably plentiful. It's just, we take it from the most economical sources today. But now we're having to get more creative, and it's worth the investment. So Bad news is it's expensive. The good news is a lot of people will invest in it. So it's, this tension again and this dynamic is at play. But Ted, I'll let you jump in.
In addition to what Ted said, I would say quality.
Yeah.
As you're transforming and scaling an industry, Hummer moves 50 pounds of lithium back and forth between the anode and the cathode. You don't see it because it's at the atomic level, but we're moving metal. And that lithium element is hyperactive. And it'll do lithium byproducts, losing capacity or creating other byproducts. The nature of the cell, the smallest amount of moisture, H2O, will turn the electrolyte into an acid and go after that. And so it's every operator, every factory, every day having the courage to put their hand up to say it doesn't look the same. We don't want them to say it looks bad. We just say it doesn't look the same. And then getting that fast response team to have this scale really react to it. And so, the cars are incredible. People, we have incredible loyalty on our EVs. I think some of my, I probably shouldn't say this, but biggest joy is reading Mach-E reviews, where the cars work. Now we just got to make them meet every expectation with our quality systems.
Do we have time for maybe one more somewhere?
Hello, my name is Luke Workman from Electric Goddess, and I had two questions. One was, we see a lot of corrosion-related failures with our battery recycling company that we have. Maybe 80, 90% of the reason we get batteries is corrosion-related. Can you comment on what actions were taken to minimize corrosion-related failures? And then my next question was on the double stack Ultium pack. Where do you make the compromise in thermal runaway path direction of plasma and hot gas? Is it down towards the other cells or up towards the passenger compartment?
You want to do corrosion first, and I'll do Ultium second?
Go ahead, I'll let you take this one.
The challenge with corrosion, as you can imagine, is how well do you seal the pack? And we do a helium check at the end of a factory to make sure that our seals are good, to minimize any of that combinational electrical energy plus any other galvanic corrosion that you can have there with it. We have a number of diagnostics that we run to say, how do we catch it very early and service it rather than have it go to a point where it's an actual vehicle performance reduction in that. And I'll tell you, one of the blessings you have with these vehicles is the Lyric's got 288 cells and the Hummer's got 576. It's a statistically valid set to look for differences and look for odd behavior that you can run all the bots up in the cloud in the virtual twin. And so, three-pronged strategy, sealing, on-vehicle detection, cloud detection is the way we look at that. Thermal propagation is a very complicated issue. It has a lot to do with initiation from your manufacturing process and other things like that. But if you look at the Hummer, there's actual channels that we have. And, we've got some separators that'll absorb energy, and then there's some mica channels to try to vent that gas as we run it. And it's all specifically designed to handle that volume as we've seen a defect cell do something unexpected. The real goal, though, and if you notice in the industry, it's actually happening, you're not hearing about them anymore because we're catching them in the cloud and we're getting them to the dealer before it happens. And I'm kind of famous inside of GM that we have to meet all the safety, including toxic gas venting. And that's where we really have to get to as an industry on a 26262 functional safety category. And so not only the mitigation, but the prevention, the industry is making great strides forward in. I hope
Go ahead.
that answered.
Yeah, I'll just add, so there's not much to add. The only thing I would say is that in some respects at Ford, we took a slightly different path, especially our early electric vehicles in the 90s. And then as we moved into hybrid electric vehicles, we really tried to keep the system as simple as possible. And so, and we tried to take advantage of everything on the vehicle. So we used air cooling with our early models, and we used, and we did a combination. It was a little more sophisticated, where we could use the AC and an aux unit. And in some ways, our life got so much easier when we sealed the packs up. When we went to liquid cooling and sealed the packs up, I think so. We dealt with corrosion when it was very real all the time. And we actually had multiple generations of vehicles that took advantage of air cooling. And it was a nice solution. It's just that the engineering challenges were significant. So I think we've actually seen that by having the sealed packs, as Tim mentioned. I think you guys kind of started there with the Volt, but we sort of migrated. We sort of started elsewhere. And so our lives got much simpler from an engineering standpoint.
All right, well, I'm sure our speakers will be around for some additional questions, but let's thank them for their great presentations. And that's going to bring us to our lunch, and lunch is located out in the areas. You have 3 areas to get lunch, so if you go to an area where we're having our lunch and you don't find a place, there's another area that you can have for lunch. So thank you. We'll be back in here starting at 2 o'clock.
Some of the old.
Hello, I'm Oliver Gross, Science and World Advisory Committee Leader of the United States Advanced Battery Consortium. I want to thank the Advanced Automotive Battery Congress for this opportunity for the USABC to sponsor the 22nd conference. The United States Advanced Battery Consortium, LLC, is a subsidiary of US CAR. Enabled by a cooperative agreement with the U.S. Department of Energy, USABC's mission is to develop electrochemical energy storage technologies and advance commercialization of next-generation electrified vehicle applications. In support of its mission, USABC has developed mid- and long-term goals to guide its projects and measure its progress. We have funded lithium-ion battery cell technology development, which has yielded significant improvements in performance and cost over the last 25 years and can be found in our vehicles on the road today. We look forward to continuing the work with battery cell technology developers to achieve our goals in the future. If you would like to know anything more about the USABC or our funding opportunities, please reach out to one of our members here today or through the US CAR website. It is our pleasure to provide lunch today. Please enjoy.
Tell which one you were on.
Cool, right?
All right, can you hear us now, Seth? I can't hear him. You're muted, Seth.
I can hear you.
All right, good. That's all I want to check. Thank you.
Sure thing.
All right, bye.
Bye.
Good afternoon. Welcome to the afternoon session of electric vehicles. My name is Mike Fitsenko. I'm the executive chairman of Scion Power. This is my 43rd year in the battery industry, and it's never been more exciting. This is even after, so I was at Ovonic, where we invented nickel metal hydride batteries and put 30 million Priuses on the road. And after also being one of the founding members of the BASF battery division, which was formed in 2012 to see $1 billion put into that. This is the most exciting time for me in the industry because I've heard about electric vehicles since I was a little boy in Detroit area. First when oil crisis happened, and then when California Air Resources Board put in, my company Ovonic was a big part of the who killed the electric car theory, and when mandates got pulled out, that evaporated. But now you're seeing the global transformation of the entire transportation industry. You're seeing money put in, the decimal points are over 2 places from where it was in the past. And it's really an amazing time. What I'm working on now is advanced next generation lithium metal stuff, which you'll hear about tomorrow if you're interested. But what we're going to hear as a Detroiter, as a born and raised Detroiter, what happened at General Motors, Ford, and at that time Chrysler, the big three, was always, what drove things in the Detroit area and across the United States. So during the plenary section, we heard the big talks, the grand vision from those big three companies on what they saw coming forward. Our session this afternoon is going to be, I'm very honored, we're going to have talks from General Motors and Ford and Stellantis today, which are going to be the complement to the grand vision you heard during the plenary sections. How are we going to accomplish this? What are the details surrounding product introductions, how they differentiate from their competitors, what gives them heartburn, what are they working on? It's a very exciting time. So with that kind of an introduction to our session, it's my honor to introduce our first speaker, Oliver Gross, a colleague from many years and in the Detroit area from Stellantis, who's going to be telling us about engineering for emerging traction batteries and related regulations. Oliver?
Well, thanks, Mike. And I also want to thank AABC organizers for inviting me to this very prestigious conference. It's actually about my 12th one here, and I don't have 42 years. I have about 30, but that's also in fuel cells, which we'll leave for another day when we start talking about that. What I find really interesting here is as we've been evolving over these, let's say, 12 years of AABC, we've seen challenges come and go, some conquered, and then new ones arise. It's all part of the maturation of the industry. And so now we're at the point where for vehicle guys and girls, we used to think about, okay, we know our cars, we know the regulations and so on, but now we have a whole new class. And batteries are falling into this category as well. And this is something that's becoming highly relevant today. So I thought it'd be really nice to go through some of the related topics of what we're seeing here. But first, a little bit about Stellantis. Stellantis, as you know, it's a relatively young company, a little under 2 years old. It's actually a merger between Fiat Chrysler Automobiles and PSA. And our CEO, Carlos Tavares, brought forth the Dare Forward initiative for 2030. And just to give you an idea of the significance of that means in the context of what we're meeting here today for electrification, some really ambitious goals were set, and with a lot of commitment to achieve those goals. 50% of all vehicles to be electrified in the United States here by 2030, and 100% of all cars in Europe by 2030. But on top of that, here in the US, that means 25 new vehicles being brought out. And of course, that also means it adds up around the world, 5 million vehicles by 2030. Just think about that for a moment, about the magnitude in terms of the batteries. And I need to also comment about carbon net zero by 2038, which is it's a slightly associated but different context point, equally challenging, potentially more. Well, where I'd like to start with is that we've done a lot of work, developing batteries on cycle life. Great. Well, let's talk about life cycle for a moment. So, and there was a lot of talk this morning about, or in the previous plenary sessions about circular economies, the circular life cycle. And I'd like to take this a little bit further. When you think about the battery, you measure it really with its experience that's related over time and its throughput energy. Cycles is one way of looking at it. So think of it this way, just a simple, cartoon perspective that we begin, with the mining, we go through the refining, synthesis, manufacture, its primary use, perhaps we convert and do some secondary use and we recycle. And the fact is that there's energy associated with every single item at every single step, and it adds up. And so when we want to look at this, we think of life, well, and measured definitely in distance traveled and in years, but we also want to look at total energy throughput in the holistic sense. And that's the one thing I want to bring forth. We're going to that mindset, and regulators are too. This is the shift that's occurring. So what we want to talk a little bit about is like some of the landscape, some of the items that we have here now. And so what we have here are some of the regulatory bodies that we have right now influencing really vehicle batteries. And it's about life cycle in that context. And if we go down the list here, they are all either having rolled out their first editions of policies and standards, or they're still in the process of doing so. The first one I'd like to highlight here is the United Nations. It's a global activity really around in-vehicle battery durability, which we're going to explore a little bit further, under GTR 22, and it affects plug-in vehicles. The European Commission, which covers EU and UK, they're looking at vehicle emissions over the life of the vehicle. And they have the European battery regulation, which also includes a battery passport from a traceability perspective. That's part of that. And please note, it covers all forms of electrification. Another one for EPA here in the United States. It's in the development area right now, but we expect that we'll probably hear the first thing about it in the first quarter of 2023. There was recently some press release from the EPA with regards to getting some approvals, and this is going to become more mature, but this is again with plug-in vehicles. And then CARB, California Air Resources Board, which covers California and the Section 177 states. This is looking at vehicle emissions over life for zero emission vehicle durability. And this covers any plug-in vehicle, fuel cell vehicles also cover that. China with the VECC also looks at the emissions. We expect that there will be revisions on that as these others roll out. Well, there's a lot of new terminologies that we're going to now need to get used to, and these will become probably part of the lexicon of our daily jobs. The first one I'd like to talk about is in-vehicle battery durability, that term that we saw from the UN. And it's really a measure of the battery life in its primary application. So first use, and it's related to looking at the battery with regards to one or more minimum performance requirements, or MPRs. Minimum performance requirements would be the setting of a limit. And it would be the typical thing that you would say with any kind of key performance indicator or so on. And what it does is it does recognize that a vehicle and the battery associated with that, it ages over time and with the distance and energy throughput, just as we typically have here. But in the case of the battery, we have to look at creating a common framework, which allows us to be able to define and track this in-vehicle battery durability. And this is really what the topic of these regulations are. So you see a power fade and energy fade. Those are the factors that we see in battery. We have to somehow translate that into life. So this is the mechanism that most of the regulators have been using to lead towards this form of regulation. I also would like to highlight that when we talk about exportable power, is a phrase which I like to use, but it's V2X. For what we'll call secondary applications. I don't mean secondary life, but I mean secondary applications, which would be when you're exporting power. That is also needing to be included in the common framework. And it's very important. We will be exploring that a little bit more. So we talked about the regulations, and we looked about in-vehicle battery durability. One of the units that we're going to explore here is something called usable battery energy. And we're going to contrast that to vehicle range, because the regulations tend to bring the vehicle and the battery together, as they should, because they are part of the common system. So the usable battery energy, in this case, it's the stored energy inside of the traction battery that's available for vehicle traction under expected normal conditions. Simple terms, it tells us that I should expect to have this much energy when operating under normal types of conditions. Because this is typically what some people think about that. For those of us who would be developing a battery cell, we might do a C/3 discharge, but we all know that the real use, it's peaky and more agitated. And this is an extreme case here, by the way. It shows that there could be a difference. But this is the realistic difference between maybe how we rate a cell and what is truly usable. So keep this in context. Well, the regulators have to do something that makes some sense where everybody can use. And so the language needs to stick around something such as certification drive cycles. And the WLTP I'm using here as an example because it's actually the one that's done by UN under GTR 22 and is used for many other activities. So that typically is, for example, the way that you would do a determination of usable battery energy by doing an agreed upon certification cycle. So this, again, is pretty typical to the way that we do our business today. Now, interestingly enough, we all talk a lot about state of health. State of health, however, is not as commonly agreed upon of a definition. And so one of the newer definitions that's been formed is looking at something that is called state of certified energy. It does recognize the state of health is definitely about capacity fade, power fade, and it's a relationship between the two. And then how do we get to a number that converges all of this into one agreed upon state? Well, that was the aspiration of state of certified energy, or SOCE. And I know by the end of this time, you guys will be like either rambling these acronyms off like there's no tomorrow or be totally lost. Either way, we'll have done well. The state of certified energy is talking about that usable battery energy, but a certified usable battery energy, which we did from the drive cycle. And then we look at the usable battery energy at any point in life. Now, think about this for a sec. There's two ways to think about the current, what we call current usable battery energy. One is what you infer from your system that it should be. The other way is that you actually go and test your vehicle and actually derive that out. And so that's something to think about. But the definition either way comes from looking at that usable battery energy. And by the way, you'll notice here that the minimum performance requirement would be then some margin that you would set forth. And so it's the same physical factors SOCE has as SOH. It's just putting it into an agreed upon reference frame. So it makes our jobs easier in terms of comparing one to the other. But the fact is that it doesn't inhibit we as automakers or battery makers from developing our own SOH algorithms. We just simply need to know what that transfer function is going to look like. And later on, we'll talk a little bit about some of the criteria that we need to take into account when doing so. And that's, I'm going to get into one right now, which is looking at both the minimum performance requirements and when we talk about accuracy. If we have end-of-life minimum performance requirements, we need to be able to predict them and also be able to independently measure. And so what was done in one of the regulations, at least with GTR 22, was field data was taken and used to determine what typical results were from real world activities. And just to, what it looked like was this here. It was actually, this particular body was from the Geotab set. And the one I'm actually showing here is not the UN, but it's actually that was used for CARB. But what it did was it looked at the probability that you see of not being able to meet the end-of-life criteria, which is your minimum performance requirement, by the population of vehicles. Just so you know, there's an aggregate of about 60-odd different vehicles that are in here. And this was done based upon a linear fade extrapolation. I can get into the details of how that calculation was done, but it was independently vetted that it seemed to be pretty sound for an estimate. So what you see here, for example, is that if your state of health, I'm going to use that term state of health because that's what CARB uses, at 70%, it would say that 20% of all vehicles would potentially not be able to meet that. So that's that's what that basically says. But at 65%, that number drops to 10. And those numbers will become important because what happens in the case of CARB, the proposal is that the 70% state of health at 10 years and 150,000 miles is the target, but under any kind of measurement or evaluation, so long as it's meeting the 65% state of health, that's considered acceptable. Regulations get a little bit more sophisticated than that. But here's the deal. What we've done there was based upon field data and some theory. But for every single specific vehicle, every unique vehicle, there has to be the ability to take a monitor that actually gives you that SOH or SOCE and then independently measure that, usually through a certification drive cycle, and be within 5%, specifically that the monitor that is in the car that's giving you that measurement does not exceed the actual measured value by more than 5%. Now, it actually gets more complicated than that if you look at the GTR 22, but in a lumped sense, this is what this says. So the challenge here is to have an SOH algorithm that is capable of accurately predicting and presenting your results to within 5%. And that will be regulatorily driven. So now we compare a little bit. Now, the UN and CARB are pretty nice to look at. So the UN GTR minimum performance requirement, they actually set two targets. They set one for initially was 5 years, 100,000 kilometers, 60,000 miles of 80% state of certified energy, SOCE. And then for 8 years, 160,000 kilometers or 100,000 miles, 70% SOCE. So it looks like these 2 points here. Now, the good news is that CARB set identical values for battery warranty. UN, just again, is for warranty and battery durability. CARB set the same for battery warranty. However, at the vehicle level, when we talk about range of the vehicle, CARB set a different value. And in this one, it was set to at least up until 2030, 70% certified vehicle range at 10 years, 150,000 miles. So it's a different value again. Now, why is this important? It's because in a battery electric vehicle, very typically said that the battery's energy, usable battery energy, is directly related to that of the range. The two are associated. And that's typically what we assume. And so therefore, there's a bit of a disconnect in terms of warranty and durability, which is not necessarily a bad thing, because the fact is that what you're saying is you want to warrant for this and you give some grace for durability and understanding that vehicles will achieve their durability life in various ways. Well, we also understand that as technologies go ahead, that there may be batteries that don't reliably support that durability target. And that's actually one concern that's been brought up by many different members, representatives, OEMs, battery makers, and so on. And well, the good news is that under the regulations, particularly for ACC2, which is the new regulation, that a reserve battery capacity is quite allowed. And so therefore, it could be a certain amount of battery reserve that you do not use in your day-to-day operation, which then is kept in order to enhance life. So your certified vehicle range will get restricted. Now, if this happens, however, ACC2 also says that you must use the reserve energy, both the unused and the original reserve energy, in your calculation for state of health. So you don't, there's no free pass here. You still need to capture in battery state of health the actual usable battery energy when reserve is untethered. And I'm showing just one example here. You can imagine different kinds of scenarios and how to do that. This is just one example I show in the plot to the right, whereby we start with a reserve, we slowly feed it out to the end of a certain period of time, at which point in time we follow another faded pathway. But there are different kinds of ways that you can look at doing this. And it's really up to then the OE to decide on how to actually achieve this, or whether you even need it. Because the fact is, you only use this if you feel that the battery's durability life cannot easily meet the target without some form of reserve. So if we compare, say, CARB ACC2 to the UNEV GTR, we can look at a few things that are common and a few things that are different. The first things here, for example, is that they're both looking at state of health or state of certified energy. There's also the term state of certified range, which is that vehicle range, which is, it's based off the certified vehicle range. And so those are the terms that are used. But there are battery-tied parameters. Okay, these are characteristics that need to be reported. And you notice that CARB ACC2 has a list of them, all of which are pretty typical of the kinds of things that you would be seeing out of any kind of BMS. There's really nothing necessarily that's dramatic, but it is mandated that that information be accessible. And then there are on charge and discharges, there's some in the case of ACC2, none in the case of UNGTR. And then there's vehicle operating tracking parameters from both sides that you can see, because UNGTR does cover vehicle range. ACC2 does that as well, but it also looks at the interaction of it with the grid-tied services. And also, ACC2 is building itself off the experience of onboard diagnostics and prior regulations, so we should keep that in mind here. And you'll notice that both of them do take into account exported power. In the case of the UN GTR, the key thing here is that they converted to a virtual mileage, and so it's accounted for. It has not yet been completely agreed upon on how that's going to be done in the case of ACC2. It could be that, or it could be through another form of accounting measure. Now, I gave you the US side. This is the European side. And the European battery regulation also is coming out in mid-2023 with a series of parameters that also need to be exported off of the vehicle specifically related to the battery. These are still going through their final definitions, but these are also items that will be required to be exported from or exportable from the vehicle. And they are, again, as I said, battery related. I'm not saying that to be from the BMS, but they have to be exportable from the vehicle. And so if you look through here, there's many of them look rather familiar to us, right? It's a bit of an eye chart, I understand that, but you can see here that in many of these cases, there are pretty typical kinds of the parameters that we'd be looking at, although there's a couple here that perhaps maybe we're not that familiar with. So in conclusion, the things I want us to think about is that the regulatory bodies are asking for a lot of the data that we typically can see coming off of our standard BMSs. At first, it's not necessarily dramatic, but there are some calculations based upon the new terminologies that we need to take into consideration of how we're going to do that. And I went through a few of them with you here. Management of battery state of health. It's going to be based upon usable battery energy over life, and it's going to be really, really key in terms of determining the life and regulatory compliance. I do need to emphasize, be careful about the accuracy robustness that needs to be done in these systems, from the battery through the vehicle, particularly the estimation of SOH. And the implementation efforts could be incredibly complex. And finally, I did want to bring one up because I want to give homage to a presentation that was done this morning, was on heavy-duty vehicles are also being impacted both by UN and also by others. I wanted to bring the point that whereas CARB has already done some work in here, UN will be doing the same. And with that, I'd like to thank you very much for this opportunity, and hopefully we'll have a great rest of the conference.
Thank you, Oliver. I'm sure there's going to be a lot of questions that'll be handled. We'll have everybody come back up during the standard Q&A format. Our next speaker is going to be Bob Tanaka, who's the Senior Technical Leader from Ford. Bob, come on up, please. We're going to be very interested to hear his talk, Batteries for Commercial Electric Vehicle Applications.
Hello, everyone. It's an honor to be here today. So the topic is batteries for commercial electric vehicle applications. So the topics I'll be going over today will be first the commercial vehicle application types, high voltage battery capabilities needed to support those applications, differences from the retail/passenger vehicle battery usage compared to commercial vehicle battery usage. I'll go over some of the commercial battery cell types, not necessarily form factor, but the usage requirements for the commercial versus retail batteries. And I'll end up with some final comments. What you see here is commercial vehicle classifications by the US government. They're all rated by gross vehicle weight rating. 3 different columns. One is the Federal Highway Administration. Second column is the EPA emissions classification for passenger vehicles. And then the final column is EPA classifications for heavy-duty vehicles. So you can see that the light-duty Class 1 to heavy-duty Class 8, the ratings and categories are not identical. They're similar, but not necessarily exactly the same. Where Ford has a lot of vehicles is in the light-duty and medium-duty classification. As a couple of examples, the E-Transit is GVWR at 9,500 pounds. So you see it fits into the light-duty Class 2 for the Federal Highway Administration, and under medium-duty for the passenger vehicle classification. The F-150 Lightning, it has a GVWR of 8,250 pounds. So you can see it fits into the light-duty category across the board. And the heavy-duty, you can see those go up to GVWR values of in excess of 60,000 pounds. Commercial vehicles are used for a number of different purposes. One of the most important, of course, is cargo transport, truck and van. Whether the truck or van is refrigerated versus non-refrigerated, and a BEV application can have a pretty significant effect on the watt-hour per mile consumption for the vehicle. Also, whether the vehicle for cargo transport is short haul versus long haul. Short haul vehicles can be handled very well with BEVs, but when you get to long haul applications, even if you're able to use fast charging, there is still a compromise you have to take in order to get the vehicle from the starting point to its destination, right? So as you can imagine, the faster you're able to do fast charging, or the longer range, the bigger the battery, will reduce the number of times it would have to stop for a long haul. But that's where perhaps fuel cell vehicles, where you're not storing the energy in the electrodes, you're storing them in the fuel, the hydrogen. That's where fuel cell vehicles have a distinct advantage for long distance travel. Also, passenger transport, very important commercial application. Taxis and shared ride, Uber, Lyft type applications, as well as vans, shuttles, buses. Buses could be small buses or very large buses. Very different types of passenger transport applications. And the third category I've listed here is utility services. You can have powered equipment services such as tractors and cranes, and combined transport and utility. And a good example would be an ambulance, where you have not only the passenger being transported, but all of the medical equipment, and the powering of that is also needed at the same time. Similar for a tow truck, you have transportation and utility power requirements. These are some examples of Ford commercial vehicle application types. The first 5 you see in the pictures there are various forms of E-Transit vehicles: a low roof cargo van, medium roof cargo van, high roof cargo van, chassis cab, cutaway, and then an F-150 Lightning truck. You can see from the rear view, if you look at the chassis cab and the cutaway, you can see very different back ends to the cabin. And so the cabin climate loads, if you think about it, can be very different. If you have a cutaway versus a chassis cab, you may have a very small cabin area to heat or cool for the driver and passenger comfort. But in a cutaway, you may have a lot of cabin air going back into the bed area. So the climate loads can be very different. You also think of delivery type vehicles that are a lot of opening and closing of the doors. There's certain drivers that may not even bother to close the door. So especially in winter or summer, you can have quite a lot of consumption of energy that has nothing to do with the actual propulsion of the vehicle, but everything to do with the climate control of the vehicle. In looking at the frontal area of the vehicle, the low roof cargo van versus the high roof cargo van, we're using the same battery, but the vehicle load roads can vary greatly from design to design. So the high roof van, has much more frontal area, so it's less aerodynamic than the low roof van. So you actually have lower payload capability with a high roof van compared to the low roof van. And that's all slightly because of the weight, but a lot of it has to do with the aerodynamics of the vehicle. Battery capabilities needed for the propulsion of the vehicle. As I mentioned on the prior page, generally, commercial vehicle tends to have less aerodynamic characteristics than passenger vehicles. They're generally heavier than the passenger vehicles. They have wider tires generally and greater road loads that translate to greater watt-hour per mile energy consumption rates. So for a given size of battery, a commercial vehicle generally will not be able to go as long a distance as a passenger vehicle. That's a very important distinction. For vehicle cabin climate control, it can consume quite a bit of the total energy of the battery. As I mentioned, the cabin size can have a pretty big effect on how much climate control loads are actually consumed, of the battery's total energy. And auxiliary loads are another source of consumption of energy that are not part of vehicle traction. Ford has something called ProPower on board, which gives 120 volt or 240 volt plugs that are part of the vehicle. Our F-150 Lightning has standard 8 120 volt plug and an option for 2 additional 120 volt plugs and 1 240 volt plug. So with the premium version of the Lightning, you would have 2.4 kilowatt plugs, a total of 20 amps, plus 1 240 volt plug, 9.6 kilowatts with about 30 amps capability. So the ProPower on board is one example. Cargo heating and refrigeration, another example of the aux loads. Monitoring and medical equipments, again, such as an ambulance. Third, usage of the battery's power and energy besides just propulsion of the vehicle. And the aux loads, can be a significant portion, can actually even be larger consumption than the vehicle traction requirements for the battery. Seasonal energy consumption rates, that's something that maybe a lot of people don't recognize. I think more and more people realize it these days, but a vehicle EV range can be substantially reduced in winter, can actually be less than half of the vehicle range in spring or fall. And I've listed some of the items here in order of significance. The cabin climate loads are greatest during the winter months. And you will generally have higher vehicle road loads. The roads are, less traction in winter than in spring, summer, or fall. And also the battery usable energy generally decreases at colder temperatures, but that effect is not as large as the other two items listed above. It's really the cabin climate loads, the energy consumption of that has the biggest effect on the winter time versus springtime vehicle range. Conversely, in the hottest summer months, it's not uncommon to have 75 to 80% of the vehicle range that you would have in spring or fall, again, because of climate control usage. The amount of power consumption to keep the cabin cool is not as great as it is in the winter months to keep the cabin warm. But it still can have a pretty significant effect. The battery, I have parenthetically, the last item on this page, battery usable energy increases at warmer battery temperatures. So you actually have a little bit more total usable energy in the summertime from the battery. But the climate control usage still results in a reduction in vehicle range compared to the spring or fall months. Now, DC fast charge usage is another, very important point. For most commercial vehicles, they'll have a set drive route. So there'll be many commercial vehicles that may not need to do any DC fast charging, and there'll be others that will need to do it almost on a daily basis, depending upon the distances the vehicle needs to travel per day. The commercial vehicles tend to have consistent daily drive routes for the majority of them. You may have an occasion for some of them that have relatively short drives per day. There's still the need for an occasional DC fast charge. But for many of them, they really, I guess from our commercial customers, they say they don't necessarily need DC fast charges, whereas other commercial customers will tell us they need to be doing it on a daily basis. So in the second bullet, almost no DC fast charge is needed for vehicles that have short enough daily driving distances. I said less than 70% of the winter time vehicle total EV range. So if you think of the winter time, that's when you'll have the lowest amount of battery energy, and 70% with the assumption that the battery would degrade about 30% usable energy by the time it would be considered at end of life. So if the daily driving distance is less than 70% of the wintertime vehicle total EV range, you would probably have very little need for DC fast charging. Whereas conversely, if the vehicle's daily or multi-daily DC fast charging needs would be for those types of vehicles where their daily driving range is greater than 100% of the spring or fall vehicle total EV range. So if you think of a battery when it's new in the springtime, that's where you're going to have the longest, the best range. But as the battery ages, its range will decrease, and also summertime versus wintertime will also affect it. So there'll be, in those types of conditions, you would need to be doing DC fast charging during the fall and during the winter and summer months, and even more so as the battery ages over life. Commercial BEV battery cell wants is actually same as the passenger or vehicle battery cell wants. Higher energy density at the cell level, higher power density, better cycle life, better throughput capability, but at lower cost. Now these are all the wants, but really in order to achieve the best combination, it does require trade-offs or compromises for each. I'd say of these four factors, the only ones that are kind of in unison are power density and cycle life throughput. As the power density of the cell increases, it generally results in cells that have better cycle life and better throughput capability. But everything else is kind of a trade-off in a different direction. So if you want cells with higher energy density, you end up making the electrodes thicker, go to higher active material loading levels, and that ends up sacrificing some power density. So a BEV cell will have a very high power to energy ratio, but if you need more power density, you have to make the electrodes thinner, make the active material loading a little bit lower, so you get more power per square centimeter of electrode area. But because the electrodes are thinner, you have more percentage of separator and electrolyte weight in the cell and volume, so that affects the overall energy density. Going to higher energy density also results in generally higher cost because you're having to use more premium materials. It can result in lower life just because you're using the cells at a very high usage rate and not backing off, if you will, on the state of charge window and current charge and discharge current. So these are, opposing factors. And so part of the trick is really to find the best compromise of all these factors in determining the best battery cell. And if you were to try to have one battery cell, it may not be the best cell for all applications. So the choice is to commonize, minimize complexity, or to accept greater levels of complexity, but to have more optimized capability for different applications. So if you have limited or no DC fast charging, limited cycle life needs, and watt-hour or amp-hour throughput needed, that would allow you to get the highest watt-hour per liter cell design with the lowest, if you will, dollar per kilowatt-hour cost. In that case, you would have premium anodes, premium lithium-ion cells, high nickel cathodes typically, and or silicon-containing anodes. And there you'd have the thickest electrodes, highest loading, gives you the highest energy density. If you have significant DC fast charging needs or significant cycle life, you would need to sacrifice some 1 hour per liter and some cost to get the higher power to energy ratio cell designs. And it's not a technology issue, it's really a design issue. You can design cells today, just how you size the electrode thickness and active material loading. The lowest dollar per kilowatt hour comes with some acceptable compromises of vehicle attributes. For example, lithium iron phosphate, lower cost, but compromise in energy density and eventually the low temperature performance is also reduced with LFP. But as other talks have told you, lithium iron phosphate, does have much better cycle life than typical NCM battery cell. There's also various manganese-rich chemistries, LMFP, LMR, other developments going on. So I think in the future there will be more and more of these lower cost cell designs that will be implemented for commercial applications. So final comments. There are many commercial vehicle applications today. At Ford, we have the E-Transit and the F-150 Lightning. We expect there will be more and more electrification coming in the future. But as of today, there's still mostly non-electrified vehicles in use. There will be greater usage demands and cycle life expectations for battery cells for commercial and retail EV applications. And really designing the cell for the different applications can be done. It's a matter of what is the best trade-off involved. Commercial customer has very clear business financials and investment payback periods, so they know exactly the right product in the catalog that would best meet their needs. In the future, I guess I personally have little doubt that autonomous commercial electric vehicles will be part of our future. Could be very small cargo type transportation and or very large ones, but little doubt it's just a matter of time. So I appreciate your time and thank you very much.
Thank you, Bob. Maybe we can get our next speaker from General Motors is going to be virtual, so maybe we can get that set up and I can make the introductions in parallel. So
he's ready to go.
Are you with us?
Yeah, I'm with you. Hopefully you can hear me.
We can hear you very well. Thank you. So it's my great pleasure to introduce our third speaker this session, which is Andrew Orry, who's the engineering technical leader at General Motors. And his talk is going to be enabling customer choice in EVs with the Ultium platform. We've all heard a lot about the Ultium over the years, and we'd be very excited, Andrew, to hear updates and next steps.
Great. Yeah, hi everyone. This is a really great section to be a part of. I really appreciate the presentations from Oliver and Robert, and I learned a lot. My name is Andy Yowery. I'm the engineering technical leader for high voltage battery packs at General Motors, and I'm going to talk about GM's Ultium platform and how it has the flexibility to power a wide range of electric vehicles. Okay, there's 4 parts to my presentation. I'm going to take a minute to reflect on the state of electric vehicles in the industry and how things have evolved over the last few years. I'll also discuss how the Ultium platform is enabling customer choice by giving us the ability to build vehicles across different vehicle segments. Then I'm going to discuss how the platform gives us customer choice within a vehicle platform. And finally, I've got some thoughts on energy density benchmarking that falls somewhere in between the cell level and the pack level. But first, a quick video of Crab Walk. We launched the GMC Hummer EV earlier this year, and highlighted my career to get to crab walk that thing around Phoenix. Okay, so a look back. Looking at what GM said at AABC over the last 5 years, back in 2017, we were just launching the world's first long-range affordable EV, the Chevy Bolt EV. We were talking about the importance of getting battery cells at $100 per kilowatt hour or less as an important step for EV adoption. And we were just launching 50 kilowatt DC fast charge in the Bolt, which seemed pretty cool at the time. Now, 3 years ago, we talked about how we were designing a new EV platform to achieve our newly stated goals of 0 crashes, 0 emissions, and 0 congestion. We pointed out how we could afford to trade off some energy density and affirmed our support for $75 kilowatt hours as the low-cost fast charge target. And, with an eye towards crossovers and cars, we forecast that there would probably be widespread adoption of 150 kilowatt DC fast charge capability. Now, last year, we started sharing the details of our flexible modular Ultium platform, and we launched the world's first all-electric super truck, the GMC Hummer EV. And now with the focus on trucks, 350 kilowatt DC fast charge starts to look really important. Which brings us to today. I'm going to talk about how we're executing our rollout plan, and I'm going to show you how the Ultium platform supports that. I'll also note that we are continuing to engineer new models, and so we can develop EVs for everyone as we keep going forward. So the Ultium platform, it's a combination of batteries, motors, high voltage components, and software that are interchangeable, enabling different drive configurations and drive type. And that gives us the flexibility to give customers exactly what they want and helps us address customers' concerns about EVs that don't go far enough or don't charge fast enough or cost too much. So we actually engineered a new electric vehicle platform. In fact, 3 different styles of that platform shown here. And it's the modular design of the platform that's letting us quickly deploy cost-effective segment entries across a wide range of vehicles. And I want to show you the degree of choice that we're offering across these segments. So I'm actually going to cheat. I'm going to start with a non-Ultium vehicle first, 2 of them, in fact, the Bolt EV and the Bolt EUV. Those are the only 2 on this chart that are not based off of Ultium, but they are in the market today, and they're 2 of the best-selling EVs in the mid and the entry crossover space. Now, on the other end of the spectrum, last year we launched the Hummer EV, all-electric super truck. It is the longest range, most powerful, fastest charging EV truck on the road today. And leveraging components from the Hummer EV, we launched the BrightDrop Zevo 600 delivery van. It was the fastest program in GM history from concept to production, and it helps us decarbonize the fast-growing last-mile delivery commercial segment. So in the middle here, in the summer, we started deliveries of the Cadillac Lyriq. It's a true luxury crossover and just happens to be an amazing electric vehicle at the same time. In the full-size SUV space, GMC Hummer EV is going to offer an SUV alongside the SUT. It's got a shorter wheelbase for even better off-roading, and in the SUV form, it's got some interior space. The Chevy Blazer EV is going to add a larger and more expressive EV to the popular mid-crossover segment early next year. And vehicles like the Blazer EV are a great platform for us to add fleet volume. Here's an example of a police pursuit vehicle off the Blazer EV. Customers won't have to wait long to get the Chevy Equinox EV, which will join the Chevy showroom about a year from now. This is going to be one of the most affordable EVs built off the Ultium platform, and it's going to expand what customers can get in the entry segment because it's going to have available 300 miles of range and available all-wheel drive. The Ultium platform is the foundation for the fully autonomous Cruise Origin. This vehicle expands Cruise's fleet of autonomous vehicles, which are already permitted to offer and collect paid driverless rides in San Francisco. And now two of the vehicles that I'm most excited about are the GMC Sierra EV and the Chevy Silverado EV. These full-size trucks are new from the ground up, and I think they're going to really redefine what customers expect from an electric truck. And lastly, we've got our first low-roof EV will be the bespoke ultra-luxury Cadillac Celestiq. Each of these vehicles is individually commissioned and will be hand-built at the General Motors Tech Center right here in Warren, Michigan. And each of these vehicles uses the same cell. The cells will be built at 3 plants that are under construction here in the US right now, each plant capable of cranking out about 100 million cells per year. The first plant in Ohio is coming online right now. And each of these vehicles uses the same family of motors for massive economies of scale. So with just one cell and one family of motors, we've got vehicles across many popular and growing segments. And because we built in flexibility, each of these vehicles still delivers unique experiences, styling, and value to the customer while sharing a bunch of common components. Now, in the next section, I'm going to drill deeper into the Blazer and the Silverado and the Sierra to talk about how we get a lot of variation within a vehicle model. I think they both serve as really great examples for that. But briefly, I'll mention that that chart that I just showed is incomplete. It does not include all of the 30 new EVs we plan to launch globally by 2025. Now, I do want to stop for a second. Why is choice so important? You know, customers' preferences in vehicles have always varied and will continue to do so. And I like to think about the Chevy Camaro as an example. You can get a Camaro with a 2-liter turbo in a convertible, and you'll probably find that in the rental fleet at the airport. And on the other end of the spectrum, you can get a 6.2-liter V8 Camaro that you're going to find in enthusiast garages. And when we thought about what we could do with EVs, we thought we could do the same thing and have that same kind of flexibility and customer choice. And here's the thing, especially when you're trying to drive and grow EV adoption, the more options customers can choose from in an EV, the more likely they are to choose an EV. So if we offer more configurations, we meet more customers where they're at, and we sell more EVs. And lastly, you know, there is an element of why not? You know, you've already engineered the flexibility and you're offering it across vehicle segments. Well, why not offer it within a vehicle segment, within a vehicle model? You know, of course, this has to be balanced against complexity and engineering, inventory, calibrations, and stuff. But deployed thoughtfully, this is a really major benefit of the Ultium platform. So the Blazer EV is a great example of this variety and choice. It offers customers the choice of front-wheel drive or rear-wheel drive or 2 different all-wheel drive systems. And the electric Blazer SS will be available next spring. So I made up some customers to help talk through the different choices in the Blazer EV. Take this guy, for example. He just bought a Bolt EUV and he loves it. He's been living with 250 miles of range and realizes he really doesn't need any more than that. But he wants an affordable upgrade for his Bolt with more space and more expressive styling. So this customer's needs could really easily be met with an 8-module battery pack that coincidentally has the same range as his Bolt EUV. For customers that don't care about which axle is driven, or if they prefer front-wheel drive for its traction in the snow, the Blazer offers an elegant front-wheel drive system where all of the high-voltage components like the inverter and the onboard charging module, they're mounted directly to the drive unit. And if this customer's on a budget, he could opt for the 1LT trim on the Blazer EV. All right, another customer. This customer is driving a gas Blazer RS all-wheel drive, and this person's ready to try an EV. The customer's decided she wants all-wheel drive to get up her snowy driveway, and she's never had an EV, so range anxiety is a real thing. Well, with almost 300 miles of range, a 10-module battery pack would offer enough range to get over this first-time buyer's range anxiety. And the Blazer EV is offered with 2 different all-wheel drive systems. This customer would be perfect for the E all-wheel drive system, where we supplement the primary front drive unit with an efficient, lightweight, and affordable E all-wheel drive motor on the rear axle for a combined 295 horsepower, and you can get this in the Blazer EV RS. Okay, now we've got a customer who lives in sunny California and couldn't care less about all-wheel drive for traction. This customer likes to pack her dogs in the back and go for long drives on the Pacific Coast Highway. So for this customer, a 12-module battery pack would be great. Could get up to 320 miles of range on a charge, DC fast charging at up to 190 kilowatts. And with the large rear-wheel drive motor replacing the front motor, this customer is going to get 342 horsepower and that sporty driving experience you get from powering the rear wheels. This is another configuration that you can get in the Blazer EV RS. Okay, and lastly, we've got an existing EV customer. He already drives an EV and it's a fast one. His lease is up and he wants to get into a new EV with the latest tech and true hands-free driving. Well, this customer could also go for that 12-module battery pack with 290 miles of range, and could go for the performance all-wheel drive system, where we put the rear wheel motor and the front motor in at the same time, the big ones. It's like having a V6 on the front axle and a V8 on the rear axle for a combined 550 horsepower. And that makes this the first Chevy EV worth of an SS badge, and it comes with Super Cruise hands-free driving standard. So now this is only some of the diversity of options available in this one vehicle model. The whole point is our strategy is to offer more trim choices, more drive options, and more range options. The goal is to get more EV customers. Moving on to trucks. I think we're going to look back at 2022 as the tipping point for EVs. They're on track to set a record this year. In June, electric vehicles were 6.5% of the market in the United States, a new record. But perhaps the biggest sign of EVs going mainstream is the newfound popularity and optimism around something that was almost unthinkable a few years ago, EV trucks. Multiple EV trucks went on sale in 2021 and 2022, and we think we have the best EV trucks to offer here. Our electric trucks are built differently, but they still offer the capability and durability you'd expect in a truck. Traditionally, trucks are built with a body on top of a frame. And generally, if you want good structure, you want nice, straight structural elements that flows from one end of the vehicle to the other, and you want to avoid sharp bends in the structure that cause stress risers and add mass, where you have to add mass for reinforcements and so on. But there's not enough space left between traditional truck frame rails for a very long-range, highly capable truck. You can see the interference here is quite obvious. So we started over. Our system integrates the body, the frame, and the battery structurally and gives us enough space to fit enough battery that trucks like the Silverado EV can go 400 miles on a single charge. But I'm showing you on this screen, though, we did introduce some structural discontinuities at the front and back of the pack, and they're quite pronounced in this view. So how do we fix that? Well, what we did is we changed our perspective literally. It's not just about having good geometry in the top-down view. You can compensate if in the side view you have linear and planar geometry from the front bumper to the rear, over the pack and under the pack, and then you bolt all of it together around the perimeter of the pack and through the center of the pack. Doing that gives you an incredibly strong and stiff platform with a lot of the mass and structure centered down low, so you can deliver the capability people expect out of a truck, like being able to tow 20,000 pounds. So Silverado EV, great example of how we're offering a lot of choice to customers in the truck segment. I mentioned range of 400 miles, towing up to 20,000 pounds with a max trailering package offered after launch. Also, joining the GMC joining the Silverado is the Sierra EV. It's launching in the popular Denali trim, and it'll be actually much more different than the Silverado. If you compare the Silverado EV and the Sierra EV, they share fewer body panels and less components on the interior than today's gas counterparts. So very unique vehicles in terms of styling, and even though they share a lot underneath. So couple customers again. Let's say we've got a customer that runs a commercial fleet and wants an EV work truck to lower operating costs and tows heavy loads around town primarily. This customer could opt for a 16-module battery pack. Internally, it's wired like two 8-module battery packs in parallel. After launch, we're going to have a max towing package that can tow up to 20,000 pounds here. And this customer would be perfect for a Silverado EV work truck, which was engineered exactly with this customer in mind. Customer B loves off-roading. She wants to keep off-roading in the EV age. And so this customer could opt for a lighter, less expensive 20-module battery pack to save a little cost and weight. Now, I want to be clear, we have not announced the range of the 20-module battery packs, but with our larger packs offering 400 miles of range, this smaller pack should be comfortably around or probably over 300 miles of range. A dual motor all-wheel drive system with locking differentials will give this truck the traction it needs for driving off-road. And this customer will be excited to find that the same AT4 trim she's coming from in her Canyon is offered in the Sierra EV. It's got a factory lift kit and skid plates and crab walk and underbody cameras to see where she's placing her tires. Okay. Customer C is tired of dealing with blackouts. The US has more blackouts than any other developed country, and we're all starting to think differently about how we power our homes and the grid. And this customer read on the internet about some electrified trucks saving the day down in Texas last year and thinks that is a great idea. So this customer might want to opt for a 24-module battery pack. And when properly equipped, this pack has the ability to keep the lights on in your home for up to 21 days following a power outage. This customer happens to used to own a Chevy Avalanche, thinks the Silverado EV kind of looks like one, and goes for the Silverado over the Sierra. And finally, customer D loves nature and clean air, and but she tows a travel trailer, and she'd like to tow that trailer to the national parks to see all that nature. She's currently driving a Denali Ultimate, a Sierra Denali Ultimate, and she's going to check all the boxes when she orders her next truck. This customer could opt for a 24-module pack with 400 miles of range. And now, hey, we know that when you're towing, range is going to go down, and that's why it's so important that this platform offers 800-volt, 350 kilowatt DC fast charging, because if you have to charge more often while you're towing, you want to be able to charge faster. The 754 horsepower from the dual motor all-wheel drive system will have no problem with the towing, and this customer can stay with the Denali brand and get it loaded with options, including hands-free Super Cruise driving, which functions while trailering. So we think the Ultium platform gives us the flexibility we need to meet work truck customers on one end and premium truck buyers on the other end, with lots of price points in between. And with all these options like four-wheel steering for tighter turns or crab walk, offboard power, V2X, we've got great options to get more people into EV trucks, which is more EV customers overall, which is what we're all trying to do. That's how we take batteries and motors from a Hummer EV, and we use them in a Silverado EV. We take motors from a Silverado EV, and we use them in a Cadillac Lyriq, and we use motors and batteries from a Lyriq, and we use them in a Chevrolet Blazer EV, all with massive economies of scale. I'm going to wrap up quick talking about energy density. It's a topic that's near and dear to all of our heart. You know, it sounds simple, right? But it's not. Even if you could get people to agree on what dimensions and energy should be used to calculate the energy of a cell sitting on the table in front of you, it's not really what's most important to the customer. There's a lot of transfer functions that chip away at that energy density as you integrate cells into a pack. And that's really what's important. So as you put cells into a stack, you lose some energy density based on how much they expand and contract and things like that. As you wrap a module around those cells, you lose some energy density for that structure and cooling. And when you integrate that module into a pack, you have to have some height above and below it to enclose that module in a pack. Different OEMs take different approaches here. Some have smaller modules in a bigger pack. Some have bigger modules in a pack with less overhead. It's all just about functional allocation. And then there's a module array where you lose some more energy by interspersing structure in there. This is where the hot topic today is cell to pack, because you don't lose anything if you just have one big block of cells. And then finally, you've got the pack array where you lose some more energy density. So if you're starting out at like 400 to 750 watt hours per liter at a cell, you're probably going to end up like 200 to 275 watt hours per liter at a pack level. I'll make it brief. All those transfer functions are really important, and they change how it integrates. And I want to propose and ask you to think about what I've found is that if you focusing on the pack energy density is not super useful because we all make very different choices about what parts we put in a pack and what parts we don't put in a pack. There's some optional choices, but you have to have energy. And so I think if you focused on what we would call a module array, you just go corner to corner, or you make a simplified shape if it's not rectangular of what your modules are, extrude it to the top and bottom of your pack extremities, calculate your watt hours per liter, and what you'll find is that's really a good value for comparing your designs to your competitors and comparing the different designs you might be developing. All right, so I'd advocate for using the module array energy density to normalize benchmarking across disparate designs. We've got this flexible platform that helps us get EVs out by 2025, and with a common set of components, we're still getting across a bunch of vehicle segments. Bottom line, when customers have more EV choices, more customers choose EVs, and that's good for everyone. So thank you very much, and I'm looking forward to the Q&A.
Thank you, Andy. Excellent presentation. If I could ask Oliver and Bob to please come up and join the panel, and Andy, stand by. We've got questions. We'll be looking forward to your questions. If you've got one, raise your hand or stand up. Please give your name and your affiliation, and also, because we've got virtual and in-person, please identify clearly who your question is being addressed to. So maybe let me get things started. Maybe Oliver, I've heard regulation in the industry for a long time, especially CAFE standards and California Air Resources Board. And you talked a lot about regulations, but I hear that there's going to be regulations regarding the recycle of batteries. And I wonder what consequences or implications there might be.
Okay, yeah, that's also an area that's in development and more in Europe than say over here, but that will probably become a good template for the rest of the world in many ways. The notion there is that just as when you think about a traditional lead acid battery, which is one of the most recyclable commodities in the world, these batteries have the possibility to be the same way. And so there's the percent that are actually recovered for recyclability is one of the parameters that the regulators would want to put in. So that's one of the purposes of the battery passport in the European battery regulation. You can anticipate something similar here, so you can get an idea of how much battery can be recovered. And then the more interesting one, I think, of that, let's assume that we're very successful there, is the regulations will extend to the point of the percent of material going into a battery that is recycled from older batteries. This is unfolding through this decade with certain numbers. In particular, it's mainly targeted around nickel and cobalt, although we anticipate lithium will probably start getting into the fray there as well. But those are being regulated in the sense of what percent need to go in there. And that's actually going to end up with some rather interesting results too, whether that's even feasible, because it's so sensitive and dependent upon the life of the batteries, which was one of the main topics I was bringing about.
Thank you. Raise your hand if you've got questions. We'll get you a microphone. Bob, in the meantime, a question for you. You gave us a lot of optionality and a lot of choices that Ford can make, but maybe let me ask the question differently. What gives you the most headache or heartburn? What are your biggest concerns? Is it raw material, supply chain, regulation, costs? What drives you guys? What keeps you guys awake at night?
I think if you talk to different people within Ford, you'll get to the gamut of different concerns, right? The purchasing organization, they're very concerned about the supply chain, securing demand not only for the near term but for the far term. Now, I tend to come from the engineering team, so I'm focused on the product itself. And ever since we started making electrified vehicles, batteries, it's always been the quality that's been the thing that's been of greatest concern. Battery life, 15 years ago was kind of the biggest question amongst potential customers. Is the battery going to last long enough? And I think through time we've demonstrated good reliability. For me, one of my most fulfilling instances was I happened to be in New York City in 2017, I went over to Madison Square Garden and I exited the subway and up into the street level, and I saw the street just filled with yellow taxi cabs. And in 2017, about 30% of those taxi cabs were Escape hybrids. And we had stopped production of those vehicles 5 years prior to that. So, I felt very good that we had made a very durable product, and that's just maintaining that level of quality, I think, is what we always have to worry about. It's not just good enough to launch the product. You have to worry for the life of the vehicle. Is it going to continue to be a good product? So that's the thing that I'd say is utmost, and manufacturing quality and good long life designs.
I heard you had nickel metal hydride taxis in New York that went over 1 million miles.
I hadn't heard that, but I know that there's many of them exceeded 250,000 miles. I hadn't heard about the 1 million mile one, but when we launched it, I knew we'd have a good product.
Thank you. Question over here.
My name's Jim Duchek with Osaikas, and this is a question for Bob. At the end of your presentation, you made a reference to autonomous and self-driving vehicles. Are there attributes of the electric powertrain versus the internal combustion powertrain that would be advantageous or disadvantageous for adoption of autonomous and self-driving vehicles?
Well, I think you have a lot of the components that are needed for autonomous vehicles already in an electrified vehicle. So even our self-driving, or even our tip vehicles that are on the road today have a lot of autonomous features in them. And even a decade ago when we had I had like a Fusion hybrid, 10 years ago, just the adaptive cruise control, I could see that there's a lot of autonomous features. So a lot of that, I think, is already in place as far as the needs for autonomous vehicles. Internal combustion engine vehicles can certainly do that. And I think the first implementations that Ford was looking at a few years ago was for using hybrid vehicles. So, that had an internal combustion engine, and a battery. So either can be done. It's just that there's a lot of the components, I say, are already there in the vehicle for a electrified vehicle. There's a much larger consumption of power to support all of the computing and monitoring and that sort of thing. So that's, I think, one of the areas of focus is to reduce the consumption of power so that you can have autonomous vehicles that don't consume as much energy for, just the autonomous aspects of it.
Thank you.
Hey, Bob, I would add two other things briefly to that. Just that the response time with electric motors can really help the response time for the whole compute system and making its choices and reacting. And also, EVs have autonomous vehicles solve one of the problems with EVs, which is uncertainty and charging and routes, because most autonomous vehicles are operated by a fleet on a prescribed, or at least a route that can be approved or not approved and charged centrally. So they're really well aligned with fleet management, and EVs go well with fleets.
Andy, a question for you. I was impressed and amazed with the number of options that you were offering, and you raised a couple of topics. One was range anxiety, and you kind of implied a little bit about grid reliability and things like this. So a few years ago, one of the options that GM was really touting that was exciting was the plug-in hybrid. And I guess I wonder if that's off the table, on the table, or kind of little distraction. What's the present thinking on plug-in hybrid or plug-in electric vehicle at General Motors?
Yeah, I had one of the first Chevrolet Volt EVs. I actually got baby pictures of it while it was running down the assembly line. The Volt was a fantastic car, and I loved it. At this point, though, we want to take we want to dedicate all of our resources to engineering electric vehicles, which is the end where we see ourselves in the end. And I would also just reflect on if you look at the cost structure of a plug-in hybrid, both the cells themselves and the fact that you've got the gas powertrain and all of the ancillary items, the costs add up really quickly. As many of you know, like the cost of a PHEV cell, it's not $100 per kilowatt hour for a plug-in hybrid cell. They're more expensive than that. You've got a lot more layers, a lot thinner coatings, things like that. So the costs don't make sense, and our choice about where to allocate our resources is to put our chips on full BEVs for the long run.
Thank you. Question over here.
Yeah, my name is Mike Karachi. I'm with Ascend Elements now. Andy and maybe Bob, you can answer. You guys have lots of options now with lots of EVs. It looks like, Andy, you put together some example customers, and maybe Bob will have to also kind of figure out what's the ways you're going to figure out how to have your dealerships and people who are getting in touch with the customers and explaining to them what kind of vehicles are best for them.
I can go quick on that first, Bob. We actually, so obviously educating our dealer network is really important. We fly them around the country and talk to our dealers to educate them about the EVs. But one thing that we just started, which is actually really unique, just down the road from me, we bought an old Target that was shut down, and we gutted the place and we turned it into a studio. And it's a live, it's like a live auto show that runs every day, and we have product specialists in there, and they've got steady cams or selfie sticks, and they'll walk around talking to you one-on-one on the internet. As a customer, you can dial in, talk to them. They'll show you the vehicle that you're interested in, and they're trained and they know all of the information that they need to know to help you transition into an EV. So it's kind of like a phone a friend for a dealer, and it's who doesn't know enough about EVs. And it's also a way to learn about EVs while you're sitting on your couch in your pajamas. We call it EV Live.
Thank you. Bob, did you want to add anything to that?
No, I don't think we have quite as extensive a program as that at Ford, but I'd say as Andy mentioned, the training of the dealers is very important. And from time to time, we have had customer clinics that I'd say at Ford, we probably don't do enough of them, to have customers have the opportunity to come and see and ask questions. On the commercial side, there's a Ford Pro. One of their ways of operation is to get with each of the commercial customers before they purchase, to go over their specific needs, to figure out, with the customer, the Ford Pro team, what would be the right fit for their commercial needs.
Thank you. Oliver, one question that I had for you was, you showed the nice supply chain from raw materials and regulation and the cars, and you talked about at some point secondary life of the battery, second use. And this tends to be somewhat provocative, because I've heard we need to have second life to justify the cost and all of that. But then I've heard other people talk about, wait a minute, safety issues relating to second life. I guess what's the thought of Stellantis on how do you think of second life of the battery?
We do think that second life has a place in certain areas. The only thing is, the techno-economics has a little bit of an open question. I mentioned before about the regulations that are going to come out with recycling, which may fly in some ways in the face of secondary life, as well, in some cases. If we were supposed to hit these targets early, we certainly have no time for secondary life. But the basic concept is there's certain general purpose uses that make sense for second use. I don't think it's going to be 10 years as indicated there. What you're probably going to find out is that when you're talking about batteries near the end of their useful lives that were designed for cars, they're not being designed for a secondary use. And so they're going to fail in a myriad of ways that no one was anticipating. So any kind of smart implementation is going to have to be able to detect those and allow you to swap components in and out rather quickly. That's going to drive the techno-economics of any kind of secondary use. I don't think it's something that there's going to be any one simple solution for. The big debate there is whether you use complete packs or you break them down to the module level. I think you saw in some instances, like in the GM case, where it's a very, very modular system, it actually benefits that. I'm not allowed to speak about our systems yet, for our new platforms, but our current platforms actually would be a little bit more inclined, to reuse the entire pack.
Thank you. Got a question for all three of you, whoever wants to try to tackle this, and all of you can try if you'd like. We had this summer, Governor Newsom telling Californians not to take their electric vehicles and plug them in because the grid couldn't handle it. And a lot of the talks are also about fast charging, which would even put more stress on the grid. So what's the automotive company message to the consumers who, are not range anxiety, but how about grid anxiety?
Well, I'll start this one. I think we're in a new world, and we can't just live in a bubble as an auto OEM. The answer to that is grid storage, and it's not saying that we as auto OEMs are going to be in grid storage, but we're complementary with the utility, with the infrastructure, and infrastructure is absolutely essential for electrification. So, in that regards, we have to be very sensitive to the wants and needs of the infrastructure as well, and support that. Advocate for it because it does help for reliability use of our vehicles, as is for reliability of energy and power provision.
Bob, Andy, you want to add anything, or you want to leave that one alone?
No, I totally agree that it's good that people are recognizing risks there, and we are an important stakeholder in all of this. But we want to flip it on the head and think about electric vehicles as an opportunity to improve grid stability with V2X. Now, you'd have to have a lot of EVs. You'd have to have a lot of folks opt in for the V2X functionality and have properly equipped charging infrastructure. But it's totally doable to have vehicles act as a virtual power plant. And you can have a situation where the customer that needs to fast charge to continue their trip, great, go ahead and do it. And the other people who opted in and their vehicle is sitting there with extra storage available, that can be put onto the grid to help supplement what's on the grid. Also, speaking directly to the issue of grid energy storage, that's one area we are getting into. So we've got a new division called GM Energy, and they're directly building commercial and home stationary energy storage products.
Yeah, we actually have fleets in Europe right now, both in place and being deployed, that exactly demonstrate this, the entire V2G and V2X types of functionality. Aggregation, which is one of the key terms. I gave you a glossary of terms. There's another one for you, but that's really what the grid side uses. And definitely the vehicles can become certainly part of it. And as I indicated, regulations are reflecting the fact that they expect vehicles to be used this way.
Bob, you want to add anything to the topic?
No, I think everything is correct. But as was mentioned earlier today, the electric vehicles only account for maybe 6 to 8% of vehicles, and so as they get up to 30, 40, 50, 60%, the amount of energy consumption is going to be substantially larger. And as Oliver was mentioning, having on-site storage, for example, wanting to get to faster and faster DC fast charging ups the amount of power consumption as well. So having on-site storage to be able to support and not put as much of a drain on the entire grid, and as Andy was mentioning, having the if you will, the whole gamut of electrified vehicles that are unplugged to as V2X to support the issue. It's going to certainly help, but it's still pretty big item that needs to be dealt with as electrification becomes more and more prevalent.
Yeah,
thank you very
this
much.
is such a fun topic. I think there's one other thing, because we jumped to the most complicated solution, which was bidirectional power flow. Just simply managed charging at the start is something that can work. So Governor Newsom's request to not charge, that can be automated. So I think there's lots of opportunity to solve this for the grid.
I think we're going to close the session now. You can meet our participants in the coffee break, which will start. We'll resume the second session at 4:10 p.m. And there's going to be a continuation of the automotive with Toyota and Volvo, and also some exciting materials developments. So please join me in thanking our speakers for an excellent session.
Thanks, everyone.
That was good.
I used to tell Toyota a joke. Your slides will be plugged in already. The Good afternoon again. We'll let few people drifting in, so I'll give it a second before we start the second session. My name is Mike Fitsenko. I'm the Executive Chairman of Scion Power, and I'll be chairing the meeting today. I won't bore you with my intro from those of you who were here before, but I will say I think I attended my first battery conference back in 1987, and AABC has been one of the preeminent events. And one of the things that I've been amazed with and pleased by was the in-person attendance. I guess Craig tells me that there were 1,300 people for this conference, and a year ago when we were doing things virtually and all of that, it's really fantastic to be back here in person. And the conference agenda, the exhibition, these things couldn't be more impressive. The speakers that we've had during the first 2 days have been fantastic. And you just in the session right before, we heard from the traditional big three U.S. automakers, General Motors, Ford, and Stellantis. We're going to be continuing that discussion. Our first two speakers this afternoon are going to be from Toyota and from Volvo. Then we're going to be hearing from software company Voltaic, and there's all kinds of companies that are getting involved, and we're hearing about have new innovative battery pack designs, charger algorithms, life predictions, and end uses, and all this kind of thing. And our closing speaker this afternoon will be Keenan Sahin with Chemex Power. When you hear about cobalt being the most scarce and the most precious of all the materials that go into a battery, these guys have come up with an innovative way to use less cobalt, get better performance, and have cost reduction. So it's really kind of an amazing and really great group of speakers that we have, and thank you for sticking around for this next session. Our first speaker this session will be Dan McLaughlin. He's principal engineer from Toyota, and he's going to be talking to us about HV battery integration for Class 8 fuel cell trucks. Dan.
Thank you for having me. So I'd like to talk about how to integrate the high voltage battery into the heavy duty fuel cell, which is a little bit different than some of the previous talks that were more about cell specific, but this is more application specific. So Toyota is looking at expanding its core technology. So one of those core technologies is fuel cell. So maybe everyone here knows of the Toyota Mirai. So it's one of the first passenger vehicles that are fuel cell. So leveraging that energy source, we're looking at implementing that into different applications. So for example, we did a megawatt fuel cell stationary system study with NREL, marine propulsion systems, and then also zero emission freight vehicles. That study has been done with the ZANZEF project through CARB. So for this study, focusing mainly on the zero emission freight vehicles, the real question is, why are we looking at this? So right now, there's an immediate need or short-term future for zero emission freight vehicles. So locally in the Port of Los Angeles, Port of Long Beach, there's their emissions reduction plan. So in the short term, they're looking at removing all of their drayage trucks from high emission vehicle to low or near zero emission vehicles. So in the future, there'll be tariffs on the diesel trucks going into the port, and in the future, they're not going to be able to have any new registrations of any diesel trucks. So right there, there's an immediate need for either BEV heavy-duty drayage trucks or fuel cell drayage trucks. And then more statewide, CARB also has their overall target of creating all heavy-duty vehicles from drayage and then also long-haul trucks to zero emission in the short term. And in addition to that, there's also other states that are following along, such as Colorado, many states in the Northeast, and all the way up the West Coast as well. So what's the role of the fuel cell in the heavy-duty market? So compared to passenger vehicle, there's a little bit more of a need for a fuel cell than with the smaller cars. So for example, these two plots here are from an NREL study, and basically it shows the mass that a vehicle can pull. So the comparison here is What's a comparable to a diesel vehicle? So it has the same amount of power and performance, so it has the same 0 to 60 acceleration time. And they're both limited by the 80,000-pound gross vehicle weight. So just comparing the mass of the powertrain to have those same performance standards as the current diesel trucks. In the current 2020 status, the mass of the BEV powertrain is much heavier than the fuel cell powertrain, specifically considering the 500-mile range case. So because of this, the fuel cell vehicle is able to pull roughly 17% more load if you're at a load limited case compared to a volume limited case. As you can see with the trend, the load differential will decrease at lower masses, which is more similar to, or lower distances, which is more similar to the drayage, which would be less than 300 miles, so that comes closer to a parity. But you can see as you get to long haul and medium haul trucks, there's a bigger advantage for the fuel cells. And then moving out to 2050, the gap decreases. This is mainly due to maturity of the market, improvements in technology, battery energy density improvements. So that gap from 17% will just change down to 7%. But with even that gap decreasing, there's still other advantages to the fuel cell compared to the BEV trucks. So for example, the faster refueling times, right now the fuel cells can refuel about 6 times faster with a target of 15 to 20 minutes for a full fill of the hydrogen tanks, compared to most companies advertising roughly 90 minutes for a fast charge for the BEV. And then in general, if right now we're limited on our lithium ion capacity, so the hydrogen trucks are able to operate on a smaller battery size. So considering the same amount of battery availability, you could build many more hydrogen trucks than BEV trucks and get to the same xEV total target with greenhouse gas emissions. So this is kind of the landscape of the development of both BEV and fuel cell trucks. So on the top, it shows the status of the BEV, and the bottom, the fuel cells. And then left to right, it shows status of testing, announced production, and then production and taking orders. So from here, you can see the BEV is ahead of the fuel cell, and each of the trucks on the chart basically show the position of most of the major OEs in the heavy-duty market. So most of the BEV, or most of the heavy-duty truck OEs are already in production taking orders, with maybe a couple lagging behind that haven't announced their production yet. Whereas none of the fuel cells have been announced for each of the OEs, but most of them have announced some sort of testing, ongoing or trial programs with customers. So getting to the difference for how the battery is used differently in the BEV versus fuel cell application. Here we have a chart showing from top to bottom the vehicle speed profile, battery power usage, and battery energy delta. So you can consider the bottom one as like a state of charge difference. So considering the same vehicle duty cycle, you can see the difference in the battery power. So the BEV will have a higher charge and discharge power because it has to power the entire motor for the system. So there's not the supplemental fuel cell power in that application that helps with it as well. And then you're able to get more regenerative energy out of the system because the battery is bigger, so it has effectively a lower C rate going into the system. So you'll be able to recapture more energy from driving and braking. But at the bottom, you can see that the amount of energy delta from the starting condition for the fuel cell is much smaller than the battery electric vehicle. So you're able to use a much smaller energy capacity battery than the BEV condition. So for our study, this is how we would integrate the fuel cell powertrain into a truck. So the top photo shows how you integrate it into the vehicle itself. So we put the fuel cell stack where the traditional diesel engine goes, and then put the battery pack underneath the cab. And behind the cab, there's a hydrogen cabinet. And then rear of the cab, there's the entire e-drivetrain, so the motor, inverter, axle assembly. And then down below is an electrical system diagram, which shows that architecture where the hydrogen goes to the fuel cell, that electricity is converted on the DC-DC converter, and then in parallel with the hydrogen battery or the high voltage battery, and then both of those go to the motor and the auxiliary loads of the truck. So for the use condition of the battery pack, it's used in both discharge and charge. So on discharge, it mainly is a transient power buffer. It also provides supplemental energy to the system. So if you have peak acceleration that's higher than the steady state power discharge of the fuel cell, the battery can help there. And then additionally, it needs to power the auxiliaries of the fuel, such as the air pumps, the hydrogen pumps that start up before that power can come from the fuel cell itself. Additionally, if your battery is large enough, you can also have an EV mode, which can be useful in different situations as well. On the charge side, it helps with the regenerative braking to improve the overall fuel efficiency of the truck. And then also as a transient power buffer, for example, when you're shifting and you need to slow down the motor, you need to absorb that energy. So this is how we went about defining the duty cycles for the battery. So first we went to NREL, and they have their database of different drive cycles. So they have a few of them for the drayage operations. So with that, we combine that with our 1D simulation tool. So we developed this simulation tool inside Toyota mainly for the passenger vehicle market, basically to have a good simulation for the Mirai passenger vehicle. And then with that, we are able to convert all the necessary parameters to the heavy duty market. So updating the road load, wind resistance of the vehicle parameters, but maintaining the key fundamentals of our fuel cell system and having that accurate prediction. So since we have the accurate prediction of our fuel cell technology, we're able to extract out what the battery duty cycle should be, since it's already integrated with our software in the loop system. That's our power split between the two different technologies or fuel sources. And then with that, we're able to output this battery duty cycle. So for this first trial run through the sim, we did an ideal battery pack, which means we gave it unlimited energy and unlimited power, just to see exactly what the fuel cell system or the vehicle wanted from the battery itself. From there, we are able to go through a few different routes, and then we were able to summarize by what route was requiring for energy and power for both charge and discharge. Since we are looking mainly through the port applications, this is a map here on the side that shows the different areas and what the requirement was for energy. So based on the geography of the region, everything that was coastal was low energy route. And then once you got further towards the inland empire, you needed more energy. And then once into the red area, which is more mountainous area, it required a lot more energy. So roughly 7 times than the yellow area. So once we were able to cover this radar chart, we were able to see the entire range of what we wanted to cover for the battery operation. However, what we found was what was required for the battery in the optimal situation wasn't necessarily realistic. Basically, the regenerative energy was supposed to be roughly 2C on charge, which didn't really make sense with the type of technology that was available for the battery at the time, for being able to maintain the target durability that we were looking for. In order to gain that regenerative energy, we could have increased the battery size. So based off roughly the cost estimate of 70% of the battery being the cells and the rest of it being the other auxiliary systems, we probably saved 60% of the cost by not deciding to increase the battery pack and optimize for the overall vehicle system. So we wanted to optimize the battery mass and the battery cost. And with that, we gave up a little bit of regenerative energy and a little bit of fuel economy that we could have achieved with a larger battery pack system. So once we had this final specification for the battery pack, we were able to have all of the requirements together and decide how we wanted to define the supply chain. So Toyota ourselves, we work on hybrid vehicles, battery electric vehicles. We have the possibility and the capability to design battery packs in-house ourselves. And then additionally, we looked at other companies, both existing designs and then also having them make custom designs for us. So at this point, it really depended on what our priorities were for our next direction for how we wanted to proceed. Since we are working on this short-term project related to the port, we wanted to optimize our resources and time. So we went with an existing design from an outside supplier. And then with this decision, our battery pack electrical architecture was decided and basically our cell format by what was available from that supplier. So from this point, we basically went from a top-down approach for our systems engineering to a top-up. So with this, what this means is the battery was being defined by what the truck required, but now since we decided the supplier was going to give us our battery pack, the limitations of that battery pack was going to infect the vehicle in some way. But on this radar chart here in the bottom corner, you're able to see that we are able to gain a lot of time. So roughly 50% development time was saved, as opposed to a little bit of performance was lost. So overall, for the benefit of the program, it was better to go with this option than design a custom battery pack that might have had a little bit better performance or a little bit better cost in the long run. Now we defined the battery pack system. We needed to confirm that we met all of the remaining specifications. So with that size and cell format being decided, we needed to go through a couple different cells and see what was the best for the application, and then go back and double check that drive performance versus the battery durability target that we had. So we went ahead and did some cell cycling to confirm the battery pack durability, running the different duty cycles that we developed in the earlier stages. So looking at what most cell suppliers supply in their data sheet, it's mostly CC or CV cycling. However, you can see that the chart on the left shows the CC-CV cycling is much different than the duty cycle, which is the top center photo. So the CC-CV is good for comparing some aspects of different cells together as a standard, but it's not really relevant to what the battery pack in actual usage looks like. So in the center photo, you can see the battery pack energy delta throughout the cycle is made of many small cycles, so it's not very equivalent to going full charge, full discharge, which has different stress factors in the battery related to high voltage, low voltage, or big state of charge swings. So with this, we went ahead and did cell cycle testing. So we looked at 3 different cells specifically. This was mainly driven by what was available in the market. So we also dealt with some of the issues of supply constraints. So some suppliers were willing to talk to us, some suppliers weren't willing to talk to us. And then in that format, there was a few cells that were able on the data sheet to perform our target duty cycle, but we wanted to confirm that they weren't over-promising and were able to keep that correct durability that we required for our system. So we looked at the cells A, B, and C. They had slightly different capacities and slightly different powers. So when we ran the duty cycle, the target wasn't to keep the duty cycle the same for the cell itself, but for the vehicle, because the vehicle performance is the most important thing. So for example, the cell that had a higher energy didn't have to do as much power because it had the energy in storage already for the vehicle in case it needed it for a discharge event. However, the cell that had less capacity, it would be required to do more regenerative energy to maintain that fuel economy target. So the charts on the right show the test results we had with our materials engineering division. So we did the cell testing in their lab. So the red cell is cell C, the green cell cell B, and the blue cell cell A. So running roughly the same duty cycle, you can see there's a big difference in durability. And this just shows that even though the cells on the data sheet can do the same duty cycle, over time there will be performance drop-off. So we wanted to decide what was best in the long term for us. Looking at cell C, there was a lot bigger drop-off at the initial cycles. So we decided to reduce the power just to see how much more durability we could get out of that cell. So once we reduced the power, you can see that the durability did improve, but it was still far off from the other 2 cells that we looked at. So at the end of the day, we decided to prioritize cell A as our primary path going forward, but still considering the other 2 cells as potentially for secondary sourcing if that's required in the future. So in summary, we were able to define the battery cell or the cell duty cycle for the fuel cell. We showed that the duty cycle is quite different because there's additional energy source as opposed to the BEV where the battery's providing the energy for the entire vehicle. We were able to get the duty cycles from NREL and other real-world driving patterns. For example, when we went through the ZANZEF project, we were able to increase the cycles and the different routes to real-world application that we were using with our Toyota logistics systems, and then also the port partners that we were working with. And then with those routes, we were able to go through our simulation software that was developed with our fuel cell application group and passenger vehicle, and then develop the ideal battery duty cycle. And then we were able to test multiple cells to confirm which cell had the best performance for our application, and then move forward into real-world driving and testing situations. In the future, we do need to improve our development cycle. So for example, the vehicle model cycles might not line up with the battery life cycles, since the battery life cycles and development cycles are much shorter. So we'll need to leverage the data we developed with the testing of the other 3 cells through different software applications that either we're developing inside our Toyota research group or other companies in order to faster validate other cells in the future. Thank you very much.
Thank you, Dan. I'd like to ask our next speaker to come up, Anna Axelson from Volvo. Anna is the head of battery industrialization and logistics at Volvo, and will be talking today about accelerating the Volvo Group's electrification and sustainability journey. Anna.
Good afternoon, everyone. I hope you're enjoying today so far, especially with the beautiful sunset. And I did hear that Santa is due to arrive on the beach fairly soon. But instead of running off to go meet Santa, hopefully you'll stick around to hear the exciting things taking place at Volvo. So let's jump straight in. So as mentioned, I am Anna Axelson. I am in charge of leading the Battery Industrialization and Logistics Forum for North America. So as part, I am part of the Volvo Energy Group, which is under the Volvo Group umbrella. So in September last year, the decision was taken within Volvo Group to launch a new business area, hence Volvo Energy. So what Volvo Energy will do is we will have a mission to focus on the fundamentals, breakthroughs of accelerating electrification and driving circularity for a better tomorrow. So if you think about this, what is so key in that concept? Why do we need to accelerate electrification? I'm sure you're all very familiar of, sorry? True, there is definitely a climate impact that has taken place. You're absolutely correct. And with the Volvo Group, I'm sure you're very familiar that we very strongly believe in safety and environmental care. So that is our commitment to driving this electrification and circularity model. So the reason why we're doing this is we want to future-proof the Volvo Group. Today, globally, we have 12 business areas. Within North America, we have 5: Volvo Truck, Mack Truck, Volvo Construction Equipment, Volvo Penta, and Volvo Bus. So Volvo Energy will do everything possible to support those 5 business areas in North America, as well as the remaining business areas globally in their electrification sales. So Volvo, just like many of you, are fully committed to the 2050 target levels based off of the Paris Agreement. So we are doing everything possible to ensure that we will meet those targets. But we're not waiting. As you can see, even in 2030, we are taking the initiative to start reducing the emissions by 40% for trucks and buses. In 2040, we will stop the sales of all ICE vehicles, and we will be 100% fossil-free for new vehicles as of 2040. So thinking about this, the target's 2050. Why 2040? Well, what we want to do is we want to make sure that we utilize that 10-year opportunity to reduce the current ICE engine or vehicles that are currently on the market during that time frame. And what we will do is we will support them with biofuel at the same time of ramping up our electrification model. So 2050 is our target date, and we are doing everything possible to ensure we meet that target. So now let's jump into a little bit of what is Volvo Energy's responsibility. So as mentioned, my responsibility lies for North America, the North American region, is to lead the battery industrialization and logistics flows. So Volvo Energy is focused in 3 top areas: first life, second life, and enablers. So what does that mean? So first life is any Volvo vehicle that rolls off the production line and is handed over to that super excited customer that just received that Volvo vehicle, that we will actively monitor that battery while it's on board of that vehicle. We will not only monitor the battery, we will collect the data, analyze the data, and optimize it to ensure that that battery is running at the highest performance levels possible. We will also use that information to be very proactive and having a conversation with our customer if we need to, because we start to see some concerns with that potential battery. Instead of waiting, we will proactively go and approach that customer to resolve any issue. So not only will we monitor the battery, we will also focus on the charging infrastructure. And I've heard this mentioned many times throughout this week so far. There's a huge concern. The charging infrastructure just is not available today in the market. We all know that. And the more vehicles that enter the market from an electrification point of view, the more strain it's going to put on this charging infrastructure. Even so, Volvo is actively working with various groups to make sure that we're at the forefront of trying to support the charging network throughout North America. One opportunity is back in July, you may have heard that in Europe, Volvo Group partnered with Daimler Truck, which is a direct competitor, as well as Traton Group, to establish a charging network throughout Europe, roughly 1,700 units. In August this year, we Volvo Group in North America, received a $2 million award from the California Energy Commission that we will utilize to establish a charging network on the I-5 corridor here in California. So I'm sure for the local Californians in the room, you understand the importance of this I-5 corridor. It's one of the heaviest traveled areas when it comes to freight. And with that, there are additional pollutants in the air. So with this charging network that will be established, customers will be able to utilize that network to charge their vehicles. And it's not just for Volvo. These will be public charging units available throughout the corridor from Oakland down to Long Beach, located at the Volvo dealers. So as long as the customer has a vehicle and can go and charge their vehicle at the dealership, then they're on the way to their next stop. Then you may have heard in November, just last month, there was another announcement made. The Volvo Group in North America will partner with the Pilot Group. We will utilize the Pilot and Fly & J service center gas stations across North America, which are approximately 750, and do a similar setup as in Europe by adding the charging network. So even though charging is a huge concern, Volvo is proactively working to ensure that this is not one of the reasons to slow down the whole electrification journey. So now let's take a step into the second life. What we classify as second life is when it is time to take those batteries out of that vehicle currently in the market for whatever reason. There could be it's aged. It could be that we're now offering an upgraded battery that the customer would like to change out. Whatever it may be, what will happen is Volvo will go in, take those batteries back into our network. Based off of the data that we have pulled off those batteries, we will then determine which 4R that battery pack should fall. Remanufacturing. Volvo will reman these batteries in the future. We will basically take those battery packs, break them down, reestablish them, and create them as new. We will not go down to the cell level. We will just change out all the modules and the connectors, put it back into circulation. That battery receives the same warranty as a brand new battery pack. If going through the reman process is not a viable option, then we'll look at refurbishment. Refurbishment will take the battery pack, repair the components that have wear and tear, and make it good again. And if all else fails, we will absolutely utilize recycling. So I was super happy to see that over the past day and a half, there's been a lot of focus on recycling, because we're currently in the market looking for a recycler. So if anyone is out there and you're interested, please look me up when this is over. I definitely would like to speak with you. So what we're looking from a recycling partnership is we would like to partner with someone that wants to also grow. So it's not just recycle this battery and take this precious metals and dispose of them. We want to get to a point where we take those precious metals out of that black mass and feed it back into battery production. In theory, completely closing that circularity loop. So if these areas, reman, refurb, and recycling is not an option, based off of the state of health of those batteries, because as I mentioned, some of them just still may be practically new, but the customer wanted to upgrade, perfect opportunity to utilize those batteries in a repurposing application. We're also currently looking for partners to work what we call the battery energy storage system, where we will take these batteries, put it into the storage system, and offload the power grid utilities. This is a great opportunity to not only focus on recycling those batteries and get them back into production, but also to take care of a need that we immediately have today. So how can we support not only the residential customers, commercial and industrial, but how do we support the utilities? Repurposing is a great option to do just that. So just a little bit of tidbit of information. It's calculated that by 2030, we will need 367 gigawatts of energy collected in order to offset what is needed. If you do a comparison, just 1 gigawatt equates to roughly a nuclear reactor, or even better, 100 million LED light bulbs. Huge opportunity. So we definitely want to take an opportunity to continue to drive this whole concept of repurposing. So now if we jump into the enablers. So as mentioned before, we will monitor these batteries, but we need a sophisticated system to do just that. So as we start to collect data over time, as I mentioned, we will collect, analyze, and optimize. That information will be then fed into our decision engine, as well as artificial intelligence will be used to identify which second life application that battery pack should go to. So it takes the guesswork out of it from the human aspect. But we know nothing is perfect. You'll still need human interaction. But if you can have a system that's sophisticated enough to make a proposal, then you can look at it from a point of view of logistics, location. Does this make sense? And if so, you can start your circularity model. So not only are we working with the whole digitalization aspect, as I mentioned before, partnership. We're not to the state where we can do this on our own. It's all still so brand new for most of us. I heard it this morning at the roundtable. I've heard it at lunch. I mean, there's a lot of apprehension in the market with this whole change. We don't know where the world is going. But what we do know is we're committed to make sure that we get there and do everything possible within not only the OEM's power or the individual's power, state, government, whatever it may be, but for the world in whole. So with these partnerships, we are hoping that we can get to market as quickly as possible. Currently on the OEM side for heavy duty, I'm sure you're very aware that we are just not there when it comes to volume levels, but we are quickly ramping up to get more vehicles out in that market because, as I mentioned before, 2040 is going to be a big year for us because ICE engines will no longer be available. It's all going to be electric and alternative solutions. So we definitely need to keep driving this initiative. And then if you look at it from an overall personal perspective, as you mentioned, the whole climate impact of where are we going, this whole greenhouse gas issue, everything else, the commitment from the Paris Agreement that everyone is pledging to succeed in reaching. We absolutely are dedicated to make sure that happens from the Volvo Group. Otherwise, we would not have established a whole business area called Volvo Energy, which I am super happy to be part of and very proud to be part of a momentum of this electrification journey within not only the Volvo Group, but the heavy-duty sector. So with that, just wanted to leave you with a little bit of encouragement, maybe a little scary. The future is here. We know that. We hear that. It's all over the TV. It's all over the news. It's all here. So we know that the future is here, but we also know we have to stick together through partnerships because we want to improve the world we live in and leave it a much better place for future generations. And we can only do that if we work together. So thank you not only to all of you in the audience, but also to AABC for allowing me to come and introduce Volvo Energy. And I look forward to meeting with some of you and hearing some of the opportunities you may have to offer, especially when it comes to partnering on recycling, the best solution, the battery storage solution, energy storage solution, as well as charging infrastructure. So a lot of opportunity there. So with that, thank you so much.
Thank you, Anna. Our next speaker is going to be Christiana Lininger from Voltaic. Please come up, Please come up, Christiana. She's the Director of Battery Science and Engineering at Voltaic, and she will be discussing accelerating new technology qualification with the battery index. Christiana.
Okay, so thank you so much for the introduction, and thank you all for your attention this afternoon. I'm really excited to talk to you about accelerating new technology selection with the battery index. I'm also looking forward to seeing Santa on the beach after this session. So with that, let's get started. So the take-home message of this talk, and I'll say it again at the end and a couple times throughout, is that in this current commercial market, it's important to the success of your product to be agile in the cell selection process. And Dan did a really good job of teeing us up on what it means to select a cell for an electrified product. And throughout the whole conference, we've heard a lot of the difficulties throughout that process. So let's just start with what the technology selection process is. And, you know, we've heard about a lot of new exciting technologies. We've heard about improvements in energy density, improvements in power. We've heard about improvements in safety, which are incredibly important. Heard about different shapes and different engineering designs to elevate each one of these components. So here's just a list of suppliers, of cells, of batteries we could get our hands on. And over here, we have these products. Right now, we're at the Advanced Automotive Battery Conference, but there's a lot of other electrification going on outside of even automotive. But really, the technology selection process is very simple. Which battery technology is the best choice for the electrified application? The very difficult part comes in with best choice. So to answer this question, which technology is the best choice for the electrified product? Well, of course, it depends. Are you concerned with cost? Are you concerned with specific energy? Are you concerned with power? Are you concerned with lifespan? And likely the answer is yes, not just any one of those, it's all of them. And as we can see here, just comparing various chemistries, this actually came out of Toyota Research Institutes. This is an optimization problem. We don't really get to just select one technology and get it all and go off to the races. There are trade-offs that we have to make. And we're talking about new chemistries as well as new engineering, as well as new designs that can elevate some of these things. But the reality is that it's an optimization engineering problem. And a lot of us have engineering backgrounds, and as we know, these are some of the most fun problems. So this is a really great quote out of this publication. It's difficult to find one battery technology that meets all aspects. Trade-offs must be managed effectively. And so why is this so important? Why are we so focused on the battery? It's actually really exciting in electrified products. The success of the product has a lot to do with the battery technology itself. And so this might be true in other products, but specifically for us and specifically in automotive, on the engineering side, we're talking about energy density, but on the business side, we're talking about range confidence. And again, on the engineering side, we're talking about power capability. But to the success of the product, this is about whether or not the consumer has an exceptional or a poor performance experience. And of course, time to charge, fast charge. This is our refueling experience parity. And lifespan, warranty security. This is really exciting to hear what's coming out of Volvo and how they're going to be handling that lifespan and the warranty security. But it's a hard problem to get to those points and to be able to guarantee it, and it takes many years of testing to get there. Safety is imperative for the product, but also for the industry, so that the reputation of the industry and electrification is successful. And then, of course, cost. The cost of the battery is a big portion of the cost of the product, and so driving the cost down has an impact on how competitive the product can be. And so why does it matter? The details matter because the details of the technology are really important to the product success, and that's why I think a whole conference, many of these conferences about automotive electrification are focused on the battery. And so when we are thinking about our performance requirements, we're actually really talking about or thinking about details as esoteric as the chemistry. These spinel materials have very high energy density, but they have very poor ion transport, and therefore their power capability is maybe not as good as a layered material that has phenomenal ion transport, but there's just less material in there to reduce and therefore to get capacity from. And when we're thinking about these different platforms, they have different design considerations. And we got to hear about some of these challenges from Dan when he was talking about that really cool fuel cell and the heavy duty application. But there's different physical spaces that we need to try to fit these batteries in. And this can define for us, the form factor or some sort of constraint or consideration that we're working on. So this is an optimization engineering problem. And if we had everything we like, that would be great, but this engineering problem is further exacerbated by the industry trends that we're all talking about and that we're hearing about. So there's a very high demand, and it's very exciting to have automotive in electrification, but batteries, lithium-ion batteries, have sort of been an industry outside of automotive for many years. And so this industry is now getting impacted by all of this capacity, and so this is just a new space, a new problem to solve. And we have, so in light of that, of course, manufacturing is scaling up. And we've seen the time it takes to get to a manufacturing scale up is sort of on parity with some of these timelines where we're going to be delivering all of these electric vehicles. And we have supply chain constraints, which of course we all are very, very familiar with. And so this leads to this concept that I introduced, which is agile technology selection. It's very exciting to have the opportunity to solve this problem. And I think we're all going to get there. We're all invested. We're all doing the work and doing the engineering to get there. Here, we're just introducing a concept in technology selection that can enable you to get there quicker, and you can apply it even outside of technology selection. And I'll get into that in just a moment. So what is the current status quo technology selection? Again, we got to hear about it earlier. You have some sort of performance requirements. What is the requirement of the platform you're trying to electrify? Energy density, power capability, charge time, lifespan, safety. You go ahead and go out and test and select, and this is the top down. We also heard of bottom up, but you go ahead and test and select for those requirements. So you're trying to find the right technology. After that, you get to electrify your product, which is the exciting part. And of course, these things really happen sort of in parallel, but these are kind of the main steps if we were to break it down. So what is the concept of agile technology selection? It's the exact same thing. It's just sort of adding in some key points along the way so that you can accelerate the process or be more agile throughout it. So first and foremost, technology stack up. So as you are setting your requirements and as you are selecting a technology, you are continuously looking and thinking about the other technologies that are out there. And why do you do that? You do that to enable the second tenet of agile technology selection, which is optionality. So if you are always constantly planning for a change, when the change comes, everything's fine and dandy. If the change never comes, everything's still fine and dandy. If you're not planning for it, that's when you can sort of get into this 11th hour crunch, and there might be delays, or things might need to be re-engineered or redesigned. And we are all up for the challenge, but it's not a fun place to be in. The last tenet is essentially just to speed up this process in any way that you can. And so there's probably multiple different ways to speed up the process. One that we are proposing is just modeling, because it helps inform design decisions along the way. So you can accelerate decisions. Of course, you cannot answer every problem with modeling, but it can sort of point you in the right direction to understand what part of the landscape you need to focus on. So I'm going to go into these a little bit further, those three tenets. I'm just going to preface before I go into that by saying that the electrified product development process is large. I am talking only about this qualification, which is the product development section. These tenets of agile or adding agility to your process can happen in manufacturing, research and development, and launch and in-field, but we're not talking about that section here. So this leads us to the battery index. So what is the battery index? Essentially, it is a benchmarking database that can enable you to employ these three agile tenets in technology selection. And so again, optionality, technology stack up, and acceleration of decision-making with modeling. And this is a partnership. Voltaic is a software company, and we have partnered with a physics-based modeling company as well as a test house, Energy Assurance, to make this offering. And it's part of this partnership concept. When we have these new challenges, takes new ways of thought, and very frequently, getting together to try to figure out what that might be is where those intersect. And so that's really how this came together. It brings a lot of each one of our offerings to the industry. And so we're going to start by going through, I'm going to try to illustrate each of these quickly, and then we will pass it off to the next speaker. So optionality, you maintain the ability to rapidly replace the cell. So this could be due to any number of reasons, but I have here supply constraint, maybe your program requirements change, which happens very frequently, or maybe there's something going on with the supply chain. So this is just a Ragone plot. We're all very familiar with these, looking at gravimetric energy versus gravimetric power. What's exciting about this one is that we are looking at all of these suppliers, all of these form factors, and they've all been tested in a lab completely apples to apples. So you can take this data and you can look at it as a whole comparative database to understand what is out there commercially available today. So many subgroups do subsets of this experimental work in isolation. And it has to be done. You have to understand what's out there. But we think, doing it once in an apples to apples comparison way is a lot sort of more bang for the buck and a lot more value for the industry. And so you can imagine what you would do with this. We were teed up very well by Dan's design problem that he was trying to solve, and thinking about the technologies that were available. And just being able to slot in the performance requirements from any one of these cells and seeing how it would impact your program at any point throughout your development process could be very useful. So I'll show a demo of this a bit later. As I discussed at the beginning though, when we're choosing a technology, when we're choosing a cell, we aren't just interested in the energy or the power. There's many, highly esoteric details, the anode separator, the anode tab or the separator, or something about the dimension of the cell that we need to know. It's imperative to our program or some of our design considerations. And so in addition to performance metrics, we have also done measurements inside the cell as well as outside of the cell, tabulated the safety features and provided, SEM, TEM images, elemental analysis of what's going on inside. Okay, so technology stack up. I think it's sort of inherent in the picture I've painted, but this enables you to take all of these technologies and understand how they stack up. If you have internal development where you're developing your own cells, or if you are a supplier developing a cell, you can take your cell and test it in our apples to apples method that we are publishing for transparency so that everyone can understand the experimental results, and you can put your own data in here. So how does my technology stack up? How does my new supplier's technology stack up? If I'm a supplier and I'm trying to get into an OEM, what ammunition can I come in with and say, look how great we are on this apples to apples comparison. And then here is our demonstration of it. So we're just going to go through a quick video. And this is our software. What we have over here on the right-hand side is all of the inputs. And what we're going through here is this design consideration simulation where we're setting a certain power that we need, we're setting a certain energy that we need, and we see that the landscape of cells quickly goes down to the ones that are available. So we can hover over these, we can see some of their performance parameters. We see we maybe have 5 available to us in this database. We had already boiled down by format to a cylindrical cell, but the reality is frequently we're very interested in these design details, the details inside the cell, the microstructure, all of these other quantitative measurements that need to be made. We don't want to just only know the energy or the power. And so here I'm showing, we're not going to plot these, but I'm showing each one of that's available for all of the cells in the index. And the multivariable design problem. So we don't offer plots outside of 3 dimensions, but we do let you look at all of this data alongside a third axis so that you can just sort of visualize and very quickly get to what's out there and what you could potentially use. Maybe let's say anode thickness is very important to you. Maybe a diameter is very important to you of an actual cell because of a physical consideration in your electrified platform. In addition to having this information quantitatively, we also have it qualitatively in this report format where you can look through these, you can look at the images, look at the pictures, and again, get all of the information that you need to accelerate decision making. So here we have some elemental analysis and some composition analysis. And the last thing we're going to look at, frequently you need to actually just data, the electrochemical data. So what are the discharge curves? What is the surface temperature? How is it behaving as a function of C rate? How is it behaving at different temperatures? So here we're comparing 2 cells and we're looking at the surface temperature at different C rates, and we can see, they very clearly heat up to different surface temperatures, which could be very important for your pack or your system or your design that you're working with. Okay, so we're ending here in the battery index. I'm just kind of playing around and zooming in and showing some of the cells. But I just want to emphasize, I think this is useful in 2 ways. Most of my talk has been, sort of towards OEMs using it for supplier qualification. But it's also really useful to accelerate any sort of technology development you're doing. So these are cells that are commercially available on the market. But here you are trying to electrify this platform and you have an abundance of decisions that you need to make. And there's not a lot of precedence because this is a newer industry and a newer field. So can you take all of this data and collate it and help you make decisions faster? What has been done? What kind of design considerations were made in this section of NMC cells that have this form factor? So you can collate it and use it in that way as well, in addition to using it as a supplier to see how your technology might stack up against the rest of the landscape. Okay, so I'm going to end with modeling. Modeling is the third tenet of the agile cell selection concept. And essentially, it's just trying to speed up decision making in every way that you can, because this is a long process. And so some questions that you can, so each one of these cells has a physics-based model associated with it. And some questions you can interrogate those models are, how will fast charging impact my cell? How does aging in various environments affect the performance? Which cell gets how hot in the pack and why? And how to develop, an optimal BMS algorithm, and what is the short circuit behavior? So these are just examples. I'm sure there are many other examples that audience members are interrogating their models with. So these models are both physics-based, but they have elements of equivalent circuit models, so they're actually pretty rapid, and they can and have been deployed in field, which is exciting. Okay, so I would like to conclude with the first thing I told you, because that's the only thing I want you to remember. And essentially, the take-home message is that in our current commercial market, it's important to the success of your product to stay agile in your cell selection process. I want to emphasize there's likely very many ways to do this, and I'll go back to this slide, but we are just putting in 3 tenets here: technology stack-up, optionality, and modeling. Now, you can think of agility throughout the rest of your cell development process and in any way that you wish, and maybe you don't leverage these 3 concepts. Maybe you just think of how can I be faster? How can I make decisions quicker? How can we get to the finish line quicker? Okay, so with that, I would like to thank you all for your attention, and thank you for the time to speak, and for AABC allowing Voltaic to speak today.
Thank you, Christiana. My pleasure to introduce our next speaker, our closing speaker for this afternoon session, Keenan Sahin. I know Keenan, and he's the founder and president of Camex Power, and I've heard his presentation before. This guy is going to try and persuade us that he can use less cobalt, lower the cost, and increase the performance. And that really sounds good, Keenan. So please explain how.
I will try to live up to.
Yeah, speak here. You press here.
Well, I today want to come into technology from the markets. Many times we look at the technology and try to map it into the markets. This is very unusual times. I want to, first of all, take an unusual thing and acknowledge the moderator, the chairman of the session, Mike Fetchenko, for the following reason. Not for the kind words that he spoke, but I've known Mike for a long time. And behind the scenes, he really has been a key enabler, first in the nickel metal hydride era, what I would call the infancy of electrification. And then collaborating with Argonne, bringing NMC to all 4 corners of the world and convincing people in Korea, in Japan, in China, as well as in Europe, that is a material of choice. I want to acknowledge that. Secondly, I want to condemn Santa. Terrible thing to do. For years, Santa kept promising us all kinds of things. Demand is coming, demand is coming, demand is coming. Mike, this keeps going forward, but I want to go backward. I'm doing something wrong. For a technologist who even worked at Bell Labs.
Change the world, but you can't fix the clicker, huh?
That's right, yeah. That's it. Okay.
Press forward.
That's it.
Backward.
That's it. I want to condemn Santa for the following reason. We had false expectations in 2010, 2012, 2015, 16. I went to China all over. And last year, Santa delivered the demand. All the car companies are inundated with demand. But Santa forgot to bring the supply. So we're in a supply crisis. Plenty of demand, heaven. But if you can't supply, I learned a long time ago, you are in a terrible bind. So I want to come from the market. What are the pain points in the market that we're facing now? One is cathode materials. Who knew? And the reason for that is cathode is anywhere from 30 to 50% of the cell cost. And 50% of the cathode cost is in the metals. And one metal sticks out like a sore thumb. That's a cobalt. And we got caught. We got caught. We want performance. We want to go 200 miles, 300 miles. That means high nickel. But high nickel means bad cycle life. So that's one pain point. The other pain point is the concentration in this marketplace. It is not a new industry. I'm a technologist. How do you insert technology into an industry when it consists of what I call 3-7 siblings? Call them brothers or sisters, siblings. On the cathode side, I will home in on the cathode side because that is the heart of the cell. There are at best 7 producers that account for 70% of total production in the globe. That's it. In fact, you don't even get to 7. You come to cell making, LG Energy Solutions has 25%. CATL has 30%. You're at 55% with 2 companies. And you look at 7 companies, you can't even make it to 7 companies. You're at 70 to 80%. You look at OEMs, ultimate buyers, GM, Volkswagen, Toyota, you're well over 50%. So how do you deal with an industry that's so highly concentrated? And what EVs have done is create intimate linkages between the material supplier, the mines, material suppliers, cell makers, car makers. Who's going to give the warranties? Who's going to take on the liabilities? Who's going to be around for the next 5 years to deal with vehicles that have a life of 10 years? These are huge industry issues. So obviously, I'm not here to solve. I don't believe in solutions. I believe in resolutions of issues. We have many issues. We can partly resolve them. Whatever we do today will be next generation's issues, and I wish them good luck. So my point here is, how can one simple technology at least partly address some of these issues, not problems, coming from the marketplace? So that's the big point. So now I'll post these slides. So we'll skip over some of the technical slides. Now, high nickel, low cobalt materials are now the material of choice for EVs. Yes, there's iron phosphate too. I will address that. Price and limited sourcing of cobalt has become a main issue. Cycle life declines, as I mentioned, when you go to high nickel. And we discovered, I had my team focus on the cathode particle. I said, forget about electrolyte, forget about anode. Those are important. But the critical thing is, why does this cathode material degrade? Where does it happen? We're electrochemists, we're mechanical engineers. Let's take a look at it. And even as the world went to the anode side, we went into the secondary particle and very quickly discovered that there's a very simple process going on. At the grain boundaries, the grain boundaries are unstable of the primary particles. Imagine a soccer ball with particles inside. And if the particle begins to crack, the guts begins to fill out, that's where the issue is. So we focus on grain boundary engineering as the way to deal with what we're facing. Now, you cannot do development. I've been in the R&D business since the 60s, in fact, 50s. You cannot do development at this stage unless you understand the full stage. If you want to implement it. As a former academic, I wanted to publish. I was done. But if you are in industry, you want it implemented. So how do you make sure it can be implemented? You have to go all the way to the end, even though you're at the beginning. So with using vertical integration and incremental improvement, because R&D people are not like herd of cats. That's the typical description. They are a herd of tigers. They attack you if you antagonize them. Cats don't, they just go away. So how do you tame a team of tigers to do incremental development? It's not easy. They want to jump to the next grass. Now I said, guys, just keep doing, keep doing, keep doing, keep doing. So we then invented and patented globally, because you can't be in implementation business unless you get strong patents. And that's not easy in this space. The white space is highly limited. So we focus on, as I mentioned, cathode grain boundaries. We enrich the grain boundaries with this precious metal called cobalt, and we try to minimize it. It turns out when you put the cobalt primarily in the grain boundaries, you get amazing properties. So that's what we did. And we improved NCA, NMC, LNO, and MCA while keeping overall cobalt content low. So we did that. Now about Chemex Power, I will just, this is our vertical integration. We have everything. We could be in production. We could actually raise money and make a huge amount of the materials that we have invented, but we won't. Why? Because cathode really is the purview of big companies. But we do have a lot of laboratory facility, and we have extensive cell making so that we can go from one end to the other. We make cells, we scale it up, we come back, and all that. And these are some of our facilities, excellent colleagues. They're not all R&Ds, PhDs. We have technicians, we have people who sweep the floor. That's what I do, make sure I sweep the floors, because when you're the president and founder, that's one of your duties. How do you clean up? Not just deal with them. And we made sure we're ISO certified so that we have standard operating all of those things. Why? Because our business model is to enable others, especially in the cathode space. Have we succeeded? Yes, we have. Quietly. And it's not easy to convince big companies to adopt technology. You can't go to procurement and say, I have technology, will you buy it? They say, what's your product? Who are your competitors? What's your price? You say, I have none of those. They say, go away. So here we are, Samsung in 2020 licensed this. And as far as I know, they're extensively using GEMX technology in their cells. The big kahuna was in 2022. LG Energy Solutions, just after they went public, 60 billion valuation, almost equivalent to General Motors. Almost equivalent to General Motors, and they licensed it. And with Samsung and LGS, this technology is available to the third of the global cell market. And more is coming. The other one is actually a cathode maker that took over Johnson Matthey's business. So what is this platform that I talk about? And I have to tell you, it sounds simple, but many inventions inherently are simple. The most powerful inventions are very simple. So let me get into our patents a little bit. We had to make sure patents are defensible. If you have a patent that you cannot see, understand that others are practicing it, it's a useless patent. In the case of GEMX, There's something wrong, Mike, but I will keep dealing with it, going back and forth. Maybe it keeps people's attention. I don't know. I don't know. Our core patent, which is what convinced the Koreans, is that no matter how you achieve cobalt enrichment in the grain boundary, it falls under our patents. And we've expanded that to aluminum. Now, a lot of people are doing cobalt doping and aluminum doping and so on, maybe without realizing it, they're really practicing the patents. So they are these patents, and I've briefed DOE, DOD, and so on behind the scenes. This is well known. It is, in so many ways, enabling patents. Now, these are some of the properties, benefits you get with grain boundary enrichment. By the way, there's a ton of literature now coming out of Korea, coming out of Europe, coming out of our national labs. You get reduced total cobalt, you get higher power, you get higher energy, better extreme temperature performance, longer cycle life, lower impedance growth, flexible synthesis with minimal processing steps, improved electrode and self-fabrication properties. Here's another way of presenting it across the chain. And you can say, well, how can this be? Well, I will fall on recent literature, tons of literature coming out. And here are those points that the literature indicates. And I have references, we will post them on our site. And one of the things that I want to highlight here is reduced rock salt formation, reduced secondary particle cracking, reduced dissolution of metals from the cathode, and reduced lithium impurities. Now, I will give you some selected examples. I'm skipping over a lot of the literature. Here's an example. We've achieved, by the way, 6% cobalt NMC. And here's NMC, 6% cobalt. And that's the black line. And you can see its performance. And that's grain boundary enriched, same thing, NMC, accelerated cycling at 4 to 5% degrees, and look at its capacity retention, and look at its capacity at C over 20. Again, you'll see these, we'll post these results. Here's our data on cracking. Without grain boundary enrichment, cracking is a big issue. It's 10, 15, 20% cracking. When a secondary particle cracks, it's immediately exposed to the electrolyte. But when a grain boundary enriched material, even though it doesn't crack that much, if it cracks, it becomes 2 secondary particles because it's cobalt coated. Now, here is, for those of you who are interested in the boundaries, grain boundaries, there's no rock salt formation if you do grain boundary enrichment. And this is about gas formation and so on. Now, let me skip over this and look at process considerations. You might say, is this some complicated process? No, it's not. In fact, here's one advantage of this process. Because this treatment absorbs excess lithium, which you have to put in for high nickel materials, you don't have to do water washing. Just that makes the process free. And here's our data on water washing. In fact, it's even better with this process. And also, here's a key slide. We have refined the process to a point where this second step, after the material is synthesized, can be as short as 5 minutes. Typically, we use 2 hours, but recently we've realized that it can be 5 minutes, 10 minutes, and it can be in rotary kilns. It is not a second calcination. I used to say second calcination, people would say, well, that's 18 hours. Actually, our primary is, I'm sorry, yeah. So now, let me come to one of the pain points in the marketplace, which is the proliferation of xEVs. The presenter before, I think, articulated very nicely. So how can we deal with that? How can we deal with that? Each EV has its own specs. Custom formulations in this highly concentrated market is impossible. Good luck to you. You go to a cathode producer and you say, this is my spec. Will you make it? They can't. They're in a scale business. So there's time. Demand is here. Santa is delivering good news and bad news to us. How are we going to deal with it? So we have, because we have vertical integration in our company, here's what we did. We actually, using this technology, which is very straightforward to apply, generated product families. There's 9% NCA, cobalt, 8%, 6%, and so on. And on the left side are the customer requirements. It's a showroom concept. Time is of the essence. There's no time for formulation. You can't even find suppliers. So we're saying, look, we have done the heavy lifting, and we even did the precursors, which is another issue in the marketplace. We did the precursors. We have the recipe, and come take a look at these product families, down select, okay, comes close. Our model is coming in 2 years, 3 years. It doesn't have to be exactly what we have in mind. Fine. Then you can take that recipe to the cathode maker, and if you give enough of an order, they will make it. They will make it. But this way, you can qualify it at a place like our shop, where we can scale it up because of this vertical integration and so on. So in our ways, we're trying to deal with this pain point in the marketplace. Wonderful. I did the analysis. This is the ideal profile of a mate I want, but there are no such mates. It's not available. So what do you do? And here's another example I wanted to give from this family, and we have lots of data like that. The reason I wanted to give this example is the following. There's another pain point in the marketplace, cost. And costs are accelerating. How do you deal with it? My viewpoint is, let's present our data to business people in a way that they understand. Business people don't understand cycle life. You say, look, my material goes to 1,000. Great. My material goes to 15,000. That's great. Actually, it isn't. Look at this data. I've presented the data, exactly the same data, in 2 ways. There's the cycle number. Let me now move to the next one. I'm presenting it in terms of years. An xEV goes in a cycle, each cycle, 300 miles. We drive a car 15,000 miles a year. That's 50 cycles a year. That's it. 10 years, that's 500 cycles. We already have material, and we've shown it, 6% cobalt, and the capacity retention, if the required capacity retention is 80%, that's a lifetime of 13 years. So the emphasis has to be on increasingly cost reduction. How do we reduce costs? And we're sharply focusing on that, not new technologies. We have enough. How do we reduce costs? And that's where I want to make some additional points. This is another slide. It's another product family, NCA. After treatment. After treatment. You have 811, fantastic capacity, cycle life sucks. Use 15 minutes in a rotary kiln, and you can actually upgrade it. Here's an example. There's the NMC 811. After grain boundary enrichment, performance improved. Not much cost. And in fact, you don't, anyway, I will briefly get into 2 other areas because single crystals have, this is the first time I'm showing this data, have become very popular. We've looked at single crystals, and single crystals are not pure single crystals. They are also clusters of materials. We grain boundary enriched it, and look at the performance improvement. We bought this material commercially, 5% cobalt. And there's the grain boundary enrichment. And I will show one more slide, then I think I will stop. There's iron phosphate. And I'd like iron phosphate, please don't take it as dogmatic, but there's also high manganese. And we have grain boundary enriched 40% high manganese, and we're now on our way to 60% manganese. When you grain boundary enrich it, look at the performance you get with high grain. So that's my conclusion, that we have to come to technology, not from technology to market, but in this highly concentrated, highly linked, the siblings have married each other and they formed one entity almost. How do you deal with the pain points? Because as consumers, we're the ones. So I've tried to pass on some perspectives. And once again, Mike, I want to acknowledge, not because you said some nice things about me, because I've been in the industry a long time. Thank you very much.
Thank you, Keenan, for the nice talk and kind words. I'd also like to ask Dan and Christiana and Anna, please join. We're going to take a 1.5-minute video from our hosts, Toyota, for prior to the Q&A, who are hosting kindly our network reception. So, Craig, are we? I heard a rumor, Dan, that you produced that video yourself and just did it this morning prior to the, is that an accurate rumor?
I'm still on Eastern time, so I had a lot of time in the morning.
Anyway, we'd open up the question and answer period. If you have a question, please raise your hand. We'll get a microphone for you. And please identify yourself by your name. And also, we have a question right up in front, Craig. I'm not sure who's going to bring the microphone. Please identify yourself with name and your affiliation, and also identify who your question is directed to, please. But while we're getting that ready, let me ask a question in advance. First, let me start with Dan. All the other car companies seem to be focused on pure EV. And Toyota's been a king of hybrid technology, and you guys, you know, some companies are focused on fuel cell, but you guys seem to be really taking a different path. I guess I wonder, is pure EV something that Toyota is going to be pursuing also, or are you convinced that fuel cells are the way to go?
I guess it really depends on the application. So I think just based off the energy density, fuel cell has a lot better usage conditions. So like I showed in the heavy duty application, heavy loads, there's a lot better use condition or market analysis that shows it's a good option, versus maybe on the passenger vehicle, there's a lot better cost of ownership analysis for the BEV. But it's more about diversification and maybe optimizing what resources you have and grid strain as well. So hydrogen alleviates some of that, which has been discussed in some of the earlier talks today as well. So there's looking at different possibilities for different market segments, and even not just a market segments, but also just regionally as well. So like if you went to the outback of Australia, you have a lot less infrastructure. So fuel cell would make a much better base case in those locations.
Thank you very much. We have a question up front, please.
Hi, my name is Jennifer Jones. I've mostly been in healthcare, but I've always been interested in, I consider myself a revolutionary, and met Elon Musk on a video. So I joined the electric vehicle revolution, and the only way I could participate was to buy shares, stock. So by the time I did that, anyway, my question is totally unrelated. What about graphene? What do you know about graphene? Graphene.
Graphene.
Yes, a single cell electric conductor.
Well, we had a talk from Kawa.
Yeah, I didn't hear it.
Oh, you didn't hear it this morning. Maybe we can correct. You know, Keenan, you're in the materials business. She has a question about graphene additives. Do you want to try and tackle that? Well, graphene additives for various.
Additives and graphene and so on.
She didn't say additive. She's correcting me.
I see. Okay. These are all exciting technologies, and I've attended many presentations on graphene. At the beginning, it was very promising. The costs were very high. The costs have come down. You can even harvest it from a candle if you want to. Here's the issue, though. Again, coming at it from the market to technology. And I'm addressing xEV industry, EV industry, not portable. Warranties is a big issue. And the linkages of the whole supply chain is a big issue. And making sure technologies all like each other, that they team up nicely, is a big issue. So graphene is, I think, making inroads. It's relatively new. And so that's how I would come at it.
Thank you, Keenan. Next question, up front, please.
So this is Lou from Aurora Quality Science, a Boeing company. So my question is addressed to Kenan. So I understand the benefit of cobalt on the boundary of the granular materials like NMC, NCI. So when you license your technology to OEMs like Samsung, LG, what do they need to implement your technology into the material? Do they need new facility, new process, new equipment, or you just provide them formula to achieve that? So how do they achieve what you shown here?
Mike, could you summarize?
Yeah, how easy is it to implement your technology? If you were making existing cathode materials, would you have to scrap that line and start over, or is it something that is a post-treatment?
It's post-treatment. It's a second step. For instance, if you're making NMC, it might take whatever calcination time you're using in an oxygen-rich furnace, 18 hours and so on. We have a material that we make in 8 hours, but be that as it may, after you take NMC from that process in a rotary kiln, in as short a time as 15 minutes, 20 minutes, you inject cobalt, and you have to adjust the time and temperature to get it into the grain boundaries. If you don't have that combination, then it gets into the bulk and it loses its impact. So it's a very straightforward process, and you don't need water washing afterwards. In fact, if you don't have to water wash your NMC, because this process absorbs the excess lithium.
So easy to implement.
Very straightforward, and you don't need special equipment.
So I'm going to ask a follow-up question in a moment, but let me go to Anna next for a moment and say, okay, we've heard all about supply chain crunch. We hear some companies doing offtake agreements with Indonesia to get their nickel secured, and everybody seems to be teaming up. So the car companies are teaming up with the cell makers who are teaming up with the miners. I guess one of the things that I was interested for hearing from Volvo is, what's your strategy? Do you have some key alliances, or is it regional or global? Are you worried about supply chain crunch?
Great question. And the simple answer currently is I am super worried about the supply chain crunch. Not only because of we know that supply chain disturbances that we have all felt over the last 3 years, but specifically when it comes to batteries. So based off of your question, we currently have a partner with our batteries, but we are always looking to see what can we do from a local sourcing perspective.
Have you
We're just not
identified
there
that
yet.
partner yet, or that's not public?
No, we have not. It's just we're not there yet, but absolutely, going back to what I mentioned before, the ideal situation would be to not only source the battery within North America, but keep the batteries within North America to ensure that the supply chain issues are no longer an issue.
Thank you. Christiana, I had a question on, so you came up with the concept of, I think, agile design change. And consumer companies are super nimble and love that. But the automotive companies, Michael, are you crazy? You know, this is going to take 4 years to qualify on a production intent line. So I guess, how do you view the automotive people embracing your philosophy?
Yeah, it's a really great point. And actually, Voltaic, we're a software company, so we're very similar to this consumer market, and we have a lot of these tenets in our day-to-day practice in what we build. And so I think the automotive industries have a different background and different history, and I think they're up for the challenge. And I think we all recognize that we need paradigm shifts in some ways of doing things, and I think that they're the first to point some of those out. And we're just trying to offer solutions and tools that can enable that. And I mean, I'm excited for my first EV, which hopefully I'll get in the next couple of years. And so I think we'll definitely get there.
Thank you. I got a question for Keenan and Dan, and let me start with Keenan. You showed, I don't know if anybody was confused, but there's a lot of good ideas that people have, whether it's cobalt enrichment like you've done. We heard questions about graphene. We heard about carbon nanotubes. We heard about binders. Lots of good ideas sometimes get stalled in the laboratory for either they couldn't be scaled up or cost or whatever reason. So one of the big things that I saw, you mentioned that GEM-X cobalt enrichment is commercial, is through Samsung and LG. And you got a question from the gentleman in front about, how easy it is to implement. But one of the things that I was confused on, is this exclusive to those companies, or are you planning to, is it available to anyone that wants it? And if it is available to material suppliers or cell makers or automotive companies, or what is your licensing strategy?
Model. Mike, we started with cathode makers, and our business model is we can make it, but we won't. So we don't compete with those who license, and the license is not naked license, it's deep technology transfer. And because of vertical integration concept, since we've been implementing 2003, we go from the material to the electrolyte to the anode, so that the complete cell design is also part of the cathode design. But it is available, really, and we try to make it very straightforward. It's not just a license, paper license. We have ability to teach. That's why I showed the ISO certification. All our SOPs and so on are all documented. We're a teaching organization.
So clarify one thing. You said you focused on material. Is it available to anyone that wants one?
With a license, we make it available. We don't sample it, but we do. If a company is interested in licensing, we do. Yeah.
Okay, I got two questions, but let me ask a quick one to Dan. On the fuel cell technology, the big question is, I've been in this business for a long time. Fuel cell was, sometimes you show catalyst loadings for performance, but there's costs associated with that. But the bigger issue was fuel cell technology makes sense depending on the cost of the hydrogen production. And the cost, the low-cost hydrogen is typically the black or dirty hydrogen, and the more desirable hydrogen is typically more expensive and green. What is Toyota's philosophy on where to get the hydrogen, how to get the hydrogen? Will it be, what level of green to black, and what's the cost? Is the consumer going to be penalized or subsidized to, be encouraged to use it? Short question.
Unfortunately, I don't have the answer to that. But I guess whether or not you're using pure green hydrogen or a mix of different methods to get hydrogen, there's still benefits to at least localized emissions. So for example, in the port area, as long as if you remove some of the emissions from that local area or that corridor, you're at least helping those communities. So there's still some benefit depending on how the energy is collected, as opposed to just diesel emissions and those other particulate matter that goes into the air.
So are you doing anything to, what's Toyota doing on the hydrogen supply infrastructure? Or is that something you're expecting governments to do, or partnering with others?
We have partnered with different fuel companies. So I think a few of the legacy petroleum companies are switching to hydrogen. So we're a part of different consortiums, and at that point to help amplify the infrastructure so there can be better adoption or more quick adoption in the future. But I would need to discuss with the other people in our fuel cell solutions group to give you a better answer.
Thank you. Sorry, thanks for your patience.
Cool.
Your name and affiliation. And
Austin Teledyne. That's less important though. More important, you mentioned optimization and monitoring of batteries. How does that look for vehicles that have a second owner? Because in theory, that's when the battery industry is going to be at its greatest stake and the batteries are closest to failure.
And who's your question directed at?
Anna.
Anna.
Thank you for the question. So you're correct. I mean, during the first life, we're easily able to monitor that vehicle as it rolls off the production line into those customers' hands. But even so, during second life as well, because as mentioned, we do classify second life as finding a new application. So in theory, those batteries are still Volvo property until it's handed over to that customer once again. So with the Volvo program that we have, the Gold Contract, anytime an electric vehicle is purchased on the truck side, there's a 5-year minimum contract that's attached to that purchase. So that is a bumper-to-bumper contract. So we are able to monitor that battery and replace it for whatever reason up front, so there's no concern from a customer perspective. Even so, if it goes through the remanufacturing process, we create this, what we call digital twin. So we're constantly monitoring that battery, regardless if it's production or even through remanufacturing, as long as it's within Volvo's facility and vehicles, we're able to monitor it. Now, once we get to a state that we could potentially say, provide it to a recycler, then we lose visibility. But then from that perspective, we, Volvo, have committed and made sure that that battery did not end up in that landfill. We actually handed it over to that recycler.
Thank you. Question?
Yeah. Hi, Stephen Chung from Rejoule. We do battery diagnostics for repurposing and remanufacturing. My question's for Anna, kind of along the same lines of what you were just talking about. I know a lot of collection rates of automotive parts in general is quite low going back to the OEMs. So what are some strategies that you have on actually collecting or increasing the collection rates specifically of your EV batteries?
Thank you for the question. And you're correct. I mean, and it's to the point that the market is not saturated yet with the information. So what we are doing is we are utilizing our technology group as well as our IT infrastructure to monitor those batteries and build those algorithms that will eventually feed that decision engine to decide which application it will go into. So we are using the information that we've collected over time to simulate different opportunities to say, if this battery has this failure, what should it do? But to your point, we're not there yet because we just don't have enough vehicles in the market, but we will be there eventually.
Thank you, Anna. Question.
Hi, this is Natisha from Comments. My question is for Dan. So, Dan, you talked about a lot about battery evaluation and all of that. Would you like to talk about a little bit about fuel cell evaluation, cycle life, degradation, and durability of that? Thank you.
Unfortunately, I'm the battery man and not the fuel cell man.
Okay.
I think the person working on fuel cell just left a few minutes ago. But I guess based off you had specific questions about how we do testing, or
No, like you shared a lot of data in the presentation. So would you like to talk about like how does the fuel cell durability and longevity looks like for the full cycles and things like that?
Maybe if you know, Dan, is it proton exchange membrane and
Yes.
what catalyst is used, for example, and if operating temperature? Maybe any of that you can comment on, or would you like to? We can meet at the
Yeah,
coffee.
we can meet
after.
later too. Can I ask another question then?
Sure.
Yes, I think
Just
maybe
taking the
maybe
pause,
last
maybe.
question today.
Okay, if there's no one, then I would go. Okay, thank
Go
you.
ahead, go
So
ahead.
my question is for Christina. So for Voltaic, so we talked a lot about agility. I also saw some material about warranty and recalls. Would you like to talk about a little bit about that?
Yeah, that's a great question. I'd also love to hear from my colleagues because my comment on warranty and recall, we're not actually the ones experiencing the warranty and the recall, but it's certainly a big problem for the industry to work through. And a lot of the engineering that happens during the program development is working towards trying to rectify, eliminate, mitigate against warranty and recall. And so, coming from an engineering background, I just think good engineering practices from the get-go can continue to de-risk it. But, there's even processes outside of the OEM, like the manufacturer and all of these external considerations, and it's further exacerbated by the supply chain constraints. Materials get changed out without notification, and it can be very, very difficult problem. And so what we offer is data techniques that can help find these things. And it's really just this concept of looking for the needle in the haystack. And again, if my colleagues have anything to comment on it, because they are more on the end of the recall than we are. We are working to mitigate against it.
I'll actually try that. It was from BASF going into an automotive company to try and introduce your material. You say, well, who makes the decision? Is it the automotive company or the cell maker? And sometimes you get confused on that. But the warranty replacement question is actually the key, because an automaker can say, we would really like to switch from 622 to 811. But if it's the cell maker that's got the warranty obligation, finally, the buck stops there and they make the decision. So it's interesting that the guy who goes to the dealership and wants to buy the car, he can say, oh, I would like LFP or I would like NCA. No way. Here's what's offered. And if you want a warranty, it's not even the automaker often, but it's the cell maker that makes the decision. So where in the value chain you should try to introduce your new material sometimes can be confusing. And typically they have to both decide.
Mike, can I make a elaboration on that?
Briefly, I think Craig's going to blow a gasket.
That's not true. Mentioned these 7 siblings, and actually there are 7 clusters of entities, and now they are intermarrying. And for instance, Volkswagen is getting into a battery business, and Northvolt is vertically integrated. So these separations are being blurred, which creates even more complex warranty issues.
Thank you. You're right. I'd like to thank everybody for sticking around for this last session, and I'd like to really also join me in thanking our speakers for an excellent session. Craig,
Yes, thank you.
Where is the reception?
And so that'll bring us to our networking reception, which is in the exhibit hall. So please join us down in the exhibit hall by our reception sponsored by Toyota. So enjoy your evening, and we'll be back here at 9 o'clock in the morning. Thank you.